Before stars, before space, before time itself, there was nothing. Or maybe something. Then suddenly everything began. In a tiny fraction of a second, the universe exploded into being. It was hot, dense, and full of energy. This is what we call the Big Bang. But if the Big Bang created the universe, what caused the Big Bang? Scientists have searched for answers for decades. They've found ancient light still travelling through space. They've seen galaxies moving apart and time stretching like rubber. In 1964, they discovered a strange glow coming from every direction, a leftover signal from the beginning. But even now, the moment before the Big Bang remains a mystery. Could there have been something before everything? And if so, what? Before we begin the journey, let us know where in the world you're watching from, and what time it is for you right now. Post it in the comments below, and settle in for a fascinating ride through space. The story of the universe, as understood by modern science, begins not with an explosion in space, but with the expansion of space itself from an incredibly hot, dense state. This foundational idea is known as the Big Bang Theory. It describes how our universe evolved from its earliest moments to the vast, complex cosmos we observe today. The theory does not attempt to explain what existed before this moment, nor what caused it, but rather provides a comprehensive framework for the universe's development after its initial state. It is a scientific model built upon a bedrock of observational evidence and theoretical predictions, which has been refined over many decades. The conceptual seeds of the Big Bang Theory were sown in the early 20th century, a time of profound shifts in scientific thought. Albert Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity, space, and time. It proposed that gravity is not a force acting at a distance, but rather a curvature of space-time caused by mass and energy. When scientists began to apply Einstein's equations to the entire universe, they found that a static, unchanging universe, as was commonly believed at the time, was unstable. Einstein himself initially added a cosmological constant to his equations to force a static solution, a decision he would later call his biggest blunder. Independent of Einstein's initial preference for a static universe, several scientists began to explore the implications of a dynamic cosmos. In 1922, Russian physicist Alexander Friedmann developed solutions to Einstein's equations that described an expanding universe. His work, however, was not widely known in the West at the time. The crucial observational evidence began to emerge from the realm of astronomy. Vesto Slipher, an American astronomer, had been observing the spectra of spiral nebulae, which we now know are galaxies, since 1912. He found that most of these nebulae were moving away from Earth at very high speeds, indicated by a shift in their light towards the red end of the spectrum, a phenomenon known as redshift. It was a Belgian priest and physicist, Georges Lemaître, who, in 1927, independently derived the expanding universe solutions from general relativity and crucially connected them to Slipher's observations. Lemaître proposed that the universe began from a single, extremely dense point, which he called the primeval atom. He suggested that this atom then expanded and diversified, eventually forming the universe we see. His work, initially published in an obscure Belgian journal, gained wider recognition when translated into English in 1931. The most compelling observational evidence came from the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California, Hubble, along with his assistant Milton Humason, made groundbreaking measurements of the distances to these spiral nebulae. By 1929, Hubble announced his discovery. The further away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, provided powerful empirical support for the idea of an expanding universe. If everything is moving away from everything else, it implies that, in the past, everything must have been much closer together. This was a pivotal moment, shifting the scientific consensus from a static to a dynamic universe. The term Big Bang itself was coined in 1949 by British astronomer Fred Hoyle during a BBC radio broadcast. Hoyle was a proponent of the rival steady-state theory, which proposed that the universe was eternal and unchanging, with new matter continuously being created to fill the gaps left by expansion. Hoyle used Big Bang somewhat derisively to describe Lemaitre's theory, intending to ridicule its seemingly abrupt beginning. Ironically, the catchy name stuck and became the widely accepted term for the theory it was meant to discredit. While the observational evidence for expansion mounted, theoretical work continued to strengthen the Big Bang model. In the 1940s, George Gamow, along with his students Ralph Alpher and Robert Herman, made key predictions based on the hot, dense early universe. They reasoned that if the universe started from such extreme conditions, it would have been hot enough for nuclear fusion to occur in its earliest moments, leading to the formation of light elements like hydrogen and helium in specific proportions. Furthermore, they predicted that the residual heat from this early hot phase should still be detectable today, as a faint glow of microwave radiation permeating the entire universe. This prediction, made in 1948, would become one of the most significant pieces of evidence for the Big Bang. The accidental discovery of this cosmic background radiation in 1964 by Arno Penzias and Robert Wilson at Bell Labs provided the smoking gun. They were working with a new horn antenna and kept detecting a persistent uniform static or noise that they could not eliminate. It came from every direction in the sky, regardless of the time of day or year. Simultaneously, researchers at Princeton University, led by Robert Dick, were independently searching for this very radiation, unaware of Penzias and Wilson's discovery. When the two groups connected, it became clear that Penzias and Wilson had stumbled upon the cosmic microwave background, CMB, the faint afterglow predicted by Gamow and his colleagues. This discovery effectively sealed the fate of the steady-state theory and cemented the Big Bang as the leading cosmological model. The Big Bang theory, therefore, is not a description of an explosion that happened at a specific point in space, with matter flying outwards into an empty void. Instead, it describes the expansion of space itself, carrying galaxies and all matter along with it. Imagine a balloon being inflated. Dots drawn on the surface move further apart as the balloon expands, but no single dot is at the centre of the expansion, and the dots are not moving through the balloon's surface, but rather the surface itself is growing. Similarly, in the universe, every point appears to be the centre of the expansion, and galaxies are not rushing through pre-existing space, but the fabric of space-time between them is stretching. This stretching causes the light from distant galaxies to be redshifted, providing the primary observational evidence for this ongoing cosmic expansion. Over the decades, further observations and theoretical advancements have continued to refine and support the Big Bang model. The observed abundances of light elements in the universe, such as hydrogen, helium, and lithium, precisely match the predictions made by the Big Bang Nucleosynthesis theory, which describes element formation in the first few minutes after the Big Bang. The large-scale structure of the universe, with its vast cosmic web of galaxies and voids, also aligns with predictions from the Big Bang model, especially when combined with the concept of dark matter and dark energy. While the Big Bang theory provides an incredibly successful framework for understanding the universe's evolution from a tiny fraction of a second after its beginning, the question of what initiated this expansion, or what existed before, remains a profound area of ongoing scientific inquiry and speculation. One of the most profound and counterintuitive aspects of observing the universe is that when we look out into space, we are simultaneously looking back in time. This seemingly magical ability is not due to any special properties of our telescopes, but rather a fundamental consequence of the finite speed of light. Light, the fastest thing we know, travels at a specific, measurable speed through the vacuum of space. This speed is approximately 300,000 kilometers per second, or about 186,000 miles per second. While this speed seems incredibly fast in our everyday experience, the distances in the cosmos are so immense that light takes a considerable amount of time to travel from its source to our eyes or our instruments. Consider the most familiar example, the Sun. The light we see from the Sun left its surface approximately 8 minutes and 20 seconds ago. This means that if the Sun were to suddenly vanish, we would not know about it for over 8 minutes. We're always seeing the Sun as it was in the recent past, not as it is in the present moment. This principle extends to every object we observe in the universe. The further away an object is, the longer its light has been travelling to reach us, and consequently, the further back in time we are seeing it. To manage the immense distances involved in astronomy, scientists use a unit called the light year. A light year is not a measure of time, but a measure of distance. It is the distance that light travels in 1 Earth year. This distance is approximately 9.46 trillion kilometres, or about 5.88 trillion miles. Using this unit, we can grasp the scale of the cosmos. For instance, the nearest star to our solar system, Proxima Centauri, is about 4.2 light-years away. This means that the light we receive from Proxima Centauri left that star 4.2 years ago. We are seeing it as it was 4.2 years in the past. Now, extend this concept to galaxies. The Andromeda Galaxy, our closest large galactic neighbour, is about 2.5 million light-years away. When we gaze at the Andromeda Galaxy through a telescope, we are seeing light that began its journey 2.5 million years ago. This light originated when early humans were just beginning to evolve on Earth. The implications are staggering. Every image of a distant galaxy is a snapshot from the past. This principle is the cornerstone of observational cosmology, allowing astronomers to piece together the history and evolution of the universe. Telescopes, in essence, become time machines. By observing objects at progressively greater distances, we are effectively looking at different epochs in cosmic history. The most powerful telescopes, like the Hubble Space Telescope and more recently the James Webb Space Telescope, are designed to peer deep into the universe, capturing light from objects billions of light-years away. For example, when astronomers observe galaxies that are 10 billion light-years away, they are seeing those galaxies as they appeared 10 billion years ago, when the universe was only a few billion years old. At these immense distances, we are observing the universe in its infancy. We can see the earliest, most primitive galaxies, which look very different from the mature, well-formed spiral and elliptical galaxies we see closer to us. These early galaxies are often smaller, more irregular, and undergoing rapid bursts of star formation. By comparing these ancient galaxies with closer, younger ones, scientists can trace the evolutionary pathways of galaxies over cosmic time. The furthest back in time we can see with a light is to the cosmic microwave background, CMB radiation. This faint glow, detected across the entire sky, is light that was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for the first stable atoms to form. Before this time, the universe was so hot and dense that light could not travel freely. It was constantly scattered by free electrons and protons, making the universe opaque, like a dense fog. When the universe cooled and atoms formed, electrons combined with nuclei, and the universe became transparent. The light from that moment, now stretched and cooled by billions of years of expansion, is what we detect as the CMB. It represents the baby picture of the universe, the oldest light we can ever hope to observe directly. Beyond the CMB, our understanding relies purely on theoretical models, as no light from earlier epochs can reach us. However, the CMB itself provides invaluable information about the conditions of the early universe, including its temperature, composition, and slight variations in density that eventually grew into the large-scale structures we see today. Different types of telescopes allow us to observe different wavelengths of light, each revealing unique aspects of the universe's past. Optical telescopes observe visible light, showing us stars and galaxies as we typically imagine them. Radio telescopes detect radio waves, which can penetrate dust clouds and reveal regions of star formation or distant active galaxies. X-ray telescopes observe high-energy X-rays, allowing us to study phenomena like black holes and hot gas in galaxy clusters. Each wavelength provides a different window into the past, painting a more complete picture of cosmic evolution. The ability to look back in time is not just a fascinating curiosity, it is a critical tool for testing and refining cosmological models, including the Big Bang Theory. If the Big Bang Theory is correct, then the universe should have looked different in the past, and these differences should be observable. The fact that we see galaxies evolving over time, the presence of the CMB, and the distribution of light elements all provide strong confirmation of the universe's dynamic history, as described by the Big Bang model. Without the finite speed of light and our ability to measure and interpret it, our understanding of the universe's origins and evolution would be vastly more limited, confined to only the present moment of cosmic existence. The expansion of the universe is not something we can directly see in the way we observe an object moving away from us in everyday life. Instead, scientists infer this expansion from a crucial piece of evidence: the redshift of light from distant galaxies. To understand redshift, we first need to briefly consider the nature of light itself. Light is a form of electromagnetic radiation, which travels in waves. Like all waves, light waves have a wavelength, the distance between two consecutive crests or troughs, and a frequency, the number of waves that pass a point in a given amount of time. The colour of visible light depends on its wavelength. Red light has the longest wavelength, while violet light has the shortest. The phenomenon of redshift is an example of the Doppler effect, which is familiar from sound waves. Imagine an ambulance siren. As the ambulance approaches you, the sound waves are compressed, leading to a higher pitch. As it moves away, the sound waves are stretched out, resulting in a lower pitch. The same principle applies to light waves. If a light source is moving towards an observer, the light waves it emits are compressed, causing their wavelength to shorten. This shift towards shorter, bluer wavelengths is called blue shift. Conversely, if a light source is moving away from an observer, the light waves are stretched, causing their wavelength to lengthen. This shift towards longer, redder wavelengths is called redshift. In astronomy, redshift is a critical tool. When astronomers analyze the light from stars and galaxies, they use a spectroscope to break the light down into its component colors, creating a spectrum. This spectrum contains dark lines or bright lines at specific wavelengths, which are like fingerprints of the chemical elements present in the star or galaxy. For example, hydrogen atoms absorb or emit light at very precise known wavelengths. If a galaxy is moving away from us, these characteristic spectral lines will be shifted towards the red end of the spectrum, compared to where they would be if the galaxy were stationary. The amount of this redshift directly tells us how fast the galaxy is receding. The systematic observation of redshift in distant celestial objects began in the early 20th century. Vesto Slipher, an American astronomer at the Lowell Observatory, was one of the pioneers in this field. Starting in 1912, he meticulously measured the radial velocities, motion towards or away from us, of various spiral nebulae, which were then thought to be gas clouds within our own Milky Way galaxy. To his surprise, Slipher found that the vast majority of these nebulae were exhibiting significant redshifts, meaning they were moving away from Earth at tremendous speeds. By 1917, he had measured the velocities of 25 nebulae, and only a few showed blue shift. This was a puzzling observation at the time, as it implied a general outward motion from our position. The true significance of Slipher's redshifts became clear with the work of Edwin Hubble. Working at the Mount Wilson Observatory in California in the 1920s, Hubble made two monumental contributions. First, he definitively established that many of these spiral nebulae were not gas clouds within our galaxy, but were, in fact, independent galaxies far beyond the Milky Way. He did this by identifying a type of variable star called Cepheid variables in some of these nebulae, which allowed him to accurately determine their distances. Second, and most crucially for the Big Bang Theory, Hubble combined his distance measurements with Slipher's velocity measurements. In 1929, he announced his groundbreaking discovery. There was a direct relationship between a galaxy's distance from us and its recession velocity. The further away a galaxy was, the faster it was moving away. This relationship is now famously known as Hubble's law. It can be simply stated as velocity equals Hubble's constant multiplied by distance. This linear relationship was a profound revelation. It was not just that things were moving away, but that the rate of their recession increased with distance. Hubble's law provided the strongest observational evidence yet for an expanding universe. If all galaxies are moving away from each other, and the further ones are moving faster, it implies that the space between them is stretching. It's crucial to understand that this is not like an explosion, where fragments fly outwards from a central point. Instead, it's the fabric of space itself that is expanding, carrying the galaxies along with it, much like dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move further apart, but no single dot is at the centre of the expansion, and the dots themselves are not moving on the surface, but the surface itself is growing. Similarly, in the universe, there is no central point of expansion. Every observer, no matter where they are located, would see all other galaxies receding from them. The redshift observed in distant galaxies is therefore not just a measure of their speed through space, but a cosmological redshift, caused by the stretching of the light waves as the space they travel through expands. As the universe expands, the wavelength of the light travelling through it gets stretched, making it appear redder by the time it reaches our telescopes. This cosmological redshift is a direct signature of the universe's ongoing expansion. The discovery of the redshift distance relationship, formalized as Hubble's law, provided powerful support for the Big Bang model, which inherently predicts an expanding universe. It showed that the universe is not static but dynamic and evolving. The rate of this expansion, quantified by Hubble's constant, also allows scientists to estimate the age of the universe. By running the movie backward, if we know how fast things are expanding now, we can calculate how long it would have taken for everything to have been compressed into a very small, dense state. Current estimates, based on the most precise measurements of the Hubble constant and other cosmological parameters, place the age of the universe at approximately 13.8 billion years. The universe, as described by the Big Bang Theory, began in an incredibly hot and dense state. As it expanded, it cooled. A crucial prediction of this model, made decades before its discovery, was that the residual heat from this early fiery period should still be detectable today as a faint uniform glow of microwave radiation permeating all of space. This ancient light, often called the cosmic microwave background, or CMB, is the most compelling single piece of evidence supporting the Big Bang. It is essentially the universe's baby picture, showing us what the cosmos looked like when it was only a few 100,000 years old. The idea that such radiation might exist dates back to the 1940s. George Gamow, along with his students Ralph Alpher and Robert Herman, were working on the theory of Big Bang Nucleosynthesis, which describes how the first light elements were formed in the early universe. Their calculations indicated that if the universe had been hot and dense enough to fuse hydrogen into helium in its first few minutes, it must have been filled with intense radiation. As the universe expanded and cooled over billions of years, this radiation would have stretched to longer wavelengths, eventually becoming microwaves. In 1948, Alpha and Herman specifically predicted that this leftover radiation should have a temperature of about 5 Kelvin, or 5 degrees above absolute zero, a temperature that would correspond to microwave wavelengths. Their prediction, however, went largely unnoticed by the broader scientific community for many years. For the first 380,000 years after the Big Bang, the universe was a scorching hot opaque plasma. It was so hot that electrons were not bound to atomic nuclei. Instead, free electrons and atomic nuclei, mostly protons and helium nuclei, moved independently. Light or photons could not travel far in this environment without colliding with these free electrons. Imagine trying to walk through an extremely dense fog. You can only see a short distance. The early universe was like this, but for light. Photons were constantly scattering off the charged particles, making the universe effectively opaque. This period is often referred to as the photon epoch. As the universe continued to expand, it cooled. When the temperature dropped to approximately 3000 Kelvin, a critical event occurred. This was about 380,000 years after the Big Bang. At this temperature, the free electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable neutral atoms, primarily hydrogen and helium. This process is known as recombination, though it is a bit of a misnomer because electrons and nuclei were combining for the first time, not recombining. With the electrons now bound within atoms, they were no longer free to scatter photons. Suddenly the universe became transparent to light. The photons that had been trapped and constantly scattering were now free to travel across the cosmos without interruption. These are the photons we detect today as the cosmic microwave background. Over the subsequent 13.8 billion years, as the universe continued its vast expansion, These photons have travelled immense distances. The expansion of space has stretched their wavelength considerably. What was once visible or near-infrared light, with a temperature of 3000 Kelvin, has been stretched so much that its wavelength is now in the microwave portion of the electromagnetic spectrum. Its temperature has cooled to a mere 2.725 Kelvin, or about 2.725 degrees above absolute zero. This is why it is referred to as microwave background radiation. The actual discovery of the CMB was serendipitous. In 1964, two American radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were testing a new, highly sensitive horn antenna designed for satellite communication and radio astronomy. Their goal was to eliminate all sources of noise from their receiver. They meticulously checked their equipment, removed pigeon droppings from the antenna, and even considered the possibility of radar from New York City. Despite their best efforts, they kept detecting a persistent uniform low-level static, or hiss, that came from every direction in the sky, day and night, regardless of the time of year. It was a faint, steady signal that they could not explain or eliminate. Unbeknownst to Penzias and Wilson, a group of physicists at Princeton University, led by Robert Dick, along with James Peebles, P.G. Roll and David Wilkinson, were independently working on the theoretical implications of the Big Bang. They had in fact rediscovered the prediction made by Gamow, Alpha and Herman, that if the universe began with a hot Big Bang, there should be a faint uniform background of microwave radiation left over. The Princeton team was actually building an antenna to search for this very signal. Through a chance phone call, Penzias learned about Dick's work, and Dick learned about Penzias and Wilson's unexplained noise. The connection was immediately clear. Penzias and Wilson had accidentally discovered the cosmic microwave background, the ancient echo of the Big Bang. Their discovery, published in 1965, earned them the Nobel Prize in Physics in 1978. The CMB is incredibly uniform across the entire sky, with variations in temperature of only about 1 part in 100,000. This uniformity is a strong confirmation of the Big Bang's initial homogeneity. However, the tiny variations, or anisotropies, are equally important. These slight temperature differences represent minuscule density fluctuations in the early universe. These tiny ripples, amplified by gravity over billions of years, eventually grew into the vast cosmic structures we see today, such as galaxies, clusters of galaxies, and the large-scale cosmic web. Without these initial seeds of inhomogeneity, the universe would be a featureless, uniform expanse of gas. Subsequent dedicated missions have provided increasingly precise measurements of the CMB. The Cosmic Background Explorer, or COBE satellite launched by NASA in 1989, confirmed that the CMB has a perfect blackbody spectrum, exactly as predicted for thermal radiation from the early universe. This was a crucial test. COBE also detected the tiny temperature fluctuations, providing the first clear evidence of the seeds of cosmic structure. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided much higher resolution maps of these fluctuations, allowing scientists to determine key cosmological parameters with unprecedented accuracy, including the age of the universe, its composition of ordinary matter, and dark energy, and the geometry of space. Most recently, the European Space Agency's Planck satellite, launched in 2009, produced the most detailed maps of the CMB to date, further refining these measurements and providing even tighter constraints on cosmological models. The cosmic microwave background is not just a relic, it is a powerful probe of the early universe. Its existence, its black-body spectrum, its uniformity, and its tiny anisotropies all align perfectly with the predictions of the Big Bang theory. It provides a direct observational window into the universe when it was only 380,000 years old, long before the first stars and galaxies had formed. It confirms the universe was once hot, dense, and opaque, and that it has been expanding and cooling ever since. Without the discovery and detailed study of the CMB, the Big Bang theory would remain a compelling hypothesis, but with it, it stands as the overwhelmingly accepted scientific model for the evolution of our cosmos. The Big Bang theory not only explains the expansion of the universe and the existence of the cosmic microwave background, but it also provides a precise account for the observed abundance of the lightest chemical elements in the cosmos. The universe, as we observe it today, is overwhelmingly composed of hydrogen and helium, with trace amounts of lithium. The Big Bang theory accurately predicts the specific proportions of these elements, a process known as Big Bang Nucleosynthesis, or BBN. This agreement between theoretical prediction and observational fact serves as another powerful pillar supporting the Big Bang model. To understand BBN, we must go back to the very early universe, specifically the first few minutes after the Big Bang. At this time, the universe was incredibly hot and dense, far too hot for stable atomic nuclei to form. Instead, it was a rapidly expanding and cooling soup of fundamental particles: protons, neutrons, electrons, positrons, neutrinos, and photons. The temperature was so extreme, reaching billions of degrees Kelvin, that protons and neutrons could freely convert into one another. The balance between protons and neutrons was primarily determined by the universe's temperature and the slight mass difference between them. As the universe cooled, the conversion of neutrons to protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This ratio is crucial for the subsequent formation of light elements. The actual process of nucleosynthesis began when the universe was only about 1 second old and had cooled to a temperature of about 10 billion Kelvin. At this point, the strong nuclear force, which binds protons and neutrons together, became effective. However, the universe was still hot enough that any newly formed atomic nuclei would be immediately broken apart by high-energy photons. This situation is often referred to as the deuterium bottleneck. Deuterium, an isotope of hydrogen with 1 proton and 1 neutron, is the first step in the formation of heavier elements. But at temperatures above approximately 900 million Kelvin, deuterium nuclei are instantly shattered by energetic photons. Nucleosynthesis could only truly begin when the universe had cooled sufficiently to overcome this deuterium bottleneck. This occurred when the universe was roughly 3 minutes and 46 seconds old, and its temperature had dropped to around 900 million Kelvin. At this temperature, deuterium nuclei could finally survive long enough to fuse further. Once deuterium formed, it quickly combined with other protons and neutrons to build up heavier nuclei. The primary reactions during BBN involved deuterium fusing with protons to form helium-3, and then helium-3 fusing with other nuclei to form helium-4. Helium-4, with 2 protons and 2 neutrons, is an exceptionally stable nucleus, and it was the main product of Big Bang nucleosynthesis. The process was very efficient at converting almost all available neutrons into helium-4. Since there was roughly 1 neutron for every 7 protons, and each helium-4 nucleus requires 2 neutrons, this meant that for every 2 neutrons, there would be 2 protons to form 1 helium-4 nucleus. The remaining 6 protons would stay as individual hydrogen nuclei. This leads to a predicted mass ratio of about 75% hydrogen and 25% helium-4. Beyond helium-4, only trace amounts of other light elements were formed. Some helium-3 and deuterium nuclei did not fuse into helium-4 and remained in their original state. A tiny fraction of lithium-7 was also produced, primarily through the fusion of helium-4 and helium-3, or from the decay of beryllium-7. However, the conditions in the early universe were not suitable for the formation of elements heavier than lithium. The universe was expanding and cooling too rapidly. By the time heavier nuclei like carbon or oxygen could have formed through further fusion reactions, the temperature and density had dropped too low, and the nuclear reactions effectively ceased. All the heavier elements we see today, from carbon to iron and beyond, were forged much later in the cores of stars through stellar nucleosynthesis and supernova explosions. The remarkable aspect of Big Bang nucleosynthesis is the precision with which its predictions match observations. Astronomers measure the abundance of these light elements in the most pristine ancient environments they can find in the universe. This includes distant quasars, which are powered by supermassive black holes in early galaxies, and old metal-poor stars in the halos of galaxies. These environments are chosen because they have undergone minimal stellar processing. That is, their material has not been significantly altered by the nuclear fusion processes occurring in stars, which would change the elemental compositions. The observed cosmic abundance of helium-4 is consistently found to be around 24 to 25% by mass, which aligns almost perfectly with the BBN predictions. The abundance of deuterium is also a crucial test. Because deuterium is easily destroyed in stellar interiors, its primordial abundance is a sensitive probe of the conditions during BBN. Observations of deuterium in distant gas clouds, illuminated by quasars, show an abundance that is also in excellent agreement with the Big Bang model's predictions. Similarly, the observed amount of lithium-7, though subject to some complexities in measurement and theoretical understanding, generally falls within the expected range. The success of Big Bang nucleosynthesis in predicting the primordial abundances of light elements is a powerful validation of the Big Bang model. It demonstrates that the universe was indeed hot and dense enough in its early stages for these nuclear reactions to occur, and that it cooled and expanded at a rate consistent with the observed cosmic expansion. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The agreement between BBN predictions and observations allows cosmologists to determine the density of baryonic matter in the universe, which is found to be only about 4 to 5% of the total mass-energy content. This finding provides independent evidence for the existence of dark matter and dark energy, which constitute the vast majority of the universe's mass and energy, respectively. In essence, the light elements serve as fossil records from the universe's infancy. Their measured proportions across the cosmos are a direct consequence of the physical conditions that existed just minutes after the Big Bang. The fact that the Big Bang theory can explain these abundances with such accuracy provides a compelling and quantitative confirmation of its validity, reinforcing its position as the leading scientific explanation for the origin and evolution of our universe. The very first moments of the universe, immediately following the Big Bang, represent a period of extreme conditions where our current understanding of physics is pushed to its absolute limits. While direct observation of this epoch is impossible, theoretical models extrapolated from our knowledge of particle physics and general relativity allow us to paint a speculative yet scientifically informed picture of this unimaginably hot and dense beginning. This period encompasses timescales so brief they are difficult to comprehend, stretching from the Planck time to fractions of a second. The earliest conceivable moment we can discuss is the Planck epoch, which spans from time 0 up to approximately 10 to the power of minus 43 seconds after the Big Bang. At this incredibly tiny fraction of a second, the universe was compressed into a space smaller than a proton, and its temperature was an astounding 10 to the power of 32 Kelvin. In such extreme conditions, all 4 fundamental forces of nature — gravity, electromagnetism, the strong nuclear force, and the weak nuclear force — are thought to have been unified into a single superforce. Our current theories of physics, particularly general relativity, which describes gravity, and quantum mechanics, which describes the other 3 forces, break down at this scale. To fully understand the Planck epoch, a complete theory of quantum gravity is required, which scientists are still striving to develop. Theories like string theory and loop quantum gravity are attempts to bridge this gap. As the universe expanded and cooled slightly beyond the Planck time, gravity is thought to have decoupled or separated from the other 3 fundamental forces. This marked the beginning of the Grand Unification epoch, which lasted until approximately 10 to the power of minus 36 seconds. During this period, the strong, weak, and electromagnetic forces were still unified into a single, grand unified force. The universe was still extraordinarily hot and dense, but the temperature had dropped enough for distinct physical properties to begin to emerge. This epoch is also where the theory of cosmic inflation is often placed. Although inflation will be discussed in detail in another chapter, it is important to note its timing here. If it occurred, inflation was an incredibly brief period of exponential expansion, stretching the universe by a factor of at least 10 to the power of 26 in an almost unimaginably short time, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds. This rapid expansion would have smoothed out any initial irregularities and set the stage for the uniform and flat universe we observe today. Following the Grand Unification epoch, at around 10 to the power of minus 12 seconds, the universe entered the electroweak epoch. During this phase, the strong nuclear force separated from the electroweak force, leaving only the electromagnetic and weak nuclear forces still unified. The temperature had cooled to approximately 10 to the power of 15 Kelvin, which is still vastly hotter than the core of the hottest stars. At these energies, particles like quarks, leptons, such as electrons and neutrinos, and their antimatter counterparts were abundant. They existed in a hot, dense soup, constantly colliding and transforming into one another. A critical event during this early period, perhaps around 10 to the power of minus 11 seconds, was the breaking of the electroweak symmetry. This is when the electromagnetic force and the weak nuclear force separated, becoming the distinct forces we recognize today. This separation is associated with the Higgs mechanism, which gives mass to fundamental particles. Before this point, particles were massless, but after the electroweak symmetry breaking, they acquired mass through their interaction with the Higgs field. By approximately 10 to the power of minus 6 seconds, the universe had cooled to about 1 trillion Kelvin. This marked the beginning of the quark epoch, or hadron epoch. At this temperature, quarks, the fundamental building blocks of protons and neutrons, were still free and unconfined. The universe was filled with a hot, dense quark-gluon plasma, a state of matter where quarks and gluons, the particles that carry the strong force, moved freely, much like electrons in a metal. However, as the universe continued to expand and cool, the strong force became strong enough to bind quarks together. This process, called hadronization, occurred around 10 to the power of minus 6 seconds. Quarks combined to form composite particles called hadrons, primarily protons and neutrons. For every proton and neutron formed, there was also an antiparticle, antiproton and antineutron. A crucial puzzle in cosmology relates to this period, the matter-antimatter asymmetry. In the very early universe, matter and antimatter should have been produced in equal amounts. When matter and antimatter particles meet, they annihilate each other, converting their mass entirely into energy, photons. If matter and antimatter had been perfectly symmetrical, the universe would now be filled only with radiation, with no particles left to form stars, galaxies, or life. However, observations show that our universe is overwhelmingly composed of matter, with very little antimatter. Scientists believe that during these first moments, a tiny subtle asymmetry must have existed, perhaps 1 part in a billion, favouring matter over antimatter. This slight imbalance, known as baryogenesis, allowed a small residue of matter to survive the annihilation process, eventually forming everything we see today. The exact mechanism for this asymmetry is still an active area of research, potentially involving new physics beyond the standard model of particle physics. By 1 second after the Big Bang, the universe had cooled to about 10 billion Kelvin. At this point, the initial chaos had settled somewhat. The vast majority of matter-antimatter annihilation was complete, leaving behind the residual matter. Protons and neutrons were now stable, distinct particles. The universe was still too hot for atomic nuclei to form, but it was ready for the next crucial stage, Big Bang Nucleosynthesis, where these protons and neutrons would begin to fuse into the first light elements, setting the stage for the formation of stars and galaxies billions of years later. The study of these first moments is highly theoretical, relying on the standard model of particle physics, which has been rigorously tested in particle accelerators like the Large Hadron Collider. While these accelerators cannot recreate the extreme energies of the very first instant of the Big Bang, they can probe conditions that existed fractions of a second later, allowing physicists to extrapolate backward in time with increasing confidence. Understanding these initial conditions is vital because they set the fundamental parameters for the universe's subsequent evolution, determining its composition, structure, and ultimate fate. The standard Big Bang model, while remarkably successful in explaining the universe's evolution from a very hot, dense state, faced several significant puzzles in the late 20th century. These challenges concerned observations of the universe's large-scale properties that seemed too finely tuned or too uniform to be explained by the standard model alone. To address these issues, a groundbreaking theoretical concept known as cosmic inflation was proposed. Inflation posits that the universe underwent an incredibly brief but extraordinarily rapid period of exponential expansion immediately after the Big Bang. This expansion was so powerful that it stretched the fabric of space itself by an immense factor, far exceeding the subsequent more gradual expansion we observe today. The idea of inflation was first proposed by American physicist Alan Guth in 1980, building on earlier work by others. Guth was initially trying to solve the problem of magnetic monopoles, hypothetical isolated magnetic charges predicted by some grand unified theories, which should have been abundant in the early universe but have never been observed. As he worked on this problem, he realized that a period of exponential expansion could solve not only the monopole problem, but also two other major cosmological puzzles, the flatness problem and the horizon problem. Let us first delve into the concept of this rapid expansion. Inflation is theorized to have occurred extremely early in the universe's history, perhaps starting as early as 10 to the power of minus 36 seconds after the Big Bang, and ending by about 10 to the power of minus 32 seconds. This means it lasted for an unimaginably short duration, less than a trillionth of a trillionth of a trillionth of a second. During this fleeting moment, the universe is believed to have expanded by a factor of at least 10 to the power of 26, and possibly much, much more. To visualize this, imagine a region of space smaller than a proton, expanding to the size of a grapefruit in that minuscule time, or even larger. This expansion was driven by a hypothetical energy field, often called the inflaton field, which possessed unusual properties causing it to exert a repulsive gravitational force, effectively pushing space apart at an accelerating rate. When the inflaton field eventually decayed, its energy transformed into the hot, dense matter and radiation that filled the universe, initiating the standard Big Bang expansion we know. One of the key problems inflation solves is the flatness problem. Observations of the cosmic microwave background, CMB, have shown that the universe's geometry is remarkably flat. In cosmology, flat refers to a universe where the paths of parallel lines never converge or diverge, much like a flat piece of paper. A curved universe, by contrast, would be like the surface of a sphere, positive curvature, or a saddle, negative curvature. Einstein's theory of general relativity shows that the geometry of the universe depends critically on its total energy density. For the universe to be flat, its total energy density must be incredibly close to a specific critical density. Any deviation from this critical density, even a tiny one in the early universe, would have been magnified by expansion over billions of years, leading to a universe that was either very closed, curved like a sphere, and would have recollapsed quickly, or very open, curved like a saddle, and would have expanded so rapidly that structures could not form. The observed flatness is astounding, requiring the universe's initial density to be within 1 part in 10 to the power of 60 of the critical density. Inflation elegantly solves this. Just as stretching a wrinkled balloon to immense size makes its surface appear flat from any small section, inflation stretches any initial curvature of space so dramatically that the observable universe appears perfectly flat. The second major puzzle inflation addresses is the horizon problem. The cosmic microwave background radiation, which provides a snapshot of the universe when it was about 380,000 years old, appears remarkably uniform in temperature across the entire sky. This means that regions of the universe that are now separated by vast distances, so vast that light could not have travelled between them, even over the age of the universe, exhibit nearly identical temperatures. In the standard Big Bang model without inflation, these regions would have been causally disconnected. That is, they could not have exchanged information or heat. So, how did they come to have the same temperature? Inflation resolves this by proposing that all the regions we observe today originated from an incredibly tiny, causally connected patch of space before inflation began. This tiny patch was in thermal equilibrium, meaning it had a uniform temperature. Inflation then rapidly expanded this small, uniform region to astronomical scales, making it appear as if widely separated areas of the sky are in thermal contact, even though they are now beyond each other's light horizon. A third problem that inflation resolves is the magnetic monopole problem. Some grand unified theories, JWST, which attempt to unify the strong, weak and electromagnetic forces at very high energies, predict the existence of magnetic monopoles, hypothetical particles that carry an isolated north or south magnetic pole, unlike conventional magnets which always have both. These monopoles would have been produced in vast quantities in the extremely hot early universe, and if they existed, they should be easily detectable today. However, despite extensive searches, no magnetic monopoles have ever been found. Inflation offers a solution. The rapid exponential expansion would have diluted the density of these monopoles to such an extent that their current number density in the observable universe would be virtually zero, making them effectively undetectable. Beyond solving these cosmological puzzles, inflation also provides a mechanism for the origin of structure in the universe. During inflation, tiny quantum-scale fluctuations in the inflaton field were stretched to macroscopic sizes. These microscopic quantum jitters, which are an inherent part of quantum mechanics, became macroscopic density variations. After inflation ended, these slight density enhancements acted as the seeds of cosmic structure. Over billions of years, gravity amplified these initial density differences, pulling more matter into the slightly denser regions, which eventually collapsed to form the first stars, galaxies, and the large-scale cosmic web we observe today. The pattern of these density fluctuations, as imprinted on the cosmic microwave background, is remarkably consistent with the predictions of inflation. For instance, CMB maps show a nearly scale-invariant spectrum of fluctuations, meaning that variations in density occurred on roughly all scales, which is a key prediction of inflationary models. The specific pattern of polarization in the CMB, particularly the B-mode polarization, is also a target for future observations, as it could provide direct evidence of gravitational waves generated during inflation. While inflation theory has become an integral part of the Big Bang model, and its predictions are strongly supported by observations from missions like COBE, BUMAP and Planck, it is important to remember that it is still a theory. The exact nature of the inflaton field remains unknown, and there are various different models of inflation. However, the basic framework of inflation provides such elegant solutions to fundamental cosmological problems that it is widely accepted by the scientific community as the leading extension to the standard Big Bang theory. It transforms the Big Bang from a moment of unexplained initial conditions into a more comprehensive narrative that addresses why the universe possesses the large-scale properties we observe. In the earliest moments of the universe, immediately following the Big Bang, the cosmos was a place of unimaginably extreme conditions. It was incredibly hot and dense, so much so that matter as we know it could not exist. Instead, the universe was filled with a fundamental soup of pure energy and elementary particles, constantly interacting and transforming into one another. This transformation from raw energy into the building blocks of all matter is a crucial part of the universe's early story. The foundation of this process lies in Albert Einstein's famous equation, E mc2, which describes the equivalence of mass and energy. This equation tells us that mass can be converted into energy, and, critically for the early universe, energy can be converted into mass. In the superheated environment of the very early cosmos, photons or particles of light carried enormous amounts of energy. When two sufficiently energetic photons collided, their energy could spontaneously convert into a pair of particles, a particle and its corresponding antiparticle. For instance, two high-energy photons could produce an electron and its antimatter twin, a positron. This process was happening constantly throughout the universe. So, in the first fractions of a second after the Big Bang, the universe was not empty space but a churning, seething plasma. This plasma was a dense mix of fundamental particles such as quarks, which are the building blocks of protons and neutrons, leptons, which include electrons and neutrinos, and their respective antiparticles, along with a vast sea of energetic photons. These particles were moving at relativistic speeds, meaning their speeds were a significant fraction of the speed of light, and they were constantly colliding, creating new particles and antiparticles, and then annihilating back into pure energy. Let us trace this process through time as the universe expanded and cooled. In the first instance, from the Planck epoch up to perhaps 10 to the power of -6 seconds, the universe was a quark-gluon plasma. At these extreme temperatures, individual quarks were not bound together. They existed freely, along with gluons, which are the force-carrying particles for the strong nuclear force that binds quarks. The universe was a hot, dense fluid where quarks and gluons moved independently, constantly being created and annihilated. As the universe continued to expand, its temperature rapidly dropped. Around 1 microsecond, 1/1,000,000th of a second after the Big Bang, the temperature had cooled to approximately 2 trillion Kelvin. At this critical temperature, the strong nuclear force became strong enough to confine quarks. This process is called hadronization. Quarks could no longer exist freely and instead bound together to form composite particles called hadrons. The most familiar hadrons are protons, which are made of 2 up quarks and 1 down quark, and neutrons made of 1 up quark and 2 down quarks. This was a pivotal moment, as the basic constituents of atomic nuclei were now formed. During this period of particle creation and annihilation, a fundamental imbalance played a critical role in the universe's ultimate fate: the matter-antimatter asymmetry. According to our current understanding, energy should have produced equal amounts of particles and antiparticles. For instance, every time an electron was created, a positron, anti-electron, should also have been created. When a particle encounters its antiparticle, they annihilate each other, converting their entire mass back into energy. If there had been a perfect balance between matter and antimatter, all of the particles and antiparticles produced in the early universe would have annihilated each other, leaving behind a universe composed only of photons and neutrinos, with no ordinary matter to form stars, planets, or life. However, our universe is clearly dominated by matter. There are stars, galaxies, and people, and very little antimatter. This implies that there must have been a tiny, yet incredibly significant asymmetry in the early universe, favouring matter over antimatter. For every billion antiparticles, there was roughly 1,000,000,001 particles. This minuscule excess of matter, perhaps generated through processes like baryogenesis, which is still an active area of theoretical and experimental research, was what survived the annihilation epoch. As the universe continued to cool, the remaining particles and antiparticles annihilated each other, with a tiny surplus of matter, particles being the only survivors. This surviving matter is what makes up everything we see today. After the formation of protons and neutrons, and the general annihilation of antimatter, the universe continued to cool. Electrons, being much less massive than protons and neutrons, could still be readily created and annihilated by photons for a longer period. It wasn't until the universe was about 1 second old that the temperature dropped below the threshold for creating electron-positron pairs. At this point, most electrons and positrons annihilated, leaving behind a residual population of electrons, balancing the positive charge of the protons. Neutrinos, which are very light and interact only via the weak nuclear force, also decoupled from the rest of the matter and radiation around this time, forming a cosmic neutrino background that is difficult to detect but is another relic of this hot, dense epoch. So, by approximately 1 second after the Big Bang, the particle soup had largely resolved into its more familiar constituents. The universe was still a very hot, dense plasma, but it was now primarily composed of protons, neutrons, electrons, and photons, along with a vast number of neutrinos. These were the raw ingredients for the next stages of cosmic evolution, including Big Bang nucleosynthesis, where protons and neutrons would fuse to form the first light atomic nuclei, paving the way for the later formation of atoms, stars, and galaxies. The transformation from pure energy to this initial particle content was a fundamental step in shaping the universe we inhabit. The universe around us is governed by 4 fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces dictate how particles interact, how atoms form, how stars shine, and how galaxies cluster together. At first glance, these forces appear distinct, operating in different ways and at vastly different strengths and ranges. However, a cornerstone of modern physics, particularly the study of the very early universe, is the idea of unification. that these seemingly distinct forces were once, under conditions of extreme energy and temperature, unified as a single fundamental force. As the universe expanded and cooled from its initial hot state, this unified force broke into the separate forces we observe today. Let us first briefly describe each of these four forces as they appear in our present-day, relatively cool universe. Gravity. This is the force of attraction between any two objects with mass or energy. It is the weakest of the four forces but has an infinite range. It governs the motion of planets around stars, the formation of stars and galaxies, and the large-scale structure of the entire universe. Electromagnetism. This force governs the interactions between electrically charged particles. It is responsible for all chemical reactions, the behavior of light, electricity, and magnetism. It holds electrons in orbit around atomic nuclei, forming atoms and molecules. Like gravity, it has an infinite range, but its strength is vastly greater than gravity. Strong nuclear force. This is the strongest of the four forces, but it acts only over incredibly short distances, typically within the nucleus of an atom. It is responsible for binding quarks together to form protons and neutrons, and for holding these protons and neutrons together within atomic nuclei. Without the strong force, atomic nuclei would fly apart due to the electromagnetic repulsion between positively charged protons. Weak nuclear force. This force is responsible for certain types of radioactive decay, such as beta decay, where a neutron transforms into a proton, or vice versa. It plays a crucial role in nuclear fusion processes in stars, including our Sun, but it has a very short range, even shorter than the strong force, and is significantly weaker than the strong and electromagnetic forces. The concept of force unification is not new to physics. A major triumph in the 19th century was James Clerk Maxwell's unification of electricity and magnetism into a single theory of electromagnetism. Before Maxwell, electricity and magnetism were considered separate phenomena, but he showed they were two different manifestations of the same underlying force, with light itself being an electromagnetic wave. Building on Maxwell's success, physicists in the 20th century began to wonder if the other forces could also be unified. The first major step beyond electromagnetism came in the 1960s and 70s with the electroweak unification. Sheldon Glashow, Abdus Salam, and Steven Weinberg independently developed a theory that showed that at very high energies, the electromagnetic force and the weak nuclear force are not separate, but are two aspects of a single electroweak force. This unification was a monumental achievement, as it demonstrated that forces could indeed merge under specific conditions. This theory predicted the existence of new force-carrying particles, the W and Z bosons, which were later experimentally discovered at the European Organisation for Nuclear Research, or CERN, in the 1980s, providing strong confirmation of the electroweak theory. The energies required for electroweak unification correspond to temperatures that existed in the universe when it was only about 10 to the power of minus 12 seconds old, or 1/1,000,000,000 of a second after the Big Bang. At this incredibly hot stage, particles interacted via the unified electroweak force. As the universe cooled below this critical temperature, the electroweak force broke into the distinct electromagnetic and weak forces we observe today. The next ambitious step in unification is the development of grand unification theories, or GUTS. These speculative theories aim to unify the electroweak force with the strong nuclear force. If a GUT is correct, then at even higher energies, corresponding to temperatures found when the universe was perhaps 10 to the power of minus 36 seconds old, these three forces, electromagnetic, weak, and strong, would have been unified into a single, grand unified force. At these energies, the universe would have been too hot for individual protons and neutrons to form, existing instead as a quark-gluon plasma. As the universe cooled through this epoch, the grand unified force would have broken down, first separating the strong force from the electroweak force, and then the electroweak force further splitting into the electromagnetic and weak forces. GUTS makes several predictions, such as proton decay and the existence of magnetic monopoles, none of which have been definitively observed yet, which means that either these theories are incorrect, or the phenomena occur at rates too rare for us to detect with current technology. The ultimate goal for physicists is to achieve a theory of everything, or TOEU, which would unify all four fundamental forces, including gravity, into a single, comprehensive framework. Such a unification is thought to have occurred at the very highest energies, corresponding to the Planck epoch, which existed up to approximately 10 to the power of minus 43 seconds after the Big Bang. At these unimaginably high temperatures, 10 to the power of 32 Kelvin, gravity would have been as strong as the other forces and unified with them. Developing a theory that successfully integrates gravity with quantum mechanics, which describes the other three forces, is one of the most significant unsolved problems in physics. Theories like string theory and loop quantum gravity are leading candidates for such a quantum theory of gravity and a potential theory of everything. The early universe serves as the only natural laboratory where such extreme energies and temperatures existed, allowing for these force unifications to occur. By studying the remnants of the Big Bang, such as the cosmic microwave background, and by probing high-energy interactions in particle accelerators, scientists hope to find clues that will lead to a complete understanding of how these fundamental forces were unified in the universe's first moments, and how they subsequently separated to shape the physical laws that govern our cosmos today. The idea of forces uniting in the hot, dense early universe is a powerful concept that underscores the deep interconnectedness of physical reality. As the universe continued its rapid expansion after the Big Bang, its temperature steadily decreased. This cooling was essential for the formation of the first stable atomic nuclei and, later, the first complete neutral atoms. This process occurred in two distinct phases. First, the creation of light atomic nuclei during Big Bang nucleosynthesis, and then, much later, the formation of neutral atoms during recombination. Big Bang nucleosynthesis, or BBN, began when the universe was only about 3 minutes and 46 seconds old. Before this time, the universe was too hot, with temperatures exceeding billions of Kelvin, for atomic nuclei to hold together. Instead, it was a dense plasma of fundamental particles, primarily protons, neutrons, electrons, positrons, and a vast sea of energetic photons. Protons and neutrons could interconvert, but as the universe cooled, the conversion of neutrons into protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This precise ratio was critical for what was to follow. The initial hurdle for nucleosynthesis was the deuterium bottleneck. Deuterium, an isotope of hydrogen containing 1 proton and 1 neutron, is the simplest compound nucleus and the essential stepping stone for building heavier elements. However, at temperatures above approximately 900 million Kelvin, the high-energy photons in the universe would immediately smash apart any newly formed deuterium nuclei. This meant that even though protons and neutrons were present, they could not combine to form stable nuclei until the universe cooled sufficiently. Once the temperature dropped below this critical threshold, around 3 minutes and 46 seconds after the Big Bang, deuterium nuclei could finally survive. This opened the floodgates for a rapid series of nuclear fusion reactions. Deuterium quickly combined with other protons and neutrons to form heavier isotopes. For example, a deuterium nucleus could fuse with another proton to form helium-3, which has 2 protons and 1 neutron. Helium-3 could then fuse with a neutron to form helium-4, which has 2 protons and 2 neutrons, or with another deuterium nucleus to form helium-4. Helium-4 is an exceptionally stable atomic nucleus, and the nuclear reactions during BBN were highly efficient at producing it. Because each helium-4 nucleus requires 2 protons and 2 neutrons, and neutrons were relatively scarce compared to protons, the 1:7 ratio, virtually all available neutrons were incorporated into helium-4 nuclei. The remaining protons, which constituted the vast majority of the baryonic matter, remained as individual hydrogen nuclei. This process continued for about 17 minutes, effectively ending around 20 minutes after the Big Bang, when the universe had expanded and cooled so much that the density and temperature were too low for further nuclear fusion to occur. The result of Big Bang nucleosynthesis was a universe composed of approximately 75% hydrogen and 25% helium-4 by mass, with only trace amounts of deuterium, helium-3 and lithium-7. No heavier elements like carbon, oxygen or iron were formed during this period. The universe simply did not remain hot and dense enough for a sufficient duration to build up these more complex nuclei. The conditions for forming elements beyond lithium require the extreme pressures and temperatures found only in the cores of stars, which would not form for hundreds of millions of years. The predicted abundances of these light elements are one of the strongest pieces of evidence supporting the Big Bang theory. Astronomers observe the cosmic abundances of hydrogen, helium, and lithium in the most pristine ancient regions of the universe, such as distant gas clouds and the oldest stars, which have not been significantly altered by later stellar processes. The measured proportions match the BBN predictions with remarkable accuracy. This agreement confirms that the universe was indeed hot and dense enough in its early stages for these specific nuclear reactions to occur, and that it expanded and cooled at a rate consistent with our current cosmological models. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The success of BBN in matching observations provides a strong constraint on the total amount of baryonic matter, indicating it makes up only about 4 to 5% of the universe's total mass energy content. While the nuclei of the first elements were formed within the first 20 minutes, the universe was still too hot for these nuclei to capture electrons and form complete neutral atoms. Free electrons still roamed independently, constantly scattering photons. This state persisted for a much longer period. The universe remained an opaque ionized plasma, much like the interior of a star, where light could not travel freely. The second crucial phase, known as recombination, occurred much later, approximately 380,000 years after the Big Bang. By this time, the universe had continued to expand significantly, and its temperature had dropped to about 3000 Kelvin, roughly the temperature of the surface of a cool star. At this critical temperature, the kinetic energy of the free electrons was low enough that they could be captured by the positively charged atomic nuclei, protons and helium nuclei, to form stable neutral atoms. The term recombination is a bit misleading, as it was the first time electrons and nuclei combined, not a recombination. As electrons combined with nuclei, the universe underwent a dramatic transformation. With electrons now bound within atoms, they were no longer free to scatter photons. The universe suddenly became transparent to light. The photons that had been trapped and constantly scattering within the opaque plasma were now free to travel across the cosmos without interruption. These photons, released at the moment of recombination, are what we detect today as the cosmic microwave background radiation. Its uniform distribution and specific temperature of 2.725 Kelvin are direct evidence of this event. The formation of these first neutral atoms, primarily hydrogen and helium, marked the end of the plasma era and the beginning of the dark ages of the universe. For the first time, matter was organized into stable neutral structures. This transition was fundamental because it allowed light to travel freely, and it also set the stage for the next major phase of cosmic evolution: the gravitational collapse of this neutral gas to form the first stars and galaxies. Without the birth of these first atoms, the universe would have remained an undifferentiated plasma, incapable of forming the complex structures we observe today. Following the formation of the first neutral atoms during the epoch of recombination, the universe entered a period known as the Cosmic Dark Ages. This era, spanning from approximately 380,000 years after the Big Bang to roughly 300 million to 500 million years later, is characterized by the absence of light sources in the visible spectrum. While the universe was no longer an opaque plasma, it was a largely featureless expanse of neutral gas, primarily hydrogen and helium, with no stars or galaxies yet to illuminate it. The onset of the Dark Ages was marked by the decoupling of matter and radiation. Before recombination, photons were constantly interacting with free electrons, making the universe opaque. Once electrons combined with atomic nuclei to form neutral atoms, these photons were free to travel unimpeded. This moment, 380,000 years after the Big Bang, is when the cosmic microwave background CMB radiation was released. As the universe continued to expand, these CMB photons stretched to longer wavelengths and cooled. eventually becoming the faint microwave glow we detect today. During the Dark Ages, the CMB was the only significant source of radiation, and its temperature continued to drop, meaning it provided less and less light in the visible range. During this long stretch of cosmic history, the universe was indeed dark. There were no stars shining, no galaxies blazing with starlight. The gas was almost entirely neutral, meaning its atoms had their full complement of electrons. This neutral gas, predominantly hydrogen and helium, was distributed relatively uniformly throughout space. The small density fluctuations that were imprinted on the cosmic microwave background, originating from quantum fluctuations in the very early universe, were still present, but they were very subtle. The dominant force at play during the Dark Ages was gravity. While the gas was largely uniform, the tiny overdensities, or regions where the gas was slightly denser than average, began to slowly attract more matter due to their slightly stronger gravitational pull. This process of gravitational collapse was incredibly slow during the Dark Ages because the universe was still relatively smooth, and the gravitational forces were weak over the vast distances. An essential component influencing this gravitational collapse was dark matter. Dark matter is a mysterious substance that does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Cosmological models suggest that dark matter makes up about 27% of the universe's total mass energy content, far more than ordinary baryonic matter. During the Dark Ages, dark matter began to clump together under its own gravity, forming invisible structures known as dark matter halos. These halos acted as gravitational scaffolding, providing the initial gravitational wells into which the ordinary neutral gas could slowly fall. Without dark matter, the gravitational pull of ordinary matter alone would have been insufficient to form structures within the observed timescale of the universe. The temperature of the neutral gas during the Dark Ages continued to fall from the initial 3000 Kelvin at recombination. It eventually reached a minimum of around 10 Kelvin, or 10 degrees above absolute zero, after about 10 million to 100 million years. After this point, as the first structures began to form and contract, the gas within these collapsing regions would start to heat up again due to compression. The chemical composition of the universe during the Dark Ages was extremely simple. It consisted almost exclusively of hydrogen and helium, with only trace amounts of lithium. There were no heavier elements like carbon, oxygen, or iron, as these elements are forged in the interiors of stars and supernova explosions, which had not yet occurred. This lack of heavier elements meant that the cooling mechanisms for the gas were very limited. In the present-day universe, heavier elements act as efficient coolants, allowing gas clouds to radiate away energy and collapse more easily. In the Dark Ages, the primary coolant was molecular hydrogen, H2, which is less efficient than heavier elements. This limited cooling had implications for the properties of the first stars that would eventually form. Observing the Dark Ages directly is extremely challenging. Since there were no stars or galaxies emitting visible or ultraviolet light, conventional telescopes cannot see this period. However, scientists are exploring various indirect ways to probe this era. One promising avenue is through the detection of the 210 cm line of neutral hydrogen, also known as the hydrogen line, or spin-flip transition. This specific radio wavelength is emitted when the spin of the electron in a neutral hydrogen atom flips. By observing the redshifted 210 cm line from different points in the universe, astronomers hope to map the distribution of neutral hydrogen during the Dark Ages and study how the first structures began to emerge. Projects like the Low Frequency Array, or LOFAR, and the Square Kilometre Array, or SKA, are designed to detect these faint signals. The Dark Ages were a crucial transitional period. It was a time when the universe was literally dark, but beneath the quiet, expanding expanse, the seeds of future cosmic structures were slowly germinating. Gravity, guided by the distribution of dark matter, was patiently gathering the primordial gas into progressively denser clumps. This gradual accumulation of matter laid the groundwork for the universe's next major cosmic revolution, the ignition of the very first stars, which would end the Dark Ages and usher in the era of Ryanization and the formation of galaxies. Without this long, quiet period of gravitational growth, the universe would not have been able to build the complex cosmic tapestry we observe today. The Cosmic Dark Ages, a period of profound darkness lasting for hundreds of millions of years, eventually came to an end with the ignition of the very first stars. These pioneering celestial bodies, often referred to as Population 3 stars, were fundamentally different from the stars we see in the night sky today. Their formation marked a pivotal moment in cosmic history as they began the process of illuminating the universe, forging the first heavy elements, and setting the stage for the formation of galaxies. The birth of these first stars was a direct consequence of the gravitational collapse that slowly unfolded during the Dark Ages. As discussed, the universe during this era was filled with a relatively uniform distribution of neutral hydrogen and helium gas, along with the invisible scaffolding of dark matter halos. These dark matter halos, formed by the gravitational clumping of dark matter, created gravitational potential wells into which the ordinary baryonic gas could slowly fall. Within these dark matter halos, regions of slightly higher gas density began to attract more and more surrounding gas. As the gas accumulated, its density increased, and the gravitational pull became stronger, leading to a runaway collapse. However, the process was not as straightforward as in the modern universe. The primordial gas consisted almost entirely of hydrogen and helium, with only trace amounts of lithium. Crucially, there were no heavier elements, which astronomers refer to as metals. In the modern universe, metals play a vital role in cooling gas clouds, allowing them to fragment into smaller, denser clumps that can form stars of various sizes. Without these efficient coolants, the primordial gas had fewer ways to radiate away the heat generated by gravitational compression. The primary cooling mechanism available to the primordial gas was the formation and excitation of molecular hydrogen, or H2. Hydrogen atoms could combine to form H2 molecules, which could then radiate energy away, allowing the gas cloud to cool and contract further. However, H2 is not a very efficient coolant compared to metals. This limited cooling meant that the gas clouds had to be much more massive before they could collapse sufficiently to form stars. As a result, the first stars are predicted to have been extraordinarily massive. Theoretical models suggest that Population 3 stars typically had masses ranging from tens to hundreds, or even thousands of times the mass of our Sun. Some models even propose that the very first stars could have been as massive as 100,000 solar masses. This immense mass had profound implications for their characteristics and lifespans. Because of their enormous mass, Population 3 stars were incredibly hot and luminous. Their cores reached extreme temperatures and pressures, causing nuclear fusion reactions to proceed at a furious rate. They burned through their hydrogen fuel much more quickly than smaller stars. Consequently, their lifespans were incredibly short, lasting only a few million years, compared to the billions of years our Sun is expected to live. The death of these massive first stars was as dramatic as their birth. They ended their lives in spectacular supernova explosions. These were not just any supernova. They were likely a specific type known as pair instability supernova for the most massive ones. In such an explosion, the star completely disintegrates, leaving no remnant behind. These first supernovae were crucial because they were the universe's first cosmic factories for heavier elements. Inside the cores of these massive stars, nuclear fusion had forged elements up to iron. The supernova explosions then dispersed these newly created heavier elements, such as carbon, oxygen, nitrogen, and silicon, into the surrounding intergalactic medium. This chemical enrichment was essential, as these metals would later become the building blocks for subsequent generations of stars, planets, and eventually life. The supernovae of the first stars also had another profound impact. They contributed to the reionization of the universe. After recombination, the universe was filled with neutral hydrogen and helium. The ultraviolet light emitted by the first stars was energetic enough to strip electrons from these neutral atoms, reionizing the intergalactic medium. This process was gradual, starting in localized bubbles around the first stars and galaxies, and eventually spreading throughout the cosmos. By about 1 billion years after the Big Bang, the universe was largely reionized, making it transparent to ultraviolet light once again. This reionization epoch is another critical phase in cosmic evolution, and its timing and progression are actively studied using observations of distant quasars and the cosmic microwave background. Directly observing population 3 stars is extremely challenging because of their short lifespans and the vast distances involved. They existed billions of years ago, and their light is incredibly faint and redshifted. Current telescopes, even the most powerful ones like the James Webb Space Telescope, are pushing the limits to detect the faint light from the very first galaxies which would contain these stars. While individual population 3 stars have not yet been definitively observed, their existence is inferred from the properties of the cosmic microwave background, the observed abundances of light elements, and the presence of heavier elements in later generations of stars. The chemical composition of the oldest stars we can observe today, known as population 2 stars, shows very low abundances of metals, consistent with them having formed from gas that was only slightly enriched by the supernovae of population 3 stars. The first stars were cosmic pioneers. They ended the long darkness, initiated the chemical enrichment of the universe, and began the process of reionization. Their short, violent lives set in motion a chain of events that led to the formation of the galaxies, stars, and planets we see today, ultimately making the universe a more complex and hospitable place. The formation of the first galaxies represents a crucial stage in the evolution of the universe, transforming a relatively smooth, dark expanse of gas into the complex luminous structures we observe today. This process, which began hundreds of millions of years after the Big Bang, was driven primarily by gravity, with a pivotal role played by the mysterious substance known as dark matter. The standard cosmological model, often referred to as lambda CDM, lambda for dark energy and cold dark matter, provides the framework for understanding how these structures emerged through a hierarchical process, where smaller clumps of matter merged and grew into larger ones. The seeds of galaxy formation were sown much earlier, during the epoch of cosmic inflation, when tiny quantum fluctuations in the very early universe were stretched to macroscopic scales. These fluctuations manifested as minute variations in the density of matter and energy, imprinted on the cosmic microwave background. During the subsequent Dark Ages, as the universe expanded and cooled, these slight overdensities began to exert a stronger gravitational pull on surrounding matter. Crucially, the vast majority of the matter in the universe is not the ordinary baryonic matter, protons, neutrons, electrons, that makes up stars and galaxies, but rather dark matter. Dark matter, which accounts for about 27% of the universe's mass-energy content, does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Because dark matter does not experience the electromagnetic forces that would cause ordinary gas to exert pressure and resist collapse, it was able to clump together much earlier and more efficiently than ordinary matter. During the Dark Ages, dark matter began to coalesce under its own gravity, forming invisible structures known as dark matter halos. These halos were the first large-scale structures to emerge in the universe. They varied in size, from small clumps with masses equivalent to 1 million suns to much larger ones. These dark matter halos acted as gravitational scaffolding, creating the potential wells into which the ordinary baryonic gas, primarily hydrogen and helium, could slowly fall. The process of gas accumulating within these dark matter halos was gradual. As the neutral gas fell into the gravitational embrace of a dark matter halo, it became compressed and heated. For stars to form, this gas needed to cool down so that it could become dense enough to collapse further. In the early universe, without the presence of heavier elements, which act as efficient coolants in modern gas clouds, the primary cooling mechanism for the primordial gas was the formation and excitation of molecular hydrogen, H2. This limited cooling meant that the gas clouds had to be quite massive before they could cool sufficiently to initiate star formation. The very first stars, known as population 3 stars, formed within these early, relatively small dark matter halos. These stars were typically much more massive than our Sun, burning through their fuel rapidly and ending their lives in spectacular supernova explosions within just a few million years. These supernovae were vital as they dispersed the first heavy elements, forged in the star's cores, into the surrounding gas. This chemical enrichment was a critical step, as these newly synthesized metals would later enable more efficient cooling in subsequent generations of gas clouds, allowing for the formation of smaller, more diverse stars. The earliest galaxies were not the grand spiral or elliptical structures we see today. Instead, they were likely much smaller, irregular clumps of stars and gas, forming within the most massive and densest of the early dark matter halos. These nascent galaxies, sometimes referred to as proto-galaxies or mini-halos, were the building blocks of larger galaxies. The process of galaxy formation is thought to be hierarchical, meaning that small structures formed first and then merged over cosmic time to create progressively larger ones. As the universe continued to evolve, these early mini-halos and proto-galaxies, still embedded within their dark matter halos, began to attract each other through gravity. They collided and merged, a process that was particularly frequent in the early universe when structures were closer together. These mergers were violent events, disrupting existing stellar orbits, triggering bursts of star formation, and leading to the growth of larger, more complex galaxies. Each merger brought in more gas, more stars, and more dark matter, contributing to the overall growth of the galactic structures. The role of dark matter in this hierarchical formation is paramount. Without its gravitational influence, ordinary matter alone would not have been able to clump together quickly enough to form the observed large-scale structures in the universe. The pressure exerted by the hot gas in the early universe would have prevented it from collapsing into structures on the scales of galaxies. Dark matter, by providing the initial gravitational scaffolding without being affected by pressure or electromagnetic forces, allowed the first structures to form, which then served as the gravitational anchors for ordinary matter. Observations from powerful telescopes like the Hubble Space Telescope and, more recently, the James Webb Space Telescope, provide direct evidence for this hierarchical formation. These telescopes can peer deep into the universe, allowing astronomers to observe galaxies as they appeared billions of years ago, when the universe was much younger. They reveal numerous small, irregular, and often interacting galaxies in the early universe, which are consistent with the idea that larger galaxies formed through the mergers of smaller ones. The most distant galaxies observed are often small and appear to be actively forming stars, indicating they are in their early stages of development. Over billions of years, this process of gravitational collapse and hierarchical merging continued. Smaller galaxies merged to form larger ones, and these larger galaxies then grouped together to form galaxy clusters and superclusters, creating the vast cosmic web of filaments and voids that spans the universe today. The dark matter halos continued to grow, encompassing these larger structures. The properties of galaxies, such as their shape, size, and star formation rates, are influenced by their environment and their merger history. For example, elliptical galaxies are thought to be the result of multiple major mergers, while spiral galaxies may have experienced fewer significant merger events. In essence, galaxy beginnings were not a singular event but a continuous process driven by gravity and dark matter. From the initial quantum fluctuations, dark matter provided the gravitational framework for the first halos. Within these halos, primordial gas cooled and collapsed to form the first massive stars. The supernovae of these stars enriched the universe with heavier elements. Subsequently, these early small stellar systems and their dark matter halos merged repeatedly, building up the larger, more diverse galaxies that populate the universe today, a process that continues even in the present epoch. To understand our place in the vastness of the universe, it is helpful to consider our cosmic address, a hierarchical description that places our home planet within progressively larger structures, from our immediate neighbourhood to the observable limits of the cosmos. This journey through scale provides a profound sense of perspective on the immense distances and structures that comprise the universe. Our journey begins on Earth, a rocky planet orbiting a star. Earth is the third planet from the Sun, a yellow dwarf star. The Sun, along with its 8 planets, numerous dwarf planets, asteroids, comets, and other celestial bodies, forms our solar system. The solar system is a relatively small, gravitationally bound system located in one of the spiral arms of a much larger structure. The solar system resides within the Milky Way galaxy. The Milky Way is a barred spiral galaxy, a vast collection of hundreds of billions of stars along with gas, dust and dark matter, all bound together by gravity. Our Sun is located in the Orion Arm, one of the smaller spiral arms of the Milky Way, approximately 27,000 light-years from the galactic centre. To give a sense of scale, the Milky Way galaxy is estimated to be about 100,000 light-years in diameter and approximately 1,000 light-years thick. The Sun orbits the galactic centre once every 230 million years, a period known as a cosmic year. From our vantage point within the disk, we see the collective light of billions of stars as a hazy band across the night sky, which is why it is called the Milky Way. The Milky Way galaxy is not alone in the universe. It is part of a small cluster of galaxies known as the Local Group. The Local Group is a gravitationally bound collection of over 50 galaxies, though most of these are dwarf galaxies. The two largest and most dominant members of the Local Group are the Milky Way and the Andromeda Galaxy. The Andromeda Galaxy, a large spiral galaxy, is about 2.5 million light-years away and is on a collision course with the Milky Way, with a predicted merger occurring in about 4.5 billion years. Other notable members of the Local Group include the Triangulum Galaxy, the Large Magellanic Cloud, and the Small Magellanic Cloud, the latter two being satellite galaxies of the Milky Way. The Local Group itself spans approximately 10 million light-years across. The Local Group, in turn, is a small component of an even larger structure, a supercluster of galaxies. For many years, the Local Group was considered part of the Virgo supercluster, a massive collection of galaxy clusters centered on the Virgo cluster, which is about 54 million light-years away. The Virgo supercluster contains thousands of galaxies and spans roughly 110 million light-years. Our Local Group is located near the edge of this supercluster, and we are gravitationally attracted towards its centre. However, more recent and detailed mapping of the universe's large-scale structure has revealed that the Virgo supercluster is itself just a lobe of an even grander, more extensive supercluster, which has been named the Laniakea supercluster. The name Laniakea means immense heaven in Hawaiian. Discovered in 2014, the Laniakea supercluster is defined by the gravitational flow of galaxies towards a common centre of mass, a region known as the Great Attractor. The Laniakea supercluster is truly enormous, containing approximately 100,000 galaxies and spanning about 500 million light-years across. Our Local Group is located near the edge of Laniakea, and we are, along with thousands of other galaxies, slowly being pulled towards the Great Attractor. Beyond the Laniakea supercluster, the universe continues to unfold into an intricate web-like pattern of galaxy clusters, superclusters, and vast, nearly empty regions called voids. This large-scale structure is often referred to as the cosmic web. Galaxies and clusters are concentrated along filaments, which are like cosmic threads, while between these filaments lie immense voids where galaxies are scarce. This cosmic web is the largest known structure in the universe, stretching for billions of light-years. The largest structure we can observe is the observable universe itself. This is not the entire universe, which may be infinite in extent, but rather the portion of the universe from which light has had enough time to reach us since the Big Bang. Because the universe is approximately 13.8 billion years old, and light travels at a finite speed, the maximum distance from which we can receive light is about 13.8 billion light-years in any direction. However, due to the ongoing expansion of the universe, the actual distance to the most distant objects whose light we are now receiving is much greater, estimated to be around 46.5 billion light-years in every direction from us. This means the diameter of the observable universe is approximately 93 billion light-years. Within this immense observable universe, there are estimated to be hundreds of billions, possibly even trillions of galaxies, each containing hundreds of billions of stars. Each of these stars may host its own system of planets. The sheer scale is almost incomprehensible. Our Earth is a tiny speck of dust orbiting an average star, which is one of hundreds of billions of stars in a galaxy that is one of dozens in a small group, which is part of a larger supercluster, itself embedded within the vast cosmic web that fills the observable universe. Understanding our cosmic address provides a crucial perspective. It highlights that we are not at the centre of the universe, nor are we particularly special in a cosmic sense. Our existence is part of a grand narrative of cosmic evolution, from the Big Bang to the formation of stars, galaxies, and ultimately complex life. This hierarchical view of the cosmos underscores the vastness and complexity of the universe, reminding us of the ongoing scientific quest to explore and understand our place within it. The Big Bang Theory provides a highly successful framework for understanding the evolution of our universe from an incredibly hot, dense state to its current vast and complex form. It explains the expansion of space, the cosmic microwave background radiation, and the abundance of light elements with remarkable accuracy. However, despite its triumphs, the Big Bang Theory, in its current form, encounters a fundamental limitation when attempting to describe the very first instant of the universe, the concept of a singularity. This edge of knowing represents a boundary beyond which our current laws of physics, particularly general relativity, break down, leaving crucial questions about the universe's ultimate origin unanswered. A singularity, in the context of general relativity, is a point where the density of matter and the curvature of space-time become infinite. According to the standard Big Bang model, if we extrapolate the universe's expansion backward in time, all matter and energy would converge to an infinitely dense point at time zero. This is often referred to as the initial singularity. While mathematically convenient, an infinite density and infinite curvature are problematic for physics. Infinities generally signal that a theory is incomplete or being applied beyond its valid domain. When general relativity predicts a singularity, it essentially tells us that it can no longer describe what is happening at that point. It is a mathematical breakdown, not necessarily a physical description of reality. One of the key figures in understanding this limitation was Stephen Hawking, who, along with Roger Penrose, developed the singularity theorems in the 1960s and 70s. These theorems demonstrated that, under very general conditions, assuming general relativity is correct and that the universe contains a reasonable amount of matter and energy, an initial singularity is an unavoidable consequence of the universe's observed expansion. This means that if we trace the universe back far enough, we inevitably arrive at a point where the density and curvature of space-time become infinite, and the concept of space and time, as we understand them, ceases to exist. The problem with the singularity is that it prevents us from asking what happened before, or what caused it. If all of space and time originated from this singular point, then the very concept of before becomes meaningless within the framework of general relativity. The theory simply cannot provide answers to these questions because its equations no longer apply. It is like trying to use a map that only shows roads to describe the ocean. It is the wrong tool for the job. The breakdown of general relativity at the singularity points to the need for a more comprehensive theory, one that can seamlessly integrate gravity with quantum mechanics. General relativity is a classical theory, meaning it describes gravity on large scales, but it does not account for the quantum nature of reality at extremely small scales. Quantum mechanics, on the other hand, describes the behavior of particles and forces at the atomic and subatomic level, where uncertainties and probabilities dominate. At the Planck scale, which is an unimaginably tiny length, about 10 to the power of minus 35 meters, and time, about 10 to the power of minus 43 seconds, quantum effects of gravity are expected to become dominant. The initial singularity of the Big Bang occurs precisely at this Planck scale, where both general relativity and quantum mechanics are simultaneously relevant, and neither theory alone is sufficient. This is where the quest for a theory of quantum gravity becomes paramount. Such a theory would aim to unify general relativity with quantum mechanics, providing a consistent description of gravity at extremely small scales and high energies. Leading candidates for a theory of quantum gravity include string theory and loop quantum gravity. These theories offer potential ways to resolve the singularity problem. String theory, for instance, proposes that fundamental particles are not point-like, but are instead tiny, vibrating one-dimensional strings. At the Planck scale, these strings would smear out the singularity, preventing infinite densities from arising. In some string theory models, the Big Bang might not be the absolute beginning, but rather a transition from a previous state, perhaps a collision of higher dimensional branes. This could potentially eliminate the singularity by replacing it with a finite, albeit extreme event. Loop quantum gravity, another approach, suggests that space-time itself is not continuous, but is granular, made up of discrete loops, or atoms of space-time at the Planck scale. In this framework, the singularity might be replaced by a big bounce, where the universe contracts to a minimum but finite size before rebounding into expansion, avoiding infinite density. This would imply that our universe is part of a cyclic process, with no true beginning or end. The edge of knowing also extends to the very early universe before the electroweak epoch, particularly the period of cosmic inflation. While inflation theory successfully addresses several puzzles of the standard Big Bang model, such as the flatness and horizon problems, it does not explain what caused inflation itself or what existed before it. Inflationary models typically require an inflaton field to drive the exponential expansion, but the precise nature of this field and its initial conditions are still unknown. Some inflationary scenarios, particularly chaotic inflation, suggest that inflation might be eternal, leading to a multiverse where new universes are constantly being spawned. If this is the case, then our Big Bang is just one event in a much larger, eternally inflating cosmos, pushing the ultimate origin question to a higher level of complexity. Furthermore, the edge of knowing encompasses the fundamental constants of nature. The values of these constants, such as the strength of gravity, the mass of an electron, or the speed of light, appear to be finely tuned for the existence of stars, galaxies, and life. If these constants were even slightly different, the universe might be radically different or incapable of supporting complex structures. The Big Bang theory does not explain why these constants have their particular values. Some physicists appeal to the Anthropic Principle or the multiverse concept to address this, suggesting that we simply find ourselves in a universe where these values are suitable for our existence, and other universes might have different values. However, these are philosophical arguments rather than direct scientific explanations derived from a fundamental theory. In essence, the initial singularity of the Big Bang represents a boundary for our current physical theories. It is the point where general relativity, our best description of gravity on large scales, breaks down. Overcoming this limitation requires a quantum theory of gravity, which is one of the most challenging and active areas of research in theoretical physics. Until such a theory is developed and experimentally verified, the very first instant of the universe will remain shrouded in mystery, an ultimate edge of knowing that continues to inspire scientific inquiry. The question, what caused the Big Bang, naturally leads to an even more profound and challenging inquiry. What was there before the Big Bang? This question, however, immediately confronts a fundamental conceptual hurdle. The notion that time itself, as we understand it, may have begun with the Big Bang. If time originated with the universe's expansion, then the concept of before becomes meaningless in a physical sense, posing a significant challenge to both scientific and philosophical thought. In the framework of general relativity, space and time are not separate, fixed entities, but are interwoven into a single fabric called spacetime. This fabric is dynamic, capable of being stretched, warped, and curved by the presence of mass and energy. The Big Bang theory describes the evolution of this spacetime fabric from an initial, extremely dense and hot state. According to the standard model, if we trace the expansion of the universe backward in time, we arrive at a point where spacetime itself collapses to an infinitely dense singularity. At this singularity, not only does matter become infinitely compressed, but the very fabric of spacetime ceases to exist in a meaningful way. If spacetime itself began at the Big Bang singularity, then there was no before in the temporal sense. Time, as a dimension along which events unfold, would have emerged with the universe. This is a difficult concept to grasp because our human experience is deeply rooted in a linear progression of time, where every event has a preceding cause. We intuitively think of a beginning as something that must have been preceded by something else. However, if time itself is a property of the universe, and the universe began at the Big Bang, then asking what happened before is akin to asking what is north of the North Pole. The question loses its meaning within the defined coordinate system. This idea was famously articulated by Stephen Hawking, who suggested that asking what happened before the Big Bang is like asking what is south of the South Pole. There is nothing south of the South Pole because the concept of south breaks down at that point on the globe. Similarly, the concept of before breaks down at the Big Bang singularity. This perspective implies that the universe, along with time, simply came into existence at that point, and there is no prior physical state or temporal dimension to discuss. However, this interpretation is based on general relativity, which, as discussed, breaks down at the singularity. The search for a quantum theory of gravity aims to resolve this breakdown and might offer alternative perspectives on the nature of time at the very earliest moments. If a quantum theory of gravity eliminates the singularity, replacing it with a finite albeit extreme state, then the concept of before might regain some physical meaning, though perhaps not in the conventional sense. One theoretical possibility that addresses time before time is the Big Bounce hypothesis. This idea, often explored within the framework of loop quantum gravity, suggests that the Big Bang was not the ultimate beginning, but rather a rebound from a previous contracting universe. In this cyclic model, the universe undergoes an endless series of expansions and contractions. A previous universe would have contracted to an extremely dense but finite state, avoiding the singularity, then bounced back into expansion, leading to our current Big Bang. If the Big Bounce is correct, then there was indeed a before, a previous cosmic cycle, and time would have existed continuously through the bounce, albeit in a highly compressed and extreme form. This model offers a way to avoid the problem of an absolute beginning of time. Another approach comes from certain models within string theory and M theory, which propose higher dimensions and the existence of branes, multidimensional membranes. In some brane cosmology scenarios, our universe is a three-dimensional brane existing within a higher dimensional space. The Big Bang, in this context, could be the result of a collision between two such branes, or a brane emerging from a higher dimensional bulk. In these models, time might exist in the higher dimensional space even before the brane collision that created our universe. This would mean that before our Big Bang, there was a different kind of reality, operating in higher dimensions, with its own temporal progression. The concept of an eternal inflation also touches upon the idea of time before time. In some inflationary models, inflation, once it starts, never truly ends everywhere. Instead, it continues indefinitely in some regions, constantly spawning new bubble universes within a vast, ever-inflating multiverse. In this scenario, our Big Bang would be just one such bubble universe emerging from a larger, eternally inflating background. Time in the larger multiverse could be continuous, with our universe's beginning being a local event within that larger temporal framework. Philosophically, the idea of time having a beginning is deeply challenging. It forces us to reconsider our fundamental assumptions about causality and existence. If there was no time before the Big Bang, then the concept of a cause in the traditional sense becomes problematic. A cause typically precedes its effect in time. If there is no time, there can be no temporal precedence. This leads to questions about whether the universe caused itself, or if the concept of causation needs to be redefined for the very origin of existence. Ultimately, the question of time before time remains one of the most profound and unanswered questions in cosmology and philosophy. Our current scientific models, primarily general relativity, suggest a beginning of time at the Big Bang singularity. However, the limitations of these models at extreme conditions motivate the search for a quantum theory of gravity, which might offer new insights such as a Big Bounce or a higher dimensional reality, where time could have a more continuous existence. Until such a theory is developed and confirmed, the nature of time at the universe's origin will continue to be a subject of intense speculation and research. Quantum mechanics is a fundamental theory in physics that describes the behavior of matter and energy at the smallest scales, particularly at the level of atoms and subatomic particles. Unlike classical physics, which describes the world in terms of definite positions and momenta, quantum mechanics introduces concepts that are often counterintuitive and probabilistic. Understanding its basic principles is crucial for comprehending the conditions of the very early universe, where quantum effects were dominant and profoundly shaped the cosmos. One of the core principles of quantum mechanics is quantization. This means that certain physical quantities, such as energy, angular momentum, and electric charge, do not exist in continuous values but rather in discrete packets, or quanta. For example, an electron in an atom can only occupy specific energy levels. It cannot exist at any energy in between. When an electron moves from one energy level to another, it absorbs or emits a specific quantum of energy, typically in the form of a photon. This concept was first introduced by Max Planck at the turn of the 20th century to explain black-body radiation, and it revolutionized physics. Another fundamental concept is wave-particle duality. Quantum mechanics posits that particles, such as electrons and photons, can exhibit properties of both waves and particles. For instance, light can behave as a wave, demonstrating phenomena like diffraction and interference, but it can also behave as a particle, photon, carrying discrete packets of energy. Similarly, electrons, which we typically think of as particles, can also exhibit wave-like behavior, as shown in electron diffraction experiments. This duality means that the traditional distinction between waves and particles breaks down at the quantum level. The Heisenberg uncertainty principle is a cornerstone of quantum mechanics. Formulated by Werner Heisenberg, it states that there are fundamental limits to the precision with which certain pairs of physical properties of a particle, such as its position and momentum, can be known simultaneously. The more precisely you measure one property, the less precisely you can know the other. This is not a limitation of our measuring instruments, but an inherent property of nature at the quantum scale. For example, if you know an electron's exact position, its momentum becomes completely uncertain, and vice versa. This principle has profound implications for the vacuum itself. According to quantum mechanics, even seemingly empty space, or the quantum vacuum, is not truly empty. Instead, it is a hive of activity, constantly fluctuating with the spontaneous creation and annihilation of virtual particles. These particle-antiparticle pairs briefly pop into existence from the vacuum, exist for an incredibly short time, and then disappear back into the vacuum, all in accordance with the uncertainty principle. While these virtual particles cannot be directly observed, their effects are measurable, for example, in the Casimir effect. This concept of a dynamic fluctuating vacuum is highly relevant to the early universe. The probabilistic nature of quantum mechanics is another key departure from classical physics. Unlike classical physics, which predicts definite outcomes for events, quantum mechanics predicts the probabilities of various outcomes. For example, when an electron is in a superposition of states, a combination of multiple possible states simultaneously, we cannot know its exact state until it is measured. The act of measurement collapses the wave function, forcing the electron into a single definite state. This inherent randomness and the role of observation are central to the quantum world. The relevance of these quantum mysteries to the early universe is profound. In the very first moments after the Big Bang, the universe was incredibly small, dense, and hot. It was compressed to scales where quantum effects were not just relevant but absolutely dominant. The entire observable universe, which is now billions of light years across, originated from a region that was smaller than a subatomic particle. At these scales, the classical laws of physics, particularly general relativity, which describes gravity on large scales, break down. This is where the need for a quantum theory of gravity arises. To fully understand the Planck epoch, from time 0 to 10 to the power of minus 43 seconds, where all four fundamental forces were unified and quantum effects of gravity were significant, a theory that successfully combines quantum mechanics with general relativity is essential. Without it, we cannot fully describe the initial conditions of the universe or resolve the singularity problem. Theories like string theory and loop quantum gravity are attempts to achieve this unification. Furthermore, quantum mechanics plays a crucial role in the origin of structure in the universe, particularly through the theory of cosmic inflation. Inflation proposes that the universe underwent an extremely rapid, exponential expansion in its earliest moments. During this inflationary period, tiny microscopic quantum fluctuations in the energy field driving inflation, the inflaton field, were stretched to macroscopic scales. These quantum jitters, which are inherent uncertainties in the quantum vacuum, became the seeds of all the large-scale structures we see today. The slight overdensities caused by these stretched quantum fluctuations eventually grew, under gravity, into the galaxies, galaxy clusters, and the vast cosmic web. The observed pattern of temperature fluctuations in the cosmic microwave background radiation is remarkably consistent with the predictions of inflation, reinforcing the idea that quantum mechanics played a fundamental role in shaping the universe's structure. The matter-antimatter asymmetry, another puzzle of the early universe, may also find its explanation in quantum mechanics. While the precise mechanism is still unknown, theories of baryogenesis suggest that subtle quantum processes in the very early universe, perhaps involving interactions beyond the standard model of particle physics, led to a slight excess of matter over antimatter, allowing our matter-dominated universe to exist. In classical physics, a vacuum is understood as simply empty space, a region devoid of matter or energy. If one were to remove all particles, all radiation, and all fields from a given volume, what would remain, according to classical thought, is nothingness. However, the revolutionary insights of quantum mechanics radically altered this perception. In the quantum realm, the concept of a vacuum is profoundly different. It is not truly empty, but rather a dynamic, effervescent sea of fluctuating energy from which particles can momentarily emerge and vanish. This is the concept of the quantum vacuum. The fundamental principle underlying this vibrant nature of empty space is the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle, formulated by Werner Heisenberg, states that there are inherent limitations to the precision with which certain pairs of physical properties of a particle can be simultaneously known. For example, one cannot precisely know both the position and the momentum of a particle at the same time. Similarly, there is an uncertainty relationship between energy and time. This energy-time uncertainty means that for a very short duration, the energy of a system, even a vacuum, can fluctuate significantly from its average value. The shorter the time interval, the larger the possible energy fluctuation. These transient energy fluctuations in the quantum vacuum are sufficient to allow for the spontaneous creation of pairs of particles and their corresponding antiparticles. These are known as virtual particles. For an incredibly brief moment, a particle and its antiparticle, such as an electron and a positron, or a photon and an antiphoton, which is just another photon, can spontaneously pop into existence from the quantum vacuum, drawing energy from these temporary fluctuations. However, because energy must ultimately be conserved, these virtual particles must annihilate each other almost immediately, returning their borrowed energy back to the vacuum. The entire process occurs so quickly that these virtual particles typically cannot be directly observed or detected in the conventional sense. They are virtual precisely because they do not exist as stable, long-lived entities. The analogy often used to describe the quantum vacuum is that of a boiling or bubbling pot. While the pot may appear calm from a distance, up close, one sees incessant activity on the surface, with bubbles constantly forming, rising, and bursting. Similarly, the quantum vacuum, though appearing empty on macroscopic scales, is ceaselessly churning with the birth and death of these ephemeral virtual particle-antiparticle pairs. It is not a static void, but a roiling, energetic environment, even at its lowest possible energy state. Despite their fleeting nature, the existence of virtual particles in the dynamic quantum vacuum is not merely a theoretical curiosity. It has been confirmed by various experimental observations. One of the most famous pieces of evidence is the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and later experimentally verified. The Casimir effect describes a small attractive force that arises between two uncharged parallel conducting plates placed very close to each other in a vacuum. The explanation for this force lies in the quantum vacuum. Virtual particles with wavelengths too large to fit between the plates are excluded from that region, while virtual particles with smaller wavelengths can still exist there. This creates an imbalance in the pressure exerted by the virtual particles, resulting in a net attractive force that pushes the plates together. The precise magnitude of this force has been measured and matches theoretical predictions derived from the quantum vacuum. Another piece of evidence comes from the Lamb shift in atomic physics. The Lamb shift refers to a tiny but measurable difference in the energy levels of electrons in atoms, specifically between the two 20^12 and two 20p½ states of the hydrogen atom, which according to the Dirac equation, a relativistic quantum mechanical equation, should have identical energies. This minute energy shift is explained by the interaction of the electron with virtual photons continuously appearing and disappearing in the quantum vacuum. These virtual photons momentarily perturb the electron's energy levels, causing the observed shift. The experimental confirmation of the Lamb shift in 1947 provided a crucial validation of quantum electrodynamics, the quantum field theory of electromagnetism, and the reality of virtual particles. The concept of the quantum vacuum also plays a role in understanding Hawking radiation from black holes. Stephen Hawking theorized that black holes are not entirely black, but can emit thermal radiation. This phenomenon is explained by the behavior of virtual particle-antiparticle pairs near the black hole's event horizon. Sometimes, one particle of a virtual pair falls into the black hole while its partner escapes. The escaping particle effectively carries away energy from the black hole, causing it to slowly lose mass and eventually evaporate over immense timescales. This process highlights how the quantum vacuum's fluctuations can have macroscopic, observable consequences in extreme gravitational environments. The vacuum energy associated with these quantum fluctuations is a concept that also intersects with cosmology. In modern cosmological models, a form of vacuum energy is considered a candidate for dark energy, the mysterious force responsible for the accelerated expansion of the universe. If the quantum vacuum truly has a non-zero energy density, this energy would exert a repulsive gravitational force, acting like a cosmological constant. However, theoretical calculations of vacuum energy are vastly larger than the observed dark energy density, presenting a significant puzzle known as the cosmological constant problem. This discrepancy suggests that our understanding of vacuum energy or gravity at the quantum level is still incomplete. The concept that a universe, as vast and complex as our own, could theoretically emerge from nothing is one of the most provocative and challenging ideas in modern cosmology. This nothing, however, is not the intuitive philosophical void, but rather the quantum vacuum, a concept far removed from classical emptiness. The speculative idea that our universe could have arisen as a quantum fluctuation within this dynamic quantum vacuum pushes the boundaries of our scientific understanding and philosophical contemplation of origins. As established, the quantum vacuum is not truly empty. Instead, it is a restless, fluctuating field of energy, governed by the principles of quantum mechanics. Virtual particles constantly pop into and out of existence, borrowing energy for fleeting moments before annihilating. This incessant activity means that even in its lowest energy state, the quantum vacuum is never truly still. It possesses a fundamental inherent instability. It is this inherent instability and the principle of quantum fluctuation that form the basis for the idea of a universe emerging from what some physicists refer to as nothing, meaning a state devoid of classical matter, energy, space, and time, but not devoid of quantum potential. The conceptual leap involves considering whether an entire universe, with its immense energy and complexity, could itself be a giant quantum fluctuation. Normally, virtual particles are microscopic and short-lived due to the energy-time uncertainty principle. For a macroscopic structure like a universe to emerge, it would seem to require an enormous violation of energy conservation. However, some theoretical models propose a way around this. One key insight comes from considering the total energy of the universe. According to general relativity, energy in the universe includes not only the positive energy of matter and radiation, but also the negative energy associated with gravity. Gravitational energy is negative because gravity is an attractive force. As objects pull closer together, their gravitational potential energy decreases. In certain cosmological models, it is theoretically possible that the positive energy of all the matter and radiation in the universe could be precisely balanced by the negative gravitational potential energy. If this were the case, the total net energy of the universe would be exactly zero. A zero-energy universe is crucial for the universe from nothing hypothesis. If the total energy of the universe is zero, then its emergence from the quantum vacuum would not violate the fundamental principle of energy conservation. a quantum fluctuation of zero total energy could theoretically arise spontaneously from the vacuum without requiring an external energy source. This idea has been explored by physicists like Edward Tryon in the 1970s and later elaborated upon by Stephen Hawking and Lawrence Krauss. Hawking, in particular, emphasized that if the universe's total energy is zero, then the universe can and will create itself from nothing. The second crucial element that allows a microscopic quantum fluctuation to inflate into a macroscopic universe is cosmic inflation. If the universe did indeed emerge as an incredibly tiny quantum fluctuation, it would initially be microscopic, existing for an extremely short duration. However, if such a fluctuation contained within it the seeds of an inflaton field, a hypothetical field responsible for cosmic inflation, then this tiny region could undergo a period of incredibly rapid exponential expansion. This inflationary burst, lasting for only a tiny fraction of a second, would stretch the microscopic fluctuation to macroscopic, even cosmic scales, creating the vast, uniform and flat universe we observe today. Without inflation, a spontaneous quantum fluctuation would simply pop into and out of existence without ever growing into a persistent large-scale universe. This concept suggests that the universe did not need a pre-existing space or time to emerge into. Instead, space and time themselves would have been created as part of the quantum fluctuation. Before the fluctuation, there was no before in a temporal sense, and no where in a spatial sense, as those concepts emerge with the universe. It's a universe spontaneously tunneling into existence from the quantum vacuum, much like a particle tunneling through an energy barrier in quantum mechanics. This is often compared to the phenomenon of quantum tunneling, where a particle can pass through a barrier even if it does not have enough classical energy to do so, relying on the probabilistic nature of quantum mechanics. Physicists such as Alexander Vilenkin have further developed these ideas. Vilenkin's work, particularly his tunneling from nothing proposal, suggests that the universe could have quantum mechanically tunneled from a state of nothing, a state without classical spacetime, into a state where inflation began. This would imply a spontaneous, uncaused emergence of the universe, rooted entirely in the laws of quantum physics. It is important to emphasize that the universe from nothing hypothesis is highly speculative and remains a subject of ongoing theoretical research and debate within the scientific community. It relies on extrapolating quantum mechanics to scales and conditions far beyond what can be directly tested in laboratories. Furthermore, the definition of nothing used in this context, the quantum vacuum, is itself a rich, energetic entity, not the absolute void that might be intuitively imagined. This leads to philosophical discussions about whether a quantum vacuum truly constitutes nothing. Critics argue that if the vacuum has properties and laws that govern it, then it is not truly nothing. Despite its speculative nature, the idea of a universe emerging from the quantum vacuum provides a potential scientific answer to the question of cosmic origins, operating entirely within the framework of known physical laws. It eliminates the need for a supernatural creator or a pre-existing cosmic state outside of physical laws. Instead, it suggests that the universe's existence might be a natural consequence of the fundamental principles of quantum mechanics, arising from the very fabric of reality itself. However, direct empirical evidence for such an event is currently beyond our reach, and many profound questions about the ultimate origin and nature of existence continue to remain open. Loop quantum gravity, often abbreviated as LQG, is a theoretical framework that attempts to unify two of the most successful but fundamentally incompatible theories in physics: Albert Einstein's general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the smallest subatomic scales. The primary goal of loop quantum gravity is to develop a quantum theory of gravity, resolving the singularity problem of the Big Bang and providing a consistent description of spacetime at the most extreme conditions, such as those present in the very early universe or inside black holes. General relativity, published by Einstein in 1915, revolutionized our understanding of gravity by treating it not as a force acting at a distance, but as a manifestation of the curvature of spacetime. Massive objects warp the fabric of space-time, and this curvature dictates how other objects move. This theory has been incredibly successful in describing phenomena from planetary orbits to the expansion of the universe. However, general relativity is a classical theory. It does not incorporate the probabilistic and quantized nature of reality at the quantum level. Quantum mechanics, developed throughout the 20th century, successfully describes the other three fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force, in terms of quantized particles and fields. It introduced revolutionary concepts such as wave-particle duality, the Heisenberg uncertainty principle, and the idea of a quantum vacuum. The problem arises when one tries to apply quantum mechanics to gravity. General relativity describes space-time as a smooth, continuous manifold, while quantum mechanics suggests that everything, including space-time itself, should be quantized or made of discrete units at sufficiently small scales. Attempts to simply quantize general relativity using standard quantum field theory techniques lead to infinities that cannot be removed, indicating a fundamental incompatibility. Loop quantum gravity approaches this problem by attempting to quantize spacetime directly, rather than quantizing a gravitational field within a pre-existing spacetime. The central idea of LQG is that space and time are not continuous as we perceive them, but are instead discrete, made up of tiny indivisible units, much like a fabric woven from tiny fundamental loops or atoms of spacetime. These loops are incredibly small, existing at the Planck scale, which is approximately 10 to the power of minus 35 meters. At our everyday macroscopic scales, these discrete units are imperceptible, and spacetime appears continuous and smooth, just as a finely woven cloth appears smooth from a distance. In LQG, the fundamental entities are not spacetime points, but rather quantum states of geometry. These states are described by spin networks, which are graphs where lines represent quantized loops of gravity, and nodes represent discrete units of volume. These spin networks evolve over time, forming spin foams that describe the quantum history of spacetime. This granular structure of spacetime has profound implications. It suggests that there is a minimum possible unit of length and a minimum possible unit of area and volume, meaning that space is truly atomized at its most fundamental level. One of the most significant implications of loop quantum gravity is its potential to resolve the singularity problem of the Big Bang. In general relativity, extrapolating the universe backward in time leads to an initial singularity, where density and spacetime curvature become infinite. This is where the theory breaks down. In LQG, because space itself is quantized and there is a minimum unit of volume, an infinite density becomes impossible. Instead, as one traces the universe backward, it reaches a state of maximum but finite density and curvature, where it then bounces back into expansion from a previous contracting phase. This concept is known as the Big Bounce. The Big Bounce hypothesis, emerging from LQG, suggests that our universe is not the first, but rather one in a potentially infinite series of universes, each undergoing cycles of expansion and contraction. In this scenario, the Big Bang is not an absolute beginning of time and space, but a transition point where a contracting universe rebounded into an expanding one. This offers a radical alternative to the initial singularity, providing a continuous, albeit extreme, timeline for the cosmos. It implies that before the Big Bang, there was a previous cosmic epoch, albeit one that was contracting. Loop quantum gravity also addresses the challenge of quantum mechanics at the event horizon of black holes. Just as it avoids the Big Bang singularity, LQG suggests that the singularity at the center of a black hole is also replaced by a quantum bounce. This implies that matter falling into a black hole might not be destroyed in a singularity, but could instead pass through a bounce into another region of spacetime, or perhaps even another universe. It is important to note that loop quantum gravity is still a theoretical framework under development, and it has not yet been experimentally verified. The scales at which its effects would be noticeable, the Planck scale, are far beyond the reach of current particle accelerators or astronomical observations. However, LQG offers a mathematically rigorous and internally consistent approach to unifying gravity with quantum mechanics. It provides a compelling picture of a universe where space and time are not just backdrops for physical events, but are active, quantized participants in the cosmic drama, with profound implications for our understanding of the universe's ultimate origin and the nature of reality itself. Its predictions, particularly the Big Bounce, offer a fascinating alternative to the standard Big Bang singularity, pushing the boundaries of scientific inquiry into the most fundamental questions about existence. The standard Big Bang model describes the origin of our universe from an initial, infinitely dense and hot singularity. However, this singularity represents a point where the laws of physics, particularly Albert Einstein's theory of general relativity, break down. This breakdown has led physicists to explore alternative models that might provide a more complete and continuous description of cosmic history. One such compelling alternative is the Big Bounce theory, which proposes that our universe did not begin from a singularity but rather emerged from the collapse of a previous universe, rebounding from an extreme but finite state of compression. The Big Bounce hypothesis offers a solution to the singularity problem inherent in the Big Bang. Instead of an infinite density at time zero, the Big Bounce posits that the universe contracted to an incredibly dense but finite state, a point where quantum gravitational effects become dominant and prevent further collapse. At this point of maximum compression, the universe bounces and begins a new phase of expansion, leading to the universe we observe today. This implies that our universe is not the first, but part of an endless, or at least very long, cycle of expansion and contraction. The theoretical underpinnings for the Big Bounce largely come from the field of quantum gravity, specifically from loop quantum gravity, or LQG. General relativity, a classical theory, predicts the singularity. However, at the Planck scale, an unimaginably tiny length, approximately 10 to the power of minus 35 meters, and time, approximately 10 to the power of minus 43 seconds, quantum effects of gravity are expected to become dominant. Loop quantum gravity attempts to bridge the gap between general relativity and quantum mechanics by quantizing spacetime itself, suggesting that space is made of discrete indivisible units rather than being continuous. Within the framework of loop quantum gravity, the singularity is avoided. As the universe contracts, the density and curvature of spacetime increase. However, LQG predicts a strong repulsive force at extremely high densities, a quantum gravity effect that becomes significant when the universe approaches the Planck density. This repulsive force acts like a quantum pressure that prevents the universe from collapsing to an infinite density. Instead, it forces the contracting universe to rebound into a new phase of expansion. This mechanism is what gives the theory its name, the Big Bounce. This means that for a universe undergoing a Big Bounce, time does not have an absolute beginning. Instead, time would have existed continuously through the bounce. The universe would have undergone a period of contraction, reaching a minimum but non-zero size and finite maximum density, before transitioning seamlessly into a new phase of expansion. This offers a radical solution to the question of what was before the Big Bang. The answer would be a previous phase of cosmic contraction. The idea of a cyclic universe, which the Big Bounce naturally implies, has been considered by cosmologists for a long time. However, older cyclic models, often based purely on classical general relativity, face significant challenges, particularly the entropy problem. In a universe that repeatedly contracts into a big crunch and then re-expands from a new Big Bang, each cycle would accumulate entropy. Entropy, a measure of disorder or the unavailable energy in a system, always increases in a closed system according to the second law of thermodynamics. If entropy were to increase with each cycle, subsequent cycles would become progressively larger and longer, eventually leading to a cold, dilute, and infinitely expanded state, breaking the cycle. The quantum nature of the Big Bounce, however, might offer ways to circumvent this problem, though this remains an active area of research and debate within the scientific community. The Big Bounce model offers several intriguing implications for the observable universe. For example, it might provide a natural explanation for the flatness of the universe and the uniformity of the cosmic microwave background, CMB, without necessarily relying on cosmic inflation. In some Big Bounce scenarios, the preceding contracting phase could naturally smooth out initial anisotropies and flatten the universe, providing an alternative to the inflationary mechanism. Furthermore, the quantum fluctuations that would become the seeds of cosmic structure could arise from the quantum effects during the bounce itself, rather than solely from inflation. Observational evidence for the Big Bounce is currently indirect and highly sought after. Scientists are looking for specific signatures in the cosmic microwave background, which might retain subtle imprints from the pre-bounce era. One potential signature could be a distinct pattern of gravitational waves, different from those predicted by standard inflationary models. Gravitational waves are ripples in space-time, and if they were generated during the extreme conditions of the bounce, their unique characteristics could offer clues. Detecting and analysing these primordial gravitational waves is a major goal for future astronomical missions. Another area of investigation involves the specific distribution of density fluctuations in the universe. While inflation predicts a nearly scale-invariant spectrum of fluctuations, some Big Bounce models might predict slight deviations from this, particularly on very large scales, which could be discernible with future precision measurements of the CMB and large-scale structure surveys. It is important to emphasize that the Big Bounce theory remains a theoretical framework, still under active development and refinement. It is not yet as widely accepted as the standard inflationary Big Bang model, largely due to the lack of direct observational evidence that can definitively distinguish it from other cosmological models. However, its elegance in resolving the singularity problem and its potential to offer a complete, non-singular description of the universe's entire history make it a compelling and actively researched alternative in modern cosmology. It represents a significant departure from the idea of a singular beginning, proposing instead a universe that cycles through eternal phases of birth, death, and rebirth. The idea of a universe that undergoes repeated phases of expansion and contraction, an endless cosmic cycle, has a long history in cosmological thought, predating even the modern Big Bang theory. Such models, often referred to as cyclic or oscillatory universes, propose that our current phase of cosmic expansion is not a unique event, but merely one iteration in an eternal cosmic dance of birth, death, and rebirth. While historically challenged by fundamental physical problems, modern theoretical advances, particularly from quantum gravity and string theory, have led to renewed interest and sophisticated new versions of these cyclic scenarios. Classically, cyclic universe models often envisioned a big crunch scenario. In this view, the universe, after a period of expansion, would eventually exhaust its kinetic energy, and gravity would then pull all matter and energy back together. This contraction would culminate in a hot, dense state, a big crunch, which was often conceptually linked to the Big Bang as the starting point for a new expansion phase. The universe would then rebound from this crunch, effectively resetting itself for a new cycle. However, these classical cyclic models faced a significant theoretical hurdle known as the entropy problem. Entropy, a measure of disorder or the dispersal of energy, is always increasing in a closed system according to the second law of thermodynamics. If the universe were truly cyclical in the classical sense, each cycle would begin with a certain amount of entropy and end with a greater amount. This means that successive cycles would be progressively larger and longer, with higher total entropy, eventually leading to a state of perpetual expansion and increasing coldness, thus preventing a true return to initial conditions and breaking the cycle. If the universe has already undergone an infinite number of cycles, then it should have already reached a state of maximum entropy, which is not what we observe. This problem largely led to the abandonment of classical cyclic models in favour of a universe with a distinct beginning, like the Big Bang. The advent of modern quantum cosmology, however, has reopened the door for cyclic models by offering potential solutions to the entropy problem and the singularity problem. The Big Bounce theory, discussed previously, is a prime example of a modern cyclic model rooted in quantum gravity, specifically loop quantum gravity. In the Big Bounce, the universe does not collapse to an infinite density singularity, a big crunch, but reaches a finite maximum density before quantum gravitational effects cause it to rebound. This finite bounce might offer a way to avoid the increasing entropy issue, although this remains an active area of debate among physicists. Some proposals suggest that the entropy from the previous cycle is effectively flushed away or diluted during the quantum bounce, allowing each new cycle to start with fresh low-entropy conditions. Another prominent class of modern cyclic models arises from brane cosmology, a framework derived from string theory. These models, often called ekpyrotic or cyclic universe models, propose a fundamentally different mechanism for the Big Bang. Instead of a singular beginning of time, these models suggest that our four-dimensional universe exists as a brane, a higher dimensional membrane, floating within a larger, higher dimensional space called the bulk. In this scenario, the Big Bang is not an explosion from a point, but rather the result of a collision between two such branes, or an interaction between our brane and another brane in the bulk. In the ekpyrotic model, derived from the Greek word for conflagration, two branes slowly approach each other over a very long period. As they draw near, the gravitational interaction between them becomes strong, causing the branes to accelerate towards each other. Their collision releases enormous amounts of energy, which manifests as the hot, dense Big Bang phase of our universe. After the collision, the branes might bounce apart, expand and cool, and then slowly move back together over cosmic timescales, setting up the next collision and a new cycle. This model, proposed by Paul Steinhardt and Neil Turok, offers a potential solution to the entropy problem by suggesting that the universe undergoes a long, cold, and empty contracting phase between cycles, allowing entropy to be effectively diluted or minimized before the next bounce. These brane-world cyclic models also offer alternative explanations for cosmic phenomena typically addressed by inflation theory. For example, the smoothness and flatness of the universe and the origin of cosmic structure could arise from the properties of the brane collision itself, or from quantum fluctuations that occur during the long, slow contraction phase preceding the collision. This provides a compelling alternative to the inflationary paradigm for explaining the observed features of the cosmic microwave background. Different cyclic models vary in their specific mechanisms and predictions. Some propose that the universe eternally expands and contracts, others that it continues to expand for a vast period before collapsing, and some models suggest that the cycles are not perfectly identical but evolve over time. Common to all these models is the absence of a true beginning in time. Instead, the universe has always existed in some form, undergoing transformations. The motivation for exploring cyclic models is manifold. Beyond resolving the singularity problem and potentially the entropy problem, they offer a philosophical appeal of an eternal universe, avoiding the question of what came before the Big Bang by positing that there was always a before. They also provide a different theoretical laboratory for investigating fundamental physics, offering testable predictions that may distinguish them from other cosmological models. However, cyclic universe models, particularly the modern quantum gravity and brane world versions, remain highly theoretical and face significant challenges. Direct observational evidence that can definitively distinguish between a single Big Bang with inflation and a cyclic universe is still lacking. Scientists are actively looking for specific cosmological signatures, such as unique patterns in the cosmic microwave background, or the characteristics of gravitational waves, that could provide evidence for or against these cyclic scenarios. While the questions surrounding their viability persist, cyclic models continue to represent a vibrant and intriguing area of research, pushing the boundaries of our understanding of cosmic origins and the ultimate fate of the universe. The concept of brane worlds is a fascinating and highly speculative idea that emerges from string theory, one of the leading candidates for a theory of everything that aims to unify all fundamental forces of nature, including gravity. In string theory, the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings. The introduction of extra spatial dimensions beyond the three spatial dimensions and one time dimension we experience is a common feature of many string theory models. Brane-world cosmology takes this idea further, proposing that our entire universe is confined to a higher dimensional membrane, or brane, floating within a larger, higher dimensional space called the bulk, or multiverse. To understand the concept of a brane, it is helpful to use an analogy. Imagine a two-dimensional sheet of paper existing in a three-dimensional room. Creatures living on the paper can only move left, right, forward, or backward along the surface of the paper, they are unaware of the dimension extending up or down from their paper world. In the brane world scenario, our familiar 3 spatial dimensions, plus 1 time dimension, constitute such a brane which is embedded in a higher dimensional space. This higher dimensional space, the bulk, would contain extra spatial dimensions that we cannot perceive directly. The existence of these extra dimensions is a key prediction of string theory. While early string theories required 10 or 11 dimensions, brane world models often operate with a minimum of 5 dimensions, our 4-dimensional spacetime, the brane, and at least 1 extra spatial dimension, the bulk. The reason we do not observe these extra dimensions is usually explained in one of 2 ways. Either they are compactified, or curled up into extremely tiny, unobservable loops at every point in our spacetime, or they are large, but our matter and forces are confined to the brane. In the brane world scenario, ordinary matter, protons, neutrons, electrons, and the forces that govern them, electromagnetism, strong nuclear force, weak nuclear force, are all confined to our 4-dimensional brane. This means that photons, electrons, and the particles that mediate the strong and weak forces cannot travel into the extra dimensions. They are stuck on our brane. However, gravity, according to this theory, is different. Gravity is described by the warping of spacetime itself, and in brane world models, gravity is thought to be able to leak or propagate into the extra dimensions of the bulk. This property has significant implications. One of the motivations for brane world models is to address the hierarchy problem in physics. The hierarchy problem refers to the vast difference in strength between gravity and the other 3 fundamental forces. Gravity is extraordinarily weak compared to electromagnetism, for instance. If all forces originated from a unified theory at high energies, why is gravity so much weaker at lower energies? Brane world models offer a possible solution. If gravity can propagate into extra dimensions while other forces are confined to our brane, then its effective strength on our brane would appear much weaker because its influence is spread out across a larger, higher dimensional space. This idea suggests that gravity is not inherently weak, but rather its strength is diluted by its access to the bulk. The concept of brane worlds also provides a radical new perspective on the origin of the universe and the Big Bang. In some brane world models, such as the ekpyrotic or cyclic universe models, the Big Bang is not an explosion from a singularity, but rather the result of a collision between 2 or more branes. Imagine our universe's brane slowly approaching another parallel brane in the bulk. As these branes draw closer, their gravitational interaction increases, eventually leading to a collision. This collision, or bounce, releases enormous amounts of energy, which then manifest as the hot, dense Big Bang phase that expands and cools into our universe. After the collision, the branes might separate again, expanding and cooling, only to eventually move back together for another collision, leading to a cyclical universe. This offers an alternative to cosmic inflation for explaining the flatness and uniformity of the universe and the origin of cosmic structure, which could arise from the collision itself or from quantum fluctuations on the branes during their slow approach. Another intriguing implication of brane world models is the potential for dark matter to reside on a different brane or in the bulk. If dark matter particles are not confined to our brane but interact only gravitationally, or are located on a nearby shadow brane, it could explain why we cannot detect them through electromagnetic interactions. Their gravitational influence would still be felt on our brane, accounting for the observed gravitational effects of dark matter in galaxies and clusters. Brane world cosmology is an active area of theoretical research, but it remains highly speculative. There is currently no direct experimental evidence to confirm the existence of extra dimensions or branes. Scientists are exploring potential ways to test these ideas. For example, if extra dimensions are large, they might manifest themselves as subtle deviations from Newton's law of gravity at very small distances, which could be detectable in precision experiments. Particle accelerators like the Large Hadron Collider could also potentially produce exotic particles that indicate the existence of extra dimensions, or even miniature black holes that rapidly evaporate if gravity is strong at small scales due to extra dimensions. The mathematical consistency and elegance of string theory and its brane world extensions continue to make them compelling candidates for a unified theory of physics. While the concepts are abstract and far removed from everyday experience, They offer profound new ways of thinking about the universe's structure, its origin, and our place within a potentially much larger, multi-dimensional cosmos. The idea that our universe is merely a slice or a membrane within a grander cosmic architecture challenges conventional notions of reality and fuels the ongoing quest for a deeper understanding of the fundamental nature of space-time and matter. The standard Big Bang theory describes the universe expanding from an extremely hot and dense state, often extrapolated back to an initial singularity where the laws of physics break down. This unresolved singularity has led physicists to explore alternative scenarios for the universe's origin. One such intriguing concept arises from string theory, specifically within the framework of brane cosmology, where the Big Bang is not a singular point in time, but rather the result of a collision between higher dimensional membranes, or branes. To grasp the idea of colliding branes, one must first understand the concept of a brane itself. In string theory, the fundamental constituents of reality are not point-like particles, but tiny, vibrating one-dimensional strings. For string theory to be mathematically consistent, it requires the existence of extra spatial dimensions beyond the three we experience every day, plus the one dimension of time. While these extra dimensions might be curled up to an unobservably small size, some string theory models propose that they are large, and our entire universe is confined to a four-dimensional surface, or brane, embedded within this larger, higher dimensional space, often called the bulk. In this brane world scenario, all the particles that make up ordinary matter, like electrons and quarks, and the forces that govern their interactions, electromagnetism, the strong nuclear force and the weak nuclear force, are confined to our brane. They cannot travel into the extra dimensions. However, gravity, being a manifestation of the curvature of space-time itself, is thought to be able to propagate into these extra dimensions. This distinction is crucial for the colliding brane models of the Big Bang. The most prominent example of a colliding brane model is the ekpyrotic universe scenario, which later evolved into cyclic universe models, proposed by physicists Paul Steinhardt and Neil Turok, among others. The term ekpyrotic comes from an ancient Greek word meaning conflagration, or cosmic fire, referring to a universe that is born from fire and returns to fire. In the ekpyrotic model, our universe is a three-dimensional brane that exists parallel to at least one other three-dimensional brane in a higher dimensional bulk. These two branes are not static. They are slowly moving towards each other. This approach phase is characterized by a long period of slow contraction of the universe, which is very different from the standard Big Bang's initial expansion. During this slow contraction, the universe is cold, empty, and nearly flat. This long, cold phase allows for the smoothing out of any initial irregularities and the natural generation of the seeds of cosmic structure. As the two branes slowly draw closer, their gravitational interaction becomes increasingly strong. This gravitational attraction pulls them together, causing them to accelerate towards each other. The climactic event in this model is the collision of these two branes. This collision is not a gentle touch, it is a violent high-energy impact. The immense kinetic energy of the colliding branes is converted into the matter and radiation that fill our universe. This sudden release of energy, and the subsequent rapid expansion of our brane, is what we perceive as the Big Bang. So in this view, the Big Bang is not the absolute beginning of time from a singularity, but rather a violent energetic event that marks a transition from a previous phase of cosmic history. The collision effectively reheats the universe, creating the hot, dense conditions that the standard Big Bang theory describes. After the collision, the branes are thought to bounce apart, and our universe enters a new phase of expansion. This expansion continues for an incredibly long time, during which stars and galaxies form, evolve, and eventually die. As the universe expands and becomes increasingly dilute, the branes slowly begin to drift back towards each other, driven by forces within the bulk. This sets the stage for the next collision, initiating a new Big Bang and a new cycle of cosmic evolution. This makes the ekpyrotic model a type of cyclic universe, where the cosmos undergoes an endless series of collisions, expansions, and contractions. One of the significant advantages claimed by colliding brane models is their potential to address some of the puzzles that cosmic inflation was introduced to solve, without necessarily relying on inflation itself. For instance, the flatness problem, why the universe is so spatially flat, can be explained by the long, slow contraction phase preceding the collision. During this phase, any initial curvature of the brane would be squeezed out, making it appear flat at the moment of collision and subsequent expansion. The horizon problem, why distant regions of the cosmic microwave background have the same temperature, can also be addressed. In the ekpyrotic model, these regions were in causal contact during the slow, pre-collision contraction phase, allowing them to reach thermal equilibrium before the Big Bang event. Furthermore, the origin of the seeds of cosmic structure, the tiny density fluctuations that grew into galaxies, can also be explained by quantum fluctuations occurring on the branes during their slow approach, or at the moment of collision. These models predict a slightly different spectrum of density fluctuations compared to inflationary models, which could potentially be a way to distinguish between them through precise observations of the cosmic microwave background and large-scale structure. It is important to note that colliding brane models are highly theoretical and remain speculative. The existence of extra dimensions and branes has not been experimentally confirmed. While these models offer elegant solutions to some cosmological problems and provide an alternative to the Big Bang singularity, they introduce new complexities and require further development. Observational tests are challenging, as they often rely on detecting subtle signatures in the cosmic microwave background or gravitational waves that would be distinct from those predicted by inflationary Big Bang models. Despite these challenges, the concept of colliding branes represents a powerful and imaginative attempt to push the boundaries of our understanding of cosmic origins, suggesting that our universe might be part of a much grander, multi-dimensional cosmic ballet. The concept of a multiverse suggests that our universe is not the only one, but rather one of many, perhaps an infinite number of universes. This idea, once relegated to the realm of science fiction, has gained increasing traction among theoretical physicists as a potential consequence of various cosmological and quantum theories. The multiverse hypothesis offers profound implications for our understanding of existence, the laws of physics, and our place in the cosmos. The term multiverse encompasses several distinct theoretical concepts, each arising from different areas of physics. It is not a single unified theory, but a collection of scenarios where multiple universes exist. These different types of multiverses can be broadly categorized, though there is some overlap. One type of multiverse arises from the idea of an infinite universe. If space is truly infinite and contains an infinite amount of matter and energy, then according to the laws of probability, everything that can possibly happen will happen an infinite number of times. This implies that there would be infinitely many patches of space, identical to our observable universe, and even infinitely many patches where events unfolded slightly differently. This is often referred to as a level 1 multiverse. In this scenario, the other universes are simply very distant regions of the same, infinitely large universe, beyond our observable horizon. They obey the same physical laws but may have different arrangements of matter. A more complex and often discussed type of multiverse emerges from cosmic inflation, particularly the concept of eternal inflation. This will be elaborated upon in the next section, but in brief, eternal inflation suggests that the process of inflation, which rapidly expanded the early universe, never truly stops everywhere. Instead, it continues indefinitely in some regions, constantly spawning new bubble universes within a vast, ever-inflating background. Each of these bubble universes could have different initial conditions, and potentially even different fundamental physical constants or laws, depending on how the inflationary field decays. This is a level 2 multiverse, where universes can have different physical properties. Another source of multiverse ideas comes from string theory and its extensions, such as M theory. These theories suggest the existence of extra spatial dimensions and a vast number of possible ways these dimensions can be compactified or curled up. Each way of compactifying the extra dimensions could lead to a different set of physical laws and constants in the resulting 4-dimensional universe. This creates a landscape of possible universes, potentially an enormous number, each with its own unique characteristics. Our universe would simply be one point in this vast landscape of possibilities. This also falls under the Level 2 multiverse category. The brane world scenario, where our universe is a membrane in a higher dimensional space, also naturally leads to multiverse concepts, as there could be other branes existing in the same bulk, representing other universes. The many worlds interpretation of quantum mechanics offers a different kind of multiverse, sometimes called a Level 3 multiverse. This interpretation suggests that every time a quantum measurement is made, and a quantum system is forced to choose between multiple possible outcomes, e.g., an electron spin being up or down, the universe splits into multiple parallel universes, with each outcome realized in a different universe. In this view, all possible quantum outcomes are physically realized in some universe. These universes are not separated by vast distances in space, but are parallel in a more abstract quantum sense, constantly branching off from each other. This interpretation is distinct from the cosmological multiverses, as it arises from quantum events within a single, overarching quantum reality. Finally, some theoretical physicists propose a Level 4 multiverse, known as the Mathematical Universe Hypothesis. This extreme idea suggests that all mathematically consistent structures correspond to actual universes. In this view, our universe is just one of many mathematical structures that exist, and there is no deeper reality beyond mathematics. The multiverse idea, particularly the Level 2 cosmological multiverses, offers a potential solution to the fine-tuning problem. The fine-tuning problem observes that the fundamental constants of our universe, such as the strength of gravity, the mass of the electron, the cosmological constant, appear to be incredibly finely tuned for the existence of stars, galaxies, and life. If these constants were even slightly different, the universe might be sterile, incapable of forming complex structures or supporting life. In a multiverse, this fine-tuning is not seen as a coincidence or evidence of design, but rather a statistical inevitability. If there are an immense number of universes, each with different physical constants, then it is not surprising that we find ourselves in one of the rare universes where the conditions are just right for our existence. This is an application of the Anthropic Principle, which states that the universe must have properties that allow for the existence of observers. Despite its explanatory power for certain cosmological puzzles, the multiverse idea remains highly speculative. A major challenge is the lack of direct observational evidence. By definition, other universes in many multiverse scenarios are causally disconnected from our own, making them difficult or impossible to observe directly. This raises questions about the scientific testability and falsifiability of the multiverse hypothesis. However, some theoretical predictions, such as the possibility of bubble universe collisions, leaving detectable imprints on the cosmic microwave background, are being explored as potential indirect tests. In conclusion, the multiverse idea is a profound and evolving concept in theoretical physics. It moves beyond the notion of a single, isolated universe, suggesting a vast landscape of cosmic realities. Whether arising from infinite space, eternal inflation, or the intricacies of string theory, the multiverse challenges our conventional understanding of cosmic uniqueness and offers a framework for addressing some of the deepest puzzles about the nature of our universe and its seemingly special properties. The theory of cosmic inflation, while incredibly successful in addressing several fundamental problems of the standard Big Bang model, paradoxically leads to one of the most mind-bending concepts in modern cosmology, the inflationary multiverse. This idea suggests that if inflation occurred in our universe, it might not have been a one-time event, but rather an eternal process, continuously generating an endless number of new, bubble universes, of which our own is just one. Let us first briefly revisit the concept of cosmic inflation. Inflation is a hypothetical period of extremely rapid, exponential expansion that is thought to have occurred in the first tiny fractions of a second after the Big Bang, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds. This rapid expansion was driven by a hypothetical energy field, often called the inflaton field. When the inflaton field eventually decayed, its energy was converted into the hot, dense matter and radiation that filled the universe, initiating the standard Big Bang expansion we observe today. Inflation elegantly solves the flatness problem, why the universe is spatially flat, the horizon problem, why distant regions of the cosmic microwave background are at the same temperature, and the magnetic monopole problem, the absence of hypothetical particles. The concept of an inflationary multiverse arises from certain properties of the inflaton field and the dynamics of inflation itself. In many inflationary models, the inflaton field does not decay uniformly or simultaneously everywhere. Instead, it fluctuates quantum mechanically. Due to the inherent quantum nature of fields, the inflaton field can fluctuate in its energy level. In some regions of space, the inflaton field might fluctuate to a higher energy state, causing inflation to continue. In other regions, it might fluctuate to a lower energy state, causing inflation to end and convert its energy into matter and radiation, forming a bubble universe. The key insight leading to eternal inflation is that the rate of expansion during inflation is so incredibly rapid that the regions where inflation continues expand exponentially faster than the regions where it ends. This means that even as some regions of space stop inflating and form new universes, the vast majority of the volume of space continues to inflate, creating ever more space for an endless number of new bubbles to form. It is like an endlessly branching tree, where each branch is a region of inflating space, and new leaves, bubble universes, are constantly budding off. This process is called eternal inflation because once it starts, it never truly stops everywhere. It is self-perpetuating. The inflating parent universe continually expands, creating new pockets where inflation ends, leading to the birth of new bubble universes. These bubble universes then expand according to the standard Big Bang model, forming stars, galaxies, and structures within their own boundaries. Our observable universe would be just one such bubble, a tiny patch within this much larger, eternally inflating cosmos. A crucial implication of the inflationary multiverse is that these different bubble universes are likely to have different properties. The way the inflaton field decays can vary from one bubble to another. This means that different bubble universes could have different fundamental physical constants, such as the strength of the fundamental forces, the masses of elementary particles, or even different numbers of spatial dimensions, though most models assume 3 large spatial dimensions. For example, if the value of the cosmological constant, dark energy, is determined by the specific vacuum state of the inflaton field, then different bubbles could have vastly different amounts of dark energy. This diversity of universes provides a compelling, albeit controversial solution to the fine-tuning problem. As noted, the physical constants in our universe appear to be remarkably finely tuned for the existence of life. If, for instance, the strong nuclear force was slightly weaker, atomic nuclei would not hold together. If it was slightly stronger, hydrogen would have fused into helium too quickly, and stars would not have lasted long enough for life to evolve. In an inflationary multiverse, the apparent fine-tuning of our universe is simply a statistical consequence. If there are an infinite number of universes with varying physical laws and constants, then it is not surprising that we find ourselves in one of the rare universes where the conditions are just right for complex structures and life to emerge. We exist in the universe that allows for our existence. This is often referred to as the Anthropic Principle applied to the multiverse. The inflationary multiverse is a theoretical prediction of many leading inflationary models, but it is extremely difficult to test directly. By definition, these other bubble universes are causally disconnected from our own. Light and information from them cannot reach us because the space between them is inflating exponentially fast. This raises questions about the scientific testability and falsifiability of the multiverse hypothesis. However, some researchers are exploring potential indirect signatures. For example, if our bubble universe once collided with another bubble during its early expansion, it might have left a subtle imprint on the cosmic microwave background, such as a cold spot or a specific pattern of anisotropies. Detecting such an imprint would provide compelling, though still indirect, evidence for the existence of other universes. Despite the challenges of direct verification, the inflationary multiverse concept is widely discussed in theoretical cosmology because it arises naturally from a theory, inflation, that is otherwise highly successful in explaining observed features of our universe. It pushes the boundaries of our understanding of cosmic reality, suggesting that our universe is not unique, but part of an unimaginably vast and diverse collection of cosmic bubbles, each with its own history and properties. It transforms the question of what caused the Big Bang into a question of what caused the eternal inflation that spawns countless Big Bangs. The concept of a multiverse, where our universe is but one of many, opens up a vast realm of speculation about what these other universes might be like. Depending on the specific type of multiverse model, the characteristics of these parallel or distant universes could range from being almost identical to our own to being radically different, governed by entirely alien physical laws, or even possessing a different number of spatial dimensions. In the simplest form of a multiverse, often called a level 1 multiverse, these other universes are simply very distant regions of our own infinitely large universe. If space extends infinitely, and the distribution of matter and energy is roughly uniform on very large scales, then statistically, there must be regions far beyond our observable horizon that are identical to our own observable universe, or at least contain similar arrangements of matter. In this scenario, the physical laws and fundamental constants would be the same as ours, but the specific configurations of particles and fields would vary. Given infinite space, any possible arrangement of matter that can exist will eventually repeat. So, in this type of multiverse, there could be another Earth, another Milky Way, or even another version of you simply located an unimaginably vast distance away. These are not truly other universes in the sense of having different laws, but rather extremely distant copies or variations within the same overarching universe. A more profound difference arises in level 2 multiverses, which are often predicted by theories like eternal inflation or string theory's landscape. In these scenarios, the fundamental physical laws and constants can vary from one universe to another. Consider the inflationary multiverse. As discussed, eternal inflation suggests that new, bubble universes are constantly budding off from a larger ever-inflating background. The specific properties of each bubble universe depend on how the inflection field decays within that particular region. This decay process could lead to different values for fundamental constants. For example, different fundamental constants, the strength of the 4 fundamental forces, gravity, electromagnetism, strong and weak nuclear forces, could vary. Imagine a universe where the electromagnetic force is much stronger, atoms might be unstable, or chemical reactions might proceed entirely differently, making complex chemistry impossible. Conversely, if it were too weak, electrons might not bind to nuclei, preventing atom formation. The masses of fundamental particles like electrons and quarks could also differ. If the electron were much heavier, atoms might collapse. If quarks were much lighter, protons and neutrons might not form stable nuclei. The cosmological constant which drives the accelerated expansion of our universe could also take on vastly different values, leading to universes that either expand too rapidly for structures to form or collapse almost immediately. Different particle content. The types of fundamental particles themselves might vary. Perhaps some universes have different sets of quarks and leptons, or entirely new types of particles that do not exist in our universe. This would lead to entirely different forms of matter and energy. Different spatial dimensions. While our universe appears to have 3 large spatial dimensions and 1 time dimension, string theory suggests that there could be many more. In some inflationary or string theory models, the number of large, uncompactified spatial dimensions could vary from one universe to another. A universe with only 2 spatial dimensions would be a flat plane, where complex structures like stars and planets might not be able to form due to gravitational collapse. A universe with 4 or more large spatial dimensions would have vastly different gravitational laws and orbital mechanics, likely preventing stable planetary systems or even atoms from forming. Different initial conditions. Even if the fundamental laws are the same, the initial distribution of matter and energy could vary. Some universes might be born with much greater initial density fluctuations, leading to a universe dominated by massive black holes, or so smooth that no structures form. The string theory landscape also contributes to the idea of diverse universes. String theory requires extra spatial dimensions, which are typically compactified or curled up into tiny shapes. The way these extra dimensions are curled up determines the specific physical laws and constants we observe in our four-dimensional universe. String theory suggests there are an enormous number of ways, perhaps 10 to the power of 500 or more, to compactify these dimensions, each corresponding to a different vacuum state and thus a different set of physical laws. Each of these different compactifications could represent a distinct universe within the multiverse. Our universe would simply be one specific valley in this vast landscape of possibilities. In these level 2 multiverses, the other universes are truly separate entities, often causally disconnected from our own. We cannot travel to them, nor can we send signals to them, because the space between them is either expanding too rapidly, as in eternal inflation, or they exist in different inaccessible regions of the higher dimensional bulk. The many-worlds interpretation of quantum mechanics, a level 3 multiverse, presents a different kind of other universe. In this view, every time a quantum measurement is made, and a quantum system's wave function collapses into a definite state, the universe splits into multiple parallel universes. Each possible outcome of the quantum measurement is realized in a different universe. For example, if a photon can either pass through a slit or be reflected, then in one universe it passes through, and in another it is reflected. These universes are not spatially separated but exist in a quantum superposition, constantly branching. In this scenario, all universes would share the same fundamental physical laws, but their histories and specific events would diverge at every quantum choice point. This leads to an unimaginably vast number of parallel realities, where every possible outcome of every quantum event is realized somewhere. Finally, the mathematical universe hypothesis, a level 4 multiverse, is the most abstract. It posits that every mathematically consistent structure corresponds to a real, existing universe. In this view, the physical laws and constants of other universes would simply be different mathematical structures. The speculation about other universes is driven by a desire to explain why our universe has the specific properties it does, particularly the fine-tuning that allows for life. If there are countless universes with varying properties, then it is not surprising that we find ourselves in one that is hospitable to our existence. While these ideas are largely theoretical and lack direct observational confirmation, they represent a frontier in our understanding of cosmic reality, pushing the boundaries of what is possible and challenging our anthropocentric view of the cosmos. The fine-tuning problem is one of the most intriguing and perplexing puzzles in modern cosmology and fundamental physics. It refers to the observation that the fundamental constants of nature and the initial conditions of the universe appear to be remarkably precise, or tuned, to allow for the existence of stars, galaxies, and ultimately life as we know it. If these constants or conditions were even slightly different, the universe would be a radically different place, likely inhospitable to any form of complex structure or life. This apparent precision raises profound questions about chance, necessity, or design. Let's consider some examples of these finely tuned parameters. The strength of the strong nuclear force is critical. This force binds quarks into protons and neutrons and holds protons and neutrons together in atomic nuclei. If it were just a few % weaker, stable atomic nuclei beyond hydrogen couldn't form, preventing the existence of all heavier elements necessary for chemistry and life. Conversely, if it were slightly stronger, hydrogen would have fused into helium too rapidly in the early universe, leaving no hydrogen to fuel long-lived stars like our Sun, which are essential for the gradual evolution of life. Similarly, the strength of the electromagnetic force governs interactions between charged particles, holding electrons in orbit around atomic nuclei. If this force was significantly stronger, electrons would be pulled too tightly to the nucleus, preventing chemical bonds and complex molecules from forming. If it were weaker, electrons might not bind to nuclei at all, making atoms impossible. The mass difference between protons and neutrons is another crucial parameter. Neutrons are slightly more massive than protons, by about 0.1% of their mass. If neutrons were slightly less massive than protons, all protons would have decayed into neutrons in the early universe, leading to a universe composed only of neutrons, with no hydrogen to form stars or water. If the mass difference were larger, neutrons would decay too quickly before they could form helium, again leading to a universe without heavier elements. The cosmological constant, representing the energy density of empty space and responsible for the universe's accelerating expansion, is also incredibly precise. Observations suggest its value is extremely small, yet non-zero. Theoretical predictions for its value, based on quantum field theory, are vastly larger, by a factor of 10 to the power of 120, than what we observe. If the cosmological constant were much larger and positive, the universe would have expanded so rapidly in its early moments that matter would have been too diluted to form stars and galaxies. If it were negative and larger, the universe would have quickly collapsed back on itself. The observed value is incredibly precise, allowing for structure formation over billions of years. Furthermore, the initial density fluctuations, the tiny variations in density imprinted on the cosmic microwave background that served as the seeds for cosmic structure, also appear to be finely tuned. If these fluctuations were too small, gravity wouldn't have been strong enough to pull matter together to form stars and galaxies. If they were too large, the universe would have quickly collapsed into massive black holes, leaving no stable structures. Lastly, the number of spatial dimensions in our universe, which is 3 large spatial dimensions, is vital. If there were fewer, like 2, gravity would behave differently, making stable orbits for planets impossible. If there were more, such as 4 or more large dimensions, planetary orbits would be unstable, and atoms themselves might not be stable, as electrons would spiral into the nucleus. The cumulative effect of these seemingly precise values is what constitutes the fine-tuning problem. It appears as if the universe's fundamental parameters were set with extreme precision to allow for the existence of complexity and life. This observation prompts several lines of thought. One possibility is coincidence or luck, that the fine-tuning is simply an incredibly improbable coincidence. We are just extraordinarily lucky to exist in a universe where the numbers happen to fall into the narrow range required for life. However, the sheer improbability of so many independent parameters being precisely tuned makes this explanation unsatisfying for many scientists. Another possibility is necessity, that there is a deeper, currently unknown theory that dictates these constants must have the values they do. If such a theory of everything were discovered, it might show that the seemingly arbitrary values are, in fact, uniquely determined by fundamental principles. However, no such theory has been developed yet that explains all the constants. For some, the fine-tuning points towards design, a designer or creator who intentionally set these parameters for the universe to be life-permitting. This is a theological or philosophical interpretation that lies outside the realm of scientific inquiry, as it is not testable or falsifiable by scientific methods. The most common scientific explanation for fine-tuning is the Multiverse Hypothesis. If our universe is just one of an enormous, perhaps infinite number of universes, and if these other universes have different fundamental constants and laws, then it is not surprising that we find ourselves in one of the rare universes where the conditions are suitable for life. In this scenario, there is no tuning involved. It is simply a matter of selection bias. We can only observe universes that permit observers. This concept is closely tied to the Anthropic Principle, which will be discussed in the next section. The fine-tuning problem remains a significant challenge and a powerful motivator for research in fundamental physics and cosmology. It pushes scientists to explore new theories, such as string theory and inflationary cosmology, that might naturally lead to a vast landscape of possible universes, or to discover deeper principles that constrain the values of these constants. Regardless of the ultimate explanation, the apparent fine-tuning of our universe highlights the delicate balance of physical laws that allow for the existence of complexity, consciousness, and the very possibility of asking such profound questions. The Anthropic Principle is a philosophical and scientific concept that attempts to address the fine-tuning problem, which observes that the fundamental constants and laws of our universe appear to be remarkably precise for the existence of life. Rather than trying to explain why these constants have their specific values, the Anthropic Principle suggests that we observe the universe to have the properties it does simply because only in such a universe could observers like us exist. It is a statement about the relationship between the universe and the presence of intelligent observers within it. The Anthropic Principle appears in 2 main forms: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The WAP is less controversial and more widely accepted. It suggests that the physical and cosmological properties of the universe are not random but instead fall within a narrow range that allows for the emergence of carbon-based life. In other words, the universe must have certain characteristics, like the right rate of expansion or age, because if it didn't, observers like us wouldn't exist to notice it. The WAP doesn't attempt to explain why the universe is life-permitting, but rather highlights the observational bias in our existence. It's often discussed alongside the multiverse theory. If countless universes exist, each with varying physical laws, it's no surprise we find ourselves in one that happens to support life. In contrast, the strong anthropic principle, SAP, is more speculative and controversial. It takes the argument further by claiming that the universe must have the properties necessary for life to eventually develop. This implies that the emergence of observers is not just a consequence of the universe's conditions, but may actually be a fundamental feature or purpose of the universe itself. Some interpretations of the SAP suggest that the universe is in some way designed or inherently directed toward producing conscious observers, raising philosophical and metaphysical questions about purpose and necessity in the cosmos. The SAP can be interpreted in various ways. One interpretation suggests that there is an underlying law or principle that forces the universe to evolve in a way that leads to the emergence of life. Another, more radical interpretation, sometimes called the participatory anthropic principle, suggests that observers are necessary to bring the universe into existence, perhaps by collapsing quantum wave functions or by somehow actualizing physical reality. These stronger forms of the anthropic principle often venture into philosophical or theological territory and are not generally considered testable scientific hypotheses in the same way as the WAP. The anthropic principle is not a predictive scientific theory in the traditional sense. It does not provide a mechanism for explaining how the universe came to be finely tuned. Instead, it offers a framework for interpreting the observed fine-tuning. It shifts the question from why is the universe so perfectly suited for life, to given that we exist, what must the universe be like? The anthropic principle has found application in various scientific contexts, influencing how physicists interpret observed cosmic phenomena. For instance, it has been used in predicting cosmic parameters. In some cases, even before direct observational evidence, physicists have employed anthropic arguments to anticipate the values of certain cosmological features. A notable example is the cosmological constant. Some physicists suggested it must be incredibly small, arguing that a larger value would prevent the formation of galaxies, thus making life impossible. The principle is also crucial in interpreting the multiverse. If a multitude of universes exists, each with different properties, then our presence in a universe perfectly suited for life isn't a miraculous coincidence, but a statistical inevitability. Our existence simply selects for the specific universe or region that supports life, sidestepping the need for a deliberate design and explaining apparent fine-tuning through this concept of statistical sampling. Furthermore, the anthropic principle encourages a deeper understanding of fundamental physics, prompting researchers to investigate how the underlying laws and constants of the universe might inherently connect to the emergence of complexity in life itself. However, the anthropic principle also faces criticism. Some argue that it is unfalsifiable, meaning it cannot be proven wrong, which makes it less scientific. Critics also contend that it is an argument of last resort, an admission that we cannot explain the fine-tuning through fundamental physics. It can also be seen as a form of circular reasoning. The universe is suitable for life because we are here to observe it. Furthermore, the definition of life, or observer, can be vague, leading to ambiguity. Despite these criticisms, the anthropic principle serves as a powerful reminder of the profound connection between the universe's fundamental properties and the existence of observers within it. It highlights the unique conditions that allow for complexity to emerge from the simplicity of the early cosmos. While it may not provide a causal explanation for the universe's fine-tuning, it offers a framework for understanding why we find ourselves in a universe that appears so remarkably hospitable to life, especially when considered in the context of a potentially vast and diverse multiverse. Imagine standing at the very edge of Earth's atmosphere, where the blue sky fades into blackness and gravity loosens its grip. One more step and you're no longer bound to our world. You've crossed into space, a place of endless silence and chilling mystery. But here's the real question. What comes after that? What lies beyond the edge of space? Is it just more stars, more galaxies? Or is there something truly that defies the rules of physics, time, and imagination? Before we begin, let us know where in the world you're watching from and what time it is for you right now. Drop it down in the comments below and settle in for a fascinating journey through space. To truly understand the mind-blowing discoveries made by the James Webb Space Telescope, also known as JWST, we first need to travel all the way back to the very beginning of everything, the birth of the universe itself. This incredible moment is known as the Big Bang. But don't picture a typical explosion, like fireworks or a bomb. The Big Bang was something entirely different. It was the sudden and unbelievably fast expansion of the universe from a single point that was unimaginably small, scorching hot, and densely packed with energy. This cosmic event happened around 13,800 million years ago, and it wasn't just the beginning of the universe. It was the moment when space, time, and all matter burst into existence. In the first few seconds after the Big Bang, the universe was like a stormy sea of energy, filled with tiny particles zipping around in every direction. It was so incredibly hot, hotter than anything we can imagine with temperatures reaching trillions of degrees, that atoms couldn't even form. Everything was pure chaos, with no stars, no planets, and no galaxies, just glowing, blinding energy. For hundreds of millions of years, the universe stayed in this strange state. Slowly but steadily, it expanded and cooled down. Then, something extraordinary happened. Around 400 million years after the Big Bang, the first atoms came together, mainly hydrogen and helium. These simple gases were pulled together by the force of gravity, and as they clumped together, they heated up and ignited the very first stars. These newborn stars didn't shine alone. They gathered into the first primitive galaxies, lighting up the darkness of space and creating what scientists call the cosmic dawn. This was a magical era when the universe was beginning to form its first structures, and this is exactly the moment in time that the James Webb Space Telescope is now peering into. It's capturing breathtaking pictures and precious data from when the first galaxies were just starting to glow, helping us uncover the mysteries of our universe's earliest days. The James Webb Space Telescope is unlike anything humans have ever built. It was launched into space on the 25th of December 2021, a cosmic Christmas gift to humanity. But JWST doesn't orbit the Earth like most satellites. Instead, it travels around the Sun, parked at a special spot called the Second Lagrange Point, or L2. This point is about 1 million miles away from Earth. It was carefully chosen so the telescope could stay stable and far away from Earth's heat and light, giving it a crystal clear view of the universe. What makes JWST truly special is its ability to see the universe in a kind of light our eyes can't detect, infrared light. While visible light is blocked by clouds of cosmic dust, infrared light can sneak through, revealing hidden stars, galaxies, and other objects that other telescopes can't see. This is especially important for studying the oldest and most distant objects in space. As the universe expands, the light from faraway galaxies gets stretched into longer, redder wavelengths. This stretching, called the cosmological redshift, turns visible light into infrared light. Because JWST is designed to detect this faint, stretched-out infrared glow, it can look farther into space, and farther back in time, than any telescope before it. It's like having a time machine that shows us what the universe looked like more than 13,500 million years ago, just a few hundred million years after everything began. When JWST sent back its very first images, scientists were amazed. The telescope had looked deep into the ancient past and captured pictures of galaxies forming only a few hundred million years after the Big Bang. This was the universe's baby stage, and yet it was already full of surprises. Astronomers expected to find only a few tiny galaxies, but they found far more than they had imagined. These early galaxies came in all kinds of strange shapes and sizes, much different from what scientists expected. It turned out that the early universe was more lively, more crowded, and more chaotic than anyone had guessed. One of the most exciting things JWST discovered was the presence of proto-galaxies. These were the first clumps of stars that would eventually grow into the massive galaxies we see today. But they didn't look neat or orderly. Instead of smooth spirals or round shapes, these early galaxies were messy, clumpy, and wild. New stars were being born at an incredible pace, with entire clusters lighting up in bursts of energy. This discovery challenged older ideas that galaxy formation was slow and gentle. JWST showed us that the early universe was full of energy and drama, changing our entire view of how the cosmos took shape. JWST also brought us closer to finding the very first stars ever formed, called Population 3 stars. These stars were unlike anything we see in today's skies. They were made from the purest ingredients left behind by the Big Bang, mostly hydrogen and helium, without any heavier elements like carbon or oxygen. Because of this, scientists believe these stars were huge, far larger than our Sun, and burned extremely hot and bright. But they lived fast and died young, burning up their fuel quickly and exploding in massive blasts called supernovae. Some of these explosions were so powerful that they became rare events called pair instability supernovae, the most intense explosions in the universe. When these ancient stars exploded, they scattered heavier elements into space, which later helped form new stars, planets, and even the building blocks of life. By uncovering clues about these long-gone giants, scientists are slowly solving the mystery of how the universe grew from simple beginnings into the rich, complex place we live in today. But JWST doesn't stop at looking into the distant past. It is also helping scientists understand two of the biggest puzzles in the universe: dark matter and dark energy. These strange forces make up about 95% of everything in the universe, yet we can't see or touch them. Dark matter doesn't shine or give off any kind of light, but we know it's there because of the way it pulls on galaxies with its powerful gravity. JWST helps detect dark matter by watching how it bends the light from galaxies behind it, a trick of nature called gravitational lensing. This lets astronomers map where dark matter might be hiding and figure out how it helps shape the structure of the universe. Then there's dark energy, which is even more mysterious. It's a force that's causing the universe to expand faster and faster over time. By measuring how quickly galaxies are racing away from us, JWST gives scientists new clues about how dark energy works. These discoveries are incredibly important, because they might help answer one of the biggest questions of all. Will the universe keep expanding forever, or will it eventually stop and collapse? JWST is also on the hunt for something even closer to home: life beyond Earth. One of its most exciting missions is to study planets outside our solar system, known as exoplanets. Some of these distant worlds may have just the right conditions to support life. Using its advanced tools, JWST can examine the gases in a planet's atmosphere and look for special chemical signs that might hint at life. If it finds water vapor, that could mean the planet has clouds or even rain. If it finds methane, it might come from volcanic activity, or maybe even microbes. And if it finds lots of oxygen, scientists will start to wonder, could there be plants or alien life forms producing it? Just imagine the moment when we finally find proof that we're not alone in the universe. That would change everything we thought we knew. However, the James Webb Space Telescope is much more than a camera in space. It is a window into the deepest mysteries of time and space. It has already confirmed some theories and shattered others. One of its most surprising discoveries is that fully formed galaxies seem to appear much faster than anyone expected. According to older theories, it should have taken billions of years for galaxies to slowly grow and develop. But JWST is showing us galaxies that came together in a cosmic blink of an eye. This means scientists might need to rewrite major parts of our understanding of the universe. One of the most surprising discoveries made by the James Webb Space Telescope has to do with the huge black holes found in the centers of some of the oldest galaxies ever seen. According to what scientists believed before, these black holes should have been small, because there simply hadn't been enough time in the early universe for them to grow so large. But the James Webb Space Telescope has spotted black holes that are much bigger than expected. This means that black holes might form and grow much faster than scientists ever imagined. It's a mystery that challenges everything we thought we knew about how black holes begin and how they evolve over time. These strange and unexpected findings show us that the universe is still full of secrets, and thanks to the incredible technology of the James Webb Space Telescope, we're only beginning to discover what's out there. Now, let's pause for a moment and take a closer look at the amazing machine behind these discoveries. The James Webb Space Telescope, often called JWST, is one of the most advanced tools humanity has ever sent into space. It has a massive mirror covered in gold, which stretches more than 21 feet across. That's about the size of a small house. This mirror was specially designed to collect the faintest rays of infrared light coming from faraway galaxies. But what makes it even more fascinating is how it's built, not as one single piece, but from 18 golden hexagon-shaped segments. These pieces unfolded like petals in space, creating a beautiful pattern that looks like a giant golden flower blooming in the darkness. But JWST's power doesn't stop with its giant mirror. It's loaded with advanced instruments, like powerful cameras and spectrographs. These tools don't just take pictures, they analyze light in incredible detail. They can break down the light from stars and galaxies that are millions or even billions of light years away. By studying this light, scientists can learn what stars are made of, how they're moving, how old they are, and much more. It's like doing archaeology, but instead of digging into the Earth, scientists are digging into the ancient history of the universe, uncovering stories written in light that has travelled across space and time for billions of years. The James Webb Space Telescope is more than just a brilliant piece of engineering, it's also a symbol of international teamwork. While the project was led by NASA, the space agency of the United States, two other major partners helped make it possible: the European Space Agency and the Canadian Space Agency. The European Space Agency provided important scientific instruments, and the Canadian Space Agency added high-tech equipment and funding to help the mission succeed. This global partnership shows what humanity can achieve when we work together. Scientists, engineers, and dreamers from all over the world joined forces to build something truly extraordinary. The JWST proves that when people unite around a common goal, like exploring the universe, we can reach new heights and make discoveries beyond imagination. Looking at what JWST has already found, it's impossible not to feel excited about what's still to come. The telescope is gathering so much valuable data that scientists will be studying it for many years into the future. These discoveries will inspire new generations of astronomers and scientists to keep asking questions and to keep pushing the boundaries of what we know. And JWST is just the beginning. In the coming years, more amazing space missions are getting ready for launch. One of them is the Nancy Grace Roman Space Telescope, which will give us an even wider view of the cosmos. Another is the European Extremely Large Telescope, a giant observatory being built on Earth, which will give us incredibly sharp views of distant galaxies. All of these tools will work together, helping us uncover even more secrets about the universe, how it started, how it works, and where we fit in. These efforts are about more than just science. They're also about human curiosity, the drive to understand where we came from, and the deep connection we feel with the stars above. Every mission like JWST helps us feel a little closer to the universe and a little more connected to each other. The James Webb Space Telescope has already changed the way we see the universe. By looking back over 13.5 billion years into the past, it's giving us a view of the cosmos as it was just after the Big Bang. The universe is unimaginably vast, stretching out farther than our minds can fully grasp. For thousands of years, people have looked up at the night sky, wondering where it all began and how it came to be. Over the last few centuries, scientists have worked tirelessly to solve the mysteries of the cosmos. They've asked big questions. How did the universe start? What has happened to it over time? One of the most fascinating clues to answering these questions comes from something called redshift. Though it might sound like a science fiction term, redshift is a real and powerful phenomenon that helps scientists understand how the universe has been expanding ever since it was born. To understand what redshift is and why it matters, we first need to talk about light. Yes, the same light that shines from a flashlight or the sun. Light moves in waves, just like the ripples you see when you toss a stone into a calm pond. These waves come in many different lengths. Some waves are short and others are long. The length of a light wave is what gives it its colour. Shorter waves look blue or violet, while longer ones appear red. Now, here's where things get exciting. When scientists study the light coming from stars and galaxies, they look very closely at those waves. By measuring how long or short they are, they can learn all sorts of things, like what the object is made of, how far away it is, and even how fast it's moving. Redshift happens when those waves of light get stretched out during their long journey through space. When the light's stretched, its waves grow longer and begin to shift toward the red side of the colour spectrum. That's why we call it redshift. Think of it like this. Imagine a car zooming past you. As it comes closer, the sound it makes is high-pitched. But as it speeds away, the sound drops to a lower pitch. This is called the Doppler effect, and it doesn't just happen with sound, it also happens with light. When a star or galaxy moves away from us, the light it gives off stretches, and its colour shifts toward red. In space, this redshift tells us that galaxies are moving away from us, and not just a little bit. Some are racing away at incredible speeds, and the farther away they are, the faster they seem to be fleeing. That's where redshift becomes incredibly important. By measuring how much the light from a galaxy is redshifted, scientists can figure out how fast that galaxy is moving and how far it is from Earth. This discovery changed everything we thought we knew about the universe. Back in the early part of the 20th century, in the year 1929, an American astronomer named Edwin Hubble made a groundbreaking observation. While studying distant galaxies through his telescope, he noticed something truly astonishing. Every galaxy he looked at seemed to be moving away from Earth. And not only that, the farther away the galaxy was, the faster it was moving. From this, Hubble came up with what is now called Hubble's law, which says that the universe is expanding. This means that space itself is stretching, like dough rising in an oven. The galaxies aren't flying through space, they're being carried farther apart as space itself grows. This was one of the biggest clues that helped support the Big Bang Theory, the idea that the entire universe began from one incredibly hot and dense point around 13.8 billion years ago. Since that moment, the universe has been growing, and redshift is one of the ways we can track that growth. Whenever scientists detect redshifted light coming from a galaxy, they can estimate how far away that galaxy is, and more incredibly, how long ago that light started travelling toward us. In fact, the more redshifted the light, the longer it has been journeying through space. This means that redshift doesn't just tell us about distance, it lets us look back in time. Imagine this. When we observe a galaxy that is billions of light years away, we're seeing it as it was billions of years ago. The light from that galaxy has taken a very, very long time to reach us, sometimes more than 13 billion years. So, in a way, telescopes are like time machines. When we detect strong redshift, we're not just seeing how far away something is, we're seeing how it looked when the universe was still young. The galaxies with the highest redshifts, the ones furthest from us, show us what the universe looked like only a few 100 million years after the Big Bang. These galaxies are incredibly valuable to scientists because they offer a rare peek into the universe's early days. Back then, everything was different. Space was hotter, denser, and packed with more raw materials like gas and dust. The first stars and galaxies were just beginning to form, lighting up the cosmos for the first time. Studying these early galaxies is like peeling back the layers of time. Every new discovery helps us understand how the universe changed from a tiny, blazing hot point into the gigantic and complex structure we see today. To study these faraway galaxies and their redshifted light, astronomers use extremely powerful telescopes. The Hubble Space Telescope, launched in the year 1990, and the newer James Webb Space Telescope, launched in December of the year 2021, have been essential for this mission. These space telescopes can see incredibly faint light coming from galaxies that are located billions of light years away. Light so dim and ancient that no ordinary telescope could ever detect it. When scientists examine the light from these distant galaxies, they measure exactly how much it has been stretched. The more it's stretched, the higher the redshift, and the older the light is. This allows astronomers to map out the history of the universe, piece by piece, light by light. So what do we see when we look at these high redshift galaxies from the early universe? Surprisingly, they look nothing like the big, beautiful spiral or elliptical galaxies we see today. These early galaxies were small, clumpy, and often strange in shape. They were still being built, still forming stars and still gathering gas and dust to grow. Many of them were crashing into each other and merging, huge cosmic events that caused bursts of star formation and reshaped their structures. Over billions of years, these early galaxies slowly grew larger, calmer, and more organized, eventually turning into the majestic galaxies we see in the modern universe. But by studying them in their youth, through the redshifted light they left behind, astronomers can learn how galaxies grow up, how stars are born, and how the universe itself has evolved over time. One of the most exciting things about studying galaxies that are extremely far away is that they let us look deep into the past, into a time when the very first stars in the universe were born. These first stars are called Population 3 stars, and they are unlike any stars we see today. Scientists believe they formed shortly after the Big Bang, a time when the universe was still incredibly young and everything was made mostly of two very simple gases, hydrogen and helium. Back then, the universe was a quiet, dark place, filled only with these gases floating in all directions. But slowly, over millions of years, gravity started to pull the gases together, squeezing them tighter and tighter. Eventually, this pressure caused the gas clouds to collapse, and that's when the first stars burst into life. These early stars were massive, many times larger than our Sun, and they burned much hotter and brighter than anything we see today. But they were missing something important. They didn't have heavier elements like carbon, oxygen, or nitrogen, which are essential for creating life. Instead, they were made almost entirely of the two lightest elements, hydrogen and helium. When these giant stars finally reached the end of their lives, they exploded in powerful blasts called supernovae. These explosions were incredibly violent and spread newly created heavier elements into space, elements that didn't exist before. It was only through the deaths of these stars that things like carbon, oxygen, and iron were made. These elements later came together to form new generations of stars, planets, and eventually even life, including us. In many ways, the birth and death of these first stars were some of the most important events in the universe's history. They were like the first building blocks in the construction of everything that followed: galaxies, solar systems, Earth, and all living things. By studying these very old and distant galaxies, scientists are slowly uncovering the story of how the simple early universe transformed into the complex and beautiful place we see today. One of the most fascinating periods in this early cosmic story is called the Epoch of Reionization. This was a time when the universe went through a dramatic change. Before this era, the universe was dark and cloudy, and light couldn't travel very far. But when the first stars started to shine, their light began to ionize the surrounding gas, basically giving energy to the atoms and breaking them apart. This changed the gas from being thick and foggy to becoming clear and see-through. Suddenly, light could move across the universe more freely. This important moment helped shape the clear, star-filled sky we see today. Now, you might be wondering, how do we know all this? We weren't there, after all. The answer lies in something called redshift. Redshift is what happens to light from faraway galaxies as it travels across the vast distances of space. As this light moves toward us, it stretches out and shifts to a redder colour, because the universe is expanding. The farther the galaxy, the more stretched out the light becomes, and the older the image we're seeing. So when astronomers look at galaxies with very high redshift, they are actually looking back in time. They are seeing what those galaxies looked like billions of years ago when the universe was young. This isn't time travel like in science fiction movies, where people hop into machines and fly into the past. Instead, it's more like reading an ancient message carried by light that's been on a journey for billions of years. This light is like a time capsule. It holds clues about how the universe looked when the first stars and galaxies were just beginning to form. By studying it carefully, scientists can piece together the story of how the universe evolved, from a simple, empty space full of gas to a place filled with stars, planets, and the potential for life. It's amazing to think that the light we see today from faraway galaxies, like the Andromeda Galaxy or even more distant ones, has travelled through space for millions or even billions of years before finally reaching Earth. Every photon of light that hits our telescopes carries a piece of cosmic history. This idea makes us realise just how vast and old the universe is and how small we are in comparison. The study of redshift and ancient galaxies is one of the most exciting fields in modern science. In the next few decades, powerful new telescopes like the James Webb Space Telescope may help us learn even more. We could discover how the very first stars and galaxies came to be, how black holes formed in the early universe, and maybe, even more thrilling, if there are signs of life beyond Earth. Galaxies are enormous collections of stars, gas, dust, and something mysterious called dark matter. All of these things are held together by one powerful force, gravity. Galaxies come in many different shapes and sizes. Some, like our own Milky Way, are spiral-shaped, with long, curved arms spinning around a central core, kind of like a cosmic pinwheel. Others are shaped more like smooth, rounded balls. These are called elliptical galaxies, and they often contain older stars and look less detailed. Then there are irregular galaxies, which don't follow any clear shape at all. These often got their strange appearance from violent crashes or close encounters with other galaxies. But galaxies aren't just floating randomly through space. They are the main building blocks of the universe. Inside these giant star cities, new stars are born, live bright lives, and eventually die in dramatic ways, like exploding in powerful blasts called supernovae. These life and death cycles help shape the future of galaxies and create the ingredients needed to form new stars and planets. Galaxies also contain planets, moons, comets, asteroids, and all the other things that make up our known universe, including our own home, Earth. When it comes to size, galaxies can vary tremendously. Some are relatively small, with just a few billion stars. Others are incredibly huge, containing hundreds of billions or even trillions of stars. Our galaxy, the Milky Way, is somewhere in the middle. It holds about 200 billion stars. And here's the truly mind-blowing part. Scientists believe there are billions of galaxies scattered across the universe that we can see with telescopes. Each one has its own story, its own journey, and its own clues about how the universe began and how it continues to change over time. Every single galaxy, big or small, plays a part in this cosmic adventure. Experts think that galaxies started to form only a few 100 million years after the Big Bang, which is the term used to describe the powerful beginning of the universe. This incredible event is thought to have happened around 13.8 billion years ago. At that time, the universe was extremely hot, dense, and full of energy. The only elements around were hydrogen and helium, which are the lightest and simplest elements known. As the universe began to cool down, gravity started pulling together huge clouds of gas and dust. These clouds got denser and eventually collapsed in on themselves, creating the first stars. Over time, these newborn stars began to group together to form the very first galaxies. But these early galaxies were very different from the ones we see today. They were smaller, made mostly of hot young stars, and had very few of the heavier elements that come from older stars. Even so, these early galaxies laid the foundation for the larger, more complex ones that would grow over billions of years. Since the time of the Big Bang, the universe has been expanding, stretching out in all directions. Galaxies have slowly drifted farther and farther apart. What's even more surprising is that this expansion is not slowing down. It's actually speeding up. Scientists don't fully understand why, but it's one of the biggest mysteries in cosmology today. Meanwhile, galaxies have continued to grow and change. They crash into each other, merge, and form even bigger and more detailed structures. These cosmic interactions have helped shape the beautiful, massive galaxy clusters and star systems we see all around us today. But in recent times, a powerful new telescope has completely changed the way we think about all of this. The James Webb Space Telescope, often called JWST, has made some discoveries that have stunned scientists around the world, One of the most surprising discoveries is the finding of very old galaxies that seem to have formed much earlier than anyone ever thought possible. According to earlier theories, the first galaxies should have started forming around 400 to 500 million years after the Big Bang. That's because the universe needed time to cool down before stars could begin forming from the leftover gas. But JWST has found galaxies that may have appeared even earlier, just a few 100 million years after the universe began. Even more shocking, these galaxies look mature. They have organized shapes and show signs of active star formation. This suggests that they came together much faster than we previously believed. One of the most jaw-dropping discoveries made by JWST was a galaxy that appears to have formed only 230 million years after the Big Bang. This is far sooner than anyone expected. For a galaxy to form in such a short time, the conditions in the early universe must have been very different from what we imagined. It hints that the process of galaxy formation might have been much quicker and more efficient, or that we're missing some key piece of the puzzle. These findings are extremely important because they challenge everything we thought we knew about how galaxies and the universe came to be. If galaxies could form this fast, it means the early universe may have had special conditions, perhaps unknown types of matter, faster star-making processes, or chemical mixtures we haven't yet identified. It forces scientists to go back and rethink their models of the early universe. And what's even more fascinating is that these ancient galaxies seem to be bursting with activity. They are full of young stars being born at a very fast rate. Scientists had believed that in the early universe, star formation would be slow. That's because there weren't yet enough heavy elements, like carbon and oxygen, which are created in the cores of dying stars and are needed to form new ones. But if these early galaxies are already forming stars so quickly, it could mean two things. Either the conditions for starbirth were better than we thought, or we were wrong about how the first stars came into being in the first place. Some of the galaxies discovered by the James Webb Space Telescope are turning out to be far larger and more complicated than anyone ever expected. And what's even more surprising, these galaxies are incredibly old, dating back to a time not long after the universe first began. Scientists always thought that the earliest galaxies were small, rough, and not very developed. They believed that it would take billions of years for galaxies to become large and filled with different types of stars. But JWST has revealed a very different story. These ancient galaxies already have beautiful, detailed shapes, some even with spiral arms and well-organized structures. They are home to all kinds of stars, not just one type, showing a surprising variety and richness. This completely challenges the older view that early galaxies were simple and messy. It's like opening a history book and suddenly finding a chapter that was never supposed to exist. These discoveries have raised many new questions, especially about two of the biggest mysteries in science: dark matter and dark energy. Together, these invisible forces make up about 95% of all the mass and energy in the universe. Yet even today, scientists still don't fully understand what they are or how they work. The strange shapes and fast formation of these early galaxies hint that dark matter might have played a much bigger role than anyone realized. Perhaps it acted like a hidden framework, pulling normal matter together faster and helping galaxies form more quickly. Dark energy, which is thought to be driving the universe's expansion, might also have been stretching space in ways we never expected. The more we discover, the more it feels like we've only just begun to uncover the universe's secrets. These recent findings are so important that they could completely rewrite what we thought we knew about the early days of the cosmos. Old theories are starting to fall apart, and scientists will now need to come up with new ideas to explain how these massive galaxies appeared so quickly after the Big Bang. This is a thrilling moment in the world of science because it means that in the next few years, we could uncover more discoveries that totally change how we think about the universe's beginnings. Because of what JWST has found, researchers now have to take a fresh look at how galaxies form and evolve. That means rethinking ideas about dark matter, how stars are born, and how the entire structure of the universe developed when it was still very young. The evidence points toward an era filled with activity, mystery, and rapid changes, especially during the first few 100 million years after the Big Bang. That early time, once thought to be quiet and slow-moving, now seems to have been bursting with energy and transformation. These discoveries open the door to a whole new level of exploration. Scientists may soon learn more about how early galaxies interacted with each other. Were they more connected than we ever imagined? Did they grow by merging together, or by feeding off the energy of nearby stars and gas? These are the kinds of questions JWST is helping to answer. Another area of interest is the role of supermassive black holes, giant objects thought to lie at the heart of most galaxies. These mysterious giants might have helped shape galaxies right from the start, acting like cosmic engines that influenced how fast galaxies grew and how stars formed around them. One of the most mind-blowing discoveries in modern astronomy came from the observation of a distant galaxy known as GNZ11. This galaxy is located an astonishing 13.4 billion light-years away from Earth. That means we are seeing it as it looked only 400 million years after the Big Bang, at a time when the universe was still extremely young, just beginning to light up with stars. This makes GNZ11 one of the very earliest galaxies ever seen by human eyes. What truly amazed scientists was how huge this galaxy already was, even though it had only existed for a relatively short time. You would expect such a young galaxy to be small and still forming, but GNZ11 turned out to be packed with stars, hundreds of billions of them, making it as massive as the Milky Way, which is more than 13 billion years old and has had plenty of time to grow and evolve. Seeing such a large and complex galaxy so early in cosmic history was like finding a fully grown tree in a place where only tiny sprouts should exist. But there was more. GNZ11 wasn't just big, it was growing incredibly fast. The speed at which it was forming stars and building its structure was far greater than what scientists thought possible for such an early point in the universe's history. This rapid growth suggests that the galaxy had access to a massive supply of gas, the raw material that stars are made from, right when the universe was still in its baby years. This discovery shook the foundations of everything astronomers thought they understood about how galaxies form. For a long time, the belief was that galaxies start small and slowly grow bigger over billions of years. But GNZ11 didn't follow the rules. It seemed to skip ahead in cosmic time, becoming enormous and complex long before it was supposed to. Even more surprising was that GNZ11 wasn't alone. Other ancient galaxies, also located billions of light-years away, showed the same strange behaviour. They were enormous, filled with stars, and some had detailed, organised structures like spirals or bulges. A few even had supermassive black holes, giant objects with the mass of millions or even billions of suns right at their centres. This was a big shock because scientists thought these kinds of galaxies and black holes were something that only developed much later in the universe's history. The big mystery now was, how could galaxies grow so large and become so structured so quickly at a time when the universe was still just a few 100 million years old? One possible explanation is a process scientists call direct collapse. Usually galaxies form gradually as gas clouds pull together under gravity, forming stars over millions of years. But with direct collapse, an enormous cloud of gas might have skipped the usual steps and collapsed quickly into a galaxy, or even a giant black hole. This shortcut would allow a galaxy to grow very fast, almost as if it had taken a leap through time. Another idea is that the conditions in the early universe were very different from what we see today. Back then, the universe was wild and energetic, filled with intense radiation, extreme heat, and vast clouds of gas. These chaotic conditions may have caused gas to clump together more quickly, speeding up the formation of stars and galaxies. It's like a cosmic storm that helped shape entire galaxies faster than anyone expected. Some scientists also think that dark matter played a key role. Dark matter is an invisible type of matter that doesn't emit light, so we can't see it, but it still has mass and gravity. That gravity might have acted like a powerful magnet, pulling in gas and helping galaxies come together much more quickly. If large amounts of dark matter were gathered in one area, they could have acted as a framework or skeleton around which a galaxy could form in record time. One of the most astonishing features of these ancient galaxies is the presence of supermassive black holes at their centres. These black holes are not the result of single stars collapsing. Instead, they are enormous, holding millions or even billions of times the mass of our Sun. And yet, they somehow formed incredibly fast, much faster than scientists had previously thought possible. Normally, a black hole takes billions of years to grow to that size. But here, in galaxies that are only a few 100 million years old, the black holes are already fully formed and gigantic. How did they grow so fast? One idea is that these massive black holes also formed through direct collapse. Instead of forming from a star, a giant gas cloud could have collapsed straight into a black hole, skipping the star stage entirely. Another theory suggests that once the black hole formed, it fed on enormous amounts of gas from its galaxy, growing at an incredible rate by swallowing everything around it. These discoveries have forced scientists to reconsider many of their old ideas about the early universe. For a long time, it was believed that the universe developed slowly and calmly, with galaxies taking their time to form and grow. But now, it appears that the early universe may have been much more exciting and full of sudden dramatic changes. It's possible that galaxies formed in a variety of ways. In some parts of the universe, they might have developed slowly, just as scientists once thought. But in other areas, galaxies may have exploded into existence at lightning speed, fueled by the intense energy, chaotic conditions, and mysterious forces like dark matter. All of this points to one powerful idea. The early universe was not a quiet, dark place slowly waking up. It was a booming, energetic time full of activity. Galaxies forming rapidly, stars lighting up the cosmos, and black holes growing at astonishing speeds. Even the period once called the Cosmic Dark Ages might not have been so dark and quiet after all. Instead, it may have been a time of brilliant explosions and fierce creation, as the first structures of the universe took shape far faster than anyone ever imagined. Most of the galaxies we see in the sky today fall into two main groups: spiral galaxies and elliptical galaxies. Spiral galaxies, like our own Milky Way, have long, curved arms that spin outward from a bright centre. These arms are made up of stars, gas and dust, all swirling around like dancers in a cosmic whirlpool. The whole galaxy moves in a graceful, organised way. Elliptical galaxies, on the other hand, don't have arms or patterns. Instead, they look more like giant glowing balls or stretched out footballs. The stars inside them don't move in neat circles but travel in many different directions, like people wandering through a crowd. These galaxies tend to be older and less active, but when scientists look deep into space, so deep that they are actually looking far back in time, they find something very different. The oldest galaxies, formed when the universe was still very young, do not look organised at all. They are messy, lumpy, and strange. They seem to be in the middle of forming rather than already shaped. This big difference in appearance comes from how galaxies form and change over time. In the early universe, just a few 100 million years after the Big Bang, galaxies were much smaller and didn't have the tidy structure we're used to. Instead of smooth spirals or clean elliptical shapes, these early galaxies looked more like cosmic puzzles with missing pieces. They were full of stars, gas and dust clumped together in uneven patches. It's as if these galaxies were caught in the act of being built, with pieces still flying into place. This chaotic look reflects the wild and turbulent conditions of the young universe. Back then, galaxies were constantly bumping into each other, merging, breaking apart and forming new structures. The universe was a busy, noisy workshop, not a quiet museum of well-arranged galaxies. For a long time, scientists believed that galaxies would slowly grow more organised and settled as they aged. They expected to find neat, smooth shapes, even in the earliest galaxies. But when astronomers began observing the farthest galaxies, the ones that formed more than 13 billion years ago, they saw something unexpected. These ancient galaxies didn't look calm or neat at all. Instead, they looked like tangled balls of stars and gas. Some were oddly shaped, with uneven lumps and jagged edges. Others looked like they were made of smaller galaxies that hadn't finished joining together yet. So, how do we even know what these ancient galaxies looked like, if they are so far away, and the light from them has travelled for billions of years? The answer lies in a fascinating trick of nature: how light moves through space. Light doesn't move instantly, it takes time to travel. The farther away something is, the longer its light takes to reach us. So, when we look at a galaxy that is, say, 10 billion light-years away, we are not seeing it as it looks now. We are seeing it as it looked 10 billion years ago. It's like looking into a cosmic time machine. If we see a galaxy that is 1 billion light-years away, then the light we are seeing left that galaxy 1 billion years ago, and we are witnessing what it looked like all the way back then. To look this far back in time, scientists use very powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope. These amazing tools can capture the faint light from galaxies that are billions of light-years away from Earth. They allow us to see what the universe looked like when it was still young and just beginning to form its first stars and galaxies. One of the most powerful tools for studying early galaxies is the James Webb Space Telescope, often called JWST. It was specially designed to look deep into space and far back in time. It can see infrared light, which is important because the light from distant galaxies gets stretched into longer, redder wavelengths as it travels across the expanding universe. JWST can pick up this ancient light, giving scientists incredibly clear views of galaxies as they looked more than 13 billion years ago. What JWST has shown us is surprising. Many of these early galaxies look far more irregular and chaotic than scientists had predicted. This discovery has challenged the old ideas about how galaxies form. Instead of slowly turning into neat, organized systems, it seems that many galaxies were born messy and stayed that way for a long time. But why were these early galaxies so messy and wild? One possible answer involves something mysterious and invisible: dark matter. Dark matter is a strange kind of matter that does not give off light or energy, so we can't see it with our eyes or telescopes. Yet, it makes up about 27% of everything in the universe. Scientists know it exists because it has a powerful gravitational pull. It tugs on the things we can see, like stars, galaxies, and even entire clusters of galaxies. In the early universe, dark matter wasn't spread out evenly. It formed dense blobs or clumps in different places. These clumps acted like giant magnets, pulling in gas and dust from their surroundings. This material then began to collapse under its own weight, forming new stars and over time entire galaxies. But because dark matter was clumped in random ways, the galaxies that formed around it didn't look smooth or regular. They were twisted and jumbled, still being shaped by the gravity of the dark matter. This may be why the earliest galaxies appear so strange. They were still under construction, shaped by invisible hands. Another reason early galaxies looked so unusual is that they were packed much closer together than galaxies are today. Back then, the universe was smaller and more crowded. Tiny galaxies floated near one another, and many of them crashed into each other. When galaxies collide, their stars usually don't crash into each other. There is just too much space between stars for that to happen. But the gas and dust inside the galaxies do crash, mix, and heat up. These cosmic crashes caused huge changes. The swirling clouds of gas and dust would get squeezed and heated, sparking the birth of new stars. Galaxies would get pulled into new shapes. Some would merge completely into bigger galaxies. Others would stretch, twist, or break apart. These violent events helped shape the galaxies into what we see today. Over time, this rough and chaotic dance gave rise to larger and more stable galaxies. But it all began in a time of cosmic turmoil. When the universe was still young, galaxies were still forming, and everything was changing rapidly. Even now, galaxies still collide and change, but it happens less often than it did in the early days. Back then, it was a regular part of the universe's wild and dramatic story of growth. Long ago, when the universe was still very young, only a few 100 million years after the Big Bang, galaxies looked and behaved very differently from the ones we see today. Back then, the early galaxies were filled with enormous amounts of gas, far more than the galaxies we see in the present. This gas was mostly made of hydrogen and helium, the two lightest and simplest elements in the universe. These gases were the main ingredients used to make new stars. Because there was so much gas flying around, early galaxies didn't have the neat and graceful shapes we often admire now, like spirals or smooth ellipses. Instead, they were wild and messy. The gas inside them was spread out unevenly, causing the galaxies to look lopsided, clumpy, and irregular. These young galaxies were like cosmic storms, turbulent, full of motion, and still trying to find their shape. Even the way stars were born in those early times was very different. In today's galaxies, like our own Milky Way, new stars usually form in special places, such as the spiral arms. These regions are organized and relatively calm, But in the early universe, star-making was much more chaotic. Stars could pop into existence almost anywhere inside a galaxy. Sometimes they were born in giant bursts, triggered by turbulence or by galaxies crashing into one another. This scattered and uncontrolled pattern of star formation gave early galaxies their clumpy and jumbled appearance. All of this happened because those galaxies were still in the process of growing up. Over billions of years, galaxies collided, merged, and matured. As this happened, they slowly began to form more organized shapes. Some turned into spiral galaxies with beautiful sweeping arms, while others became smooth and round, forming elliptical galaxies. By studying those early disorganized galaxies, astronomers can learn a lot about how galaxies grow and how the universe itself has changed over time. Deep in the center of almost every large galaxy, including our Milky Way, there lies something truly extraordinary: a supermassive black hole. These are unimaginably dense objects with gravity so strong that nothing, not even light, can escape once it gets too close. But black holes aren't just sitting quietly at the center of galaxies. They can actually shape the galaxies around them in powerful and surprising ways. Scientists believe that even in the earliest days of the universe, more than 13 billion years ago, supermassive black holes were already beginning to form in the hearts of young galaxies. Their intense gravitational pull could suck in huge amounts of gas, dust, and even entire stars. This powerful attraction didn't just affect the black hole's immediate surroundings, it could stir up the entire galaxy, making it even more chaotic. Stars might have been flung into odd orbits, and the whole galaxy could have become unstable. But black holes don't only pull things in, sometimes they explode with energy. As gas and dust spiral into a black hole, they heat up to extreme temperatures, creating enormous flashes of radiation. Some black holes even shoot out blazing jets of particles that travel at nearly the speed of light. These outbursts could punch through the surrounding space, pushing gas and dust away, and even stopping new stars from forming. In this way, black holes may have played a big role in shaping the strange and irregular shapes of early galaxies. Even now, scientists are still trying to fully understand how these cosmic giants influenced the early universe. But one thing is clear: supermassive black holes were not just silent observers, they were active, powerful forces that helped build the galaxies we see today. In the beginning, not long after the Big Bang, the universe was a wild and unruly place. Swirling clouds of gas, dust, and newborn stars filled the space, and galaxies looked nothing like they do today. Most of them didn't have smooth shapes or neat spiral arms. Instead, they looked like scattered clumps of stars and gas, without much structure at all. But over time, over billions and billions of years, something amazing happened. The invisible force of gravity began to pull everything together. Galaxies started to interact with one another, and sometimes they even crashed into each other. When two galaxies merged, their stars didn't usually collide because the space between them is so vast. But their gas and dust did interact, creating massive bursts of new stars. These galactic collisions, although violent and dramatic, actually helped galaxies settle down. The rough and messy shapes began to smooth out. Slowly, galaxies started to look more familiar. Some formed beautiful spiral arms like those of the Milky Way, while others became smooth and rounded like elliptical galaxies. Even today, this process isn't over. The universe is still changing. Galaxies continue to grow, merge, and reshape themselves. Our own Milky Way galaxy, for example, is heading toward a collision with the nearby Andromeda galaxy. This cosmic crash will happen in about 4 billion years. Eventually, the two will combine into one giant galaxy. This shows that the story of galaxy evolution is still being written. Recent discoveries have shocked scientists by showing that early galaxies were even more chaotic than anyone had guessed. These new findings are changing the way we understand galaxy formation. For a long time, scientists believed that galaxies slowly and steadily took shape over time. But now, we know the truth is much messier. The early universe was full of unpredictable and strangely shaped galaxies. Many of them looked like blobs or scattered collections of stars rather than anything structured. The forces that shape these galaxies are still not fully understood. The conditions back then were so different from today that researchers are still trying to figure out what exactly happened. Why were these galaxies so disorderly? What caused such wild bursts of star formation? These are questions that scientists are still working hard to answer. These strange early galaxies are like the universe's first building blocks. By studying them closely, scientists can trace the history of how galaxies grow, evolve, and change over time. Each clumpy, chaotic galaxy gives us a clue about how the universe went from a wild, swirling cloud of gas to the vast, structured cosmos we live in today. One of the most exciting and mind-blowing discoveries in modern astronomy is something scientists call the earliest light, a faint glow coming from galaxies that were born only about 200 to 300 million years after the Big Bang. Imagine that! This means we are looking at light that began its journey across space more than 13 billion years ago, giving us a rare and magical glimpse into the universe's very first chapter, a time when everything we now know was just beginning to form. Back then, the universe wasn't clear and open like it is now. It was filled with a dense, hot fog made of tiny particles. In this thick fog, light couldn't travel freely. The light particles, called photons, kept bumping into other particles, getting scattered in all directions. It was as if the whole universe was wrapped in a cosmic curtain that blocked any light from shining through. But over time, hundreds of thousands of years in fact, the universe slowly cooled down and expanded. As it did, the fog started to thin out. Finally, a turning point came when light was able to escape and travel freely across space. This incredible moment is known as the Cosmic Microwave Background, or CMB. It's a faint glow that still lingers in the universe today, a kind of baby picture of the cosmos that tells us what things looked like when it was very young. But even more fascinating is what happened a little later, between 200 and 300 million years after the Big Bang. That's when the first galaxies and stars began to form, and the first real starlight filled the universe. This starlight didn't just brighten up the sky, it completely changed the cosmos. Before this, the universe was a dark, foggy place, but the birth of these first galaxies and stars helped clear away the fog, allowing light to shine freely for the first time. This transformation is known as the Cosmic Dawn, the beginning of a new era when the universe started to glow with stars, galaxies, and beauty. What makes this discovery so important is that the light from these very early galaxies has been travelling toward us for over 13 billion years. That's an unimaginable distance, and yet we can detect this ancient light today, like a whisper from the distant past. This light holds incredible secrets. It tells us about the moment when the universe started to build structure, when stars, galaxies, and eventually planets began to take shape out of the chaos of the early cosmos. Scientists had always believed that galaxies began forming this early, but proving it was extremely difficult. The problem is that the farther away a galaxy is, the longer its light takes to reach us. And since these galaxies formed so long ago, their light is incredibly faint by the time it gets to Earth. Also, as the universe keeps expanding, the light gets stretched out along the way, moving from shorter wavelengths like ultraviolet and visible light into longer wavelengths, especially infrared. That makes the light invisible to our eyes. To see this stretched ancient light, scientists needed very special tools. They used incredibly advanced telescopes like NASA's James Webb Space Telescope, the Hubble Space Telescope, and some of the world's most powerful ground-based observatories. These telescopes are designed to detect infrared light, which our eyes cannot see. Thanks to these amazing instruments, astronomers were finally able to pick up the faint signals coming from the universe's earliest galaxies, signals that have been travelling across space for more than 13 billion years. One of the biggest challenges in finding this early light is the way the universe has been stretching ever since the Big Bang. As space stretches, the light travelling through it gets stretched too, so the light that was once bright and blue, like ultraviolet light, is now so stretched that it looks like infrared light, which is much redder and softer. This is why infrared telescopes are so important. The James Webb Space Telescope was specially built to look into this infrared range. It allows scientists to see things that were completely hidden before, things that happened shortly after the universe was born. This light is more than just beautiful. It's incredibly useful. It shows that galaxies and stars began forming much sooner than scientists once thought. That helps answer a big question. How fast did the universe start organising itself after the Big Bang? The answer is faster than expected. This early starlight proves that the universe didn't wait long to start creating, and this brings us to some of the most mysterious stars of all, known as Population 3 stars. These were the very first stars in the universe. They were nothing like the stars we see today. These ancient stars were made almost entirely of hydrogen and helium, the simplest and lightest elements created during the Big Bang. What made them unique is that they had no metals, nothing heavier than helium. Because of this, they burned much hotter and faster, shining brightly for only a short time before exploding in powerful supernovae. These stars helped shape the universe by sending out energy and spreading new elements into space. They also played a key role in a major event called ionization, which helped make the universe transparent, allowing light to travel freely across space. Studying this ancient light also helps scientists understand how galaxies were built. At first, the earliest galaxies were probably small and uneven, kind of messy compared to the massive, beautiful galaxies we see today. But over billions of years, these early galaxies crashed into one another, merged, and grew bigger and more complex. This process of growth and transformation eventually led to the creation of galaxies like our own Milky Way. The very first light that ever reached us from the ancient universe has a deep and mysterious connection to two of the strangest and most puzzling things in all of space: dark matter and dark energy. These two invisible forces are believed to make up almost all of the universe, much more than the stars, planets, and galaxies we can actually see. Yet, we still don't fully understand what they are or how they work. We can't see them with our eyes or even with the most powerful telescopes, but scientists know they're out there because of the strange effects they have on everything else in the universe. Dark matter is thought to act like a cosmic glue. It helps galaxies form and stay together, using its strong gravitational pull to gather stars and gas into clusters. Dark energy, on the other hand, seems to be the reason the universe is expanding faster and faster, pushing galaxies apart more quickly over time. These two invisible forces are shaping everything, but in secret. Now, here's where the first ancient light becomes incredibly important. This light, emitted from some of the earliest galaxies to ever exist, gives scientists a rare and powerful tool for peeking into the past. By studying this light, scientists can learn how dark matter affected the universe during its earliest moments. Although dark matter doesn't shine, glow, or reflect light, it does leave clues behind in the way galaxies moved and formed in those first billions of years. The light acts like a spotlight, revealing the hidden fingerprints of forces we cannot see. Every time we discover more of this ancient light, we are peeling back the layers of time. It's as if we are looking through a magical window into the distant past. This light began its journey billions of years ago, long before our solar system existed, even before the Earth was formed. When we observe it now, it's like watching a cosmic movie showing the birth and growth of the universe itself. One of the most breathtaking discoveries so far is the light coming from galaxies that formed only 200 to 300 million years after the Big Bang. Considering that the Big Bang happened about 13 billion and 800 million years ago, this means we're seeing light from a time when the universe was still very young, a newborn in cosmic terms. These early galaxies were just beginning to take shape, and their light has been travelling across space for almost the entire age of the universe to reach us today. And this is only the beginning of our journey into the past. Thanks to incredible advancements in technology, especially the powerful James Webb Space Telescope, we can now see farther and clearer than ever before. These new tools are opening up corners of the universe that were once completely hidden. With every new piece of ancient light we uncover, we gain new clues about how galaxies were built, how stars were born, and how the universe slowly transformed into the giant, beautiful place we live in today. But this search is not just about stars and galaxies, it's also about us, our story, our beginnings. As we keep learning about dark matter, dark energy, and the early days of the universe, we're also learning about our own place in the grand story of existence. The ancient light we study today helps us understand how everything we know, including our planet, our sun, and even life itself, came into being. Picture the universe just after the Big Bang, a moment when everything we know began. It was not calm or quiet. Instead, It was a wild and fiery place filled with blinding energy, scorching heat, and swirling particles racing in every direction. Time had just started ticking, and space itself was stretching and expanding at an unbelievable speed. In those first few heartbeats of existence, just fractions of a second after the Big Bang, something strange began to happen. The matter in the universe wasn't spread out evenly. Some parts had a little more stuff crammed into them than others. These small differences, though tiny, would change the course of everything. In the areas where matter was packed more tightly, gravity became stronger. And in some rare spots, this pull was so intense that space itself may have collapsed inward, creating what scientists call primordial black holes. These black holes are very different from the ones we usually hear about, the kind that form when giant stars burn out and die. Primordial black holes didn't come from stars at all. They may have been born directly out of the raw, chaotic energy of the early universe. They could have appeared in less than 1 second after the Big Bang, making them some of the very first objects ever to exist in the cosmos. Now, here's the really surprising part. Some of these black holes could have been incredibly small, maybe even as tiny as a single proton. That's unimaginably small, but despite their size, they could have been unbelievably powerful. Inside their tiny space, they might have held the mass of an entire mountain, or even a large asteroid. Some may have contained a mass close to that of a small planet like Earth. The reason this is possible is because black holes squeeze matter into an incredibly dense form. Imagine cramming something as big as a city, or even a planet, into a space no larger than a grain of sand. That's the kind of extreme density we're talking about. These mysterious black holes are called primordial because they may have been born before anything else, long before stars twinkled, before planets spun in orbit, and before galaxies formed their elegant shapes. Some of them may have vanished over billions of years through a strange process called Hawking radiation, where black holes slowly lose energy and fade away. But others, especially the larger ones, might still be out there, quietly drifting through space. Even though we can't see them, these ancient black holes could still be tugging on stars, bending light, or even passing through galaxies without being noticed. Some scientists believe that if these black holes exist in large enough numbers, they could explain one of the universe's greatest mysteries: dark matter. Dark matter is an invisible substance that makes up most of the mass in the universe. We can't see it, touch it, or shine a light on it, but we know it's there because of the way it affects the movement of galaxies and stars. Scientists have been searching for answers about dark matter for many decades, and primordial black holes might just be the key. If we can prove that these ancient black holes exist, it could unlock secrets about how the universe was formed and how it has grown over the past 13.8 billion years. It might even help us understand how gravity works on the most basic level. Let's go back to that chaotic beginning again. In the first tiny sliver of time, less than 1 second after the Big Bang, the universe was a thick, glowing soup of particles and energy. The temperature was unimaginably high. In this hot and crowded place, not everything was balanced. Some spots had just the right mix of density and pressure that gravity took over. These rare spots collapsed in on themselves, forming small but incredibly heavy black holes. They didn't need stars to be born. All they needed was the extreme environment of the newborn universe. When most people hear the term black hole, they usually think of a giant star that has collapsed under its own weight. These are called stellar black holes, and they form when massive stars, those several times heavier than our own sun, burn through all their fuel and collapse in on themselves. These cosmic monsters can weigh anywhere from a few times the mass of the sun to dozens of times more. But there's another kind of black hole that is far more mysterious and possibly much older. These are called primordial black holes, and they might have been born in the very first moments of the universe, right after the Big Bang, more than 13 billion years ago. Unlike stellar black holes, which come from dying stars, primordial black holes didn't come from stars at all. In fact, they may have formed before stars even existed. Scientists believe that in the chaotic and fiery newborn universe, everything was packed together tightly and swirling with incredible energy. Some tiny areas had more matter than others. These denser spots might have collapsed under their own gravity, instantly becoming black holes. And so, primordial black holes could have formed naturally from the raw energy of the early universe. What makes them even more fascinating is that they could be incredibly small. Some might be no bigger than a single atom. But don't let their size fool you. Even if one is that tiny, it could still hold an unbelievable amount of mass inside. That means they would be extremely dense, far more so than anything we can easily imagine. These ancient black holes may act very differently from the ones we usually study, and that's why scientists are so interested in them. Some even believe these tiny but powerful objects might help explain one of the biggest cosmic puzzles of all time: dark matter. Dark matter is a strange and invisible form of matter that we cannot see or touch, but we know it's there because it affects how galaxies move and how light bends around them. Scientists estimate that dark matter makes up about 85% of all the matter in the universe, yet no one has ever directly detected it. It's like a hidden force shaping the cosmos, quietly pulling the strings behind the scenes. Some researchers think that primordial black holes might actually be dark matter, or at least part of it. Because these ancient black holes would be tiny, dark, and scattered across space, they would be almost impossible to see. But they still have gravity, and gravity is something we can measure. If enough primordial black holes exist, their combined gravity could help explain the invisible pull of dark matter. And that's not all. If primordial black holes really did form right after the Big Bang, they could be scattered throughout the entire universe. Some scientists even believe there might be some floating around in our own galaxy, hiding in plain sight. They would be almost invisible, completely dark and too small to detect easily, but they might still leave subtle clues. Their presence could slightly bend the light from stars or affect the way objects move through space. Even though we haven't directly seen a primordial black hole yet, scientists are searching for evidence in several exciting ways. One method involves studying gravitational waves. These are like ripples in the fabric of space and time, created when massive objects like black holes crash into each other. Over the past few years, scientists have detected several of these waves, and some of them might have come from collisions between primordial black holes. If more of these mysterious waves are found coming from unexpected sources, it could be a big clue that these ancient black holes are out there. Another way researchers search for signs of primordial black holes is by studying something called the Cosmic Microwave Background, or CMB for short. This is a faint glow left over from the Big Bang, still drifting through space almost 14 billion years later. If tiny black holes had formed in those early moments, they might have disturbed this ancient radiation. These disturbances could leave behind special patterns or fingerprints that we might be able to detect with powerful telescopes. Primordial black holes aren't just interesting because they're old or small, they could actually help us answer some of the deepest questions in all of science. They might tell us what the universe was like in its very first seconds, when time itself was just beginning to tick. They might help explain how everything, from stars and planets to light and matter, came to be. Even more exciting, these mysterious black holes could help scientists unite two of the most important ideas in physics: Einstein's theory of general relativity, which explains how gravity works and how massive objects bend space and time, and quantum physics, which explains how the tiniest particles behave. These two theories don't always get along, and scientists have been trying for many years to find a way to connect them. Some believe that studying primordial black holes could be the key to building a theory of everything, a single set of rules that explains how the entire universe works, from the smallest atoms to the largest galaxies. Primordial black holes are like ancient ghosts, whispering secrets from a time before stars, before planets, and even before light itself. They may be the oldest things in the universe, formed when everything was still wild, hot, and new. And although they remain one of the greatest cosmic mysteries, each new discovery brings us one step closer to understanding where we came from, and what might be hidden out there in the dark. These extremely old black holes are believed to have formed during the very first moments after the Big Bang, which happened around 13,800 billion years ago. Scientists think they might be hiding important clues about how galaxies were born, the strange and invisible material called dark matter, and the hidden forces that help shape the entire universe. As our telescopes become more powerful, satellites more advanced, and scientific tools more accurate, researchers are hopeful that they will find more signs of these ancient black holes. If they do, it could bring us much closer to finally understanding whether these so-called primordial black holes are real, and what role they may have played in building the universe we live in today. The universe is so huge that it's hard to even imagine its size, and even with all the amazing discoveries made so far, there is still an enormous amount we don't understand. One of the biggest mysteries is the possible existence of primordial black holes. These are not the usual black holes that form when stars die. Instead, they might have appeared right at the beginning of everything, within the first tiny moments after the Big Bang. These ancient black holes are completely invisible, which makes them even harder to study. But they are incredibly important, because they might help us understand how the universe itself began. If scientists can learn more about them, it could help solve some of the greatest cosmic puzzles. That's why many researchers are so excited about the search for primordial black holes. To them, these hidden objects represent one of the most exciting and mysterious areas of modern science, an adventure that could finally explain how our vast and beautiful universe came to be. When we gaze into the night sky with powerful telescopes, we're not just looking at distant stars and galaxies, we're actually looking back in time. This might sound like something from a science fiction movie, but it's one of the most incredible truths about the way light travels through space. Light doesn't move instantly. It travels at a set speed, about 186,000 miles every second. That's incredibly fast, but space is so enormous that even light can take a very long time to reach us. When we look at the most faraway galaxies, the light we see from them began its journey millions, or even billions of years ago. So we're not seeing them as they are now. We're seeing them as they looked a long, long time ago, sometimes when the universe was still in its earlier stages. As scientists study these ancient galaxies, they've made a discovery that is shaking the very foundations of what we thought we knew about the universe. Inside some of these early galaxies, they've found something astonishing: supermassive black holes. These are enormous, mysterious objects with gravity so strong that nothing, not even light, can escape them. What's so surprising is not just that these black holes exist, but how quickly they seem to have formed. According to the best scientific models we have, black holes usually start off small, forming when a giant star dies and collapses. After that, they grow very slowly over millions or even billions of years, gradually swallowing up gas, dust, and even entire stars. But the supermassive black holes found in these ancient galaxies were already gigantic when the universe was still very young. That means they somehow grew incredibly fast, much faster than science currently says should be possible. Normally, black holes take a very long time to grow this big. It's a slow process, like a snowball rolling down a hill gradually gathering more snow, but these black holes seem to have skipped the slow part entirely. They were already massive, like finished skyscrapers, at a time when the universe was just beginning to build its first bricks. Some scientists think that something very special may have happened in the early universe. Maybe a strange process allowed black holes to grow much faster than they do today. Others suggest an even more mysterious idea. Maybe some black holes were born in a completely different way. Instead of coming from dying stars, they might have formed from gigantic clouds of gas that collapsed straight into black holes. Before diving deeper into this cosmic mystery, let's take a moment to understand what a supermassive black hole actually is. Simply put, a black hole is a spot in space where gravity is so powerful that nothing can escape it. Not even light, the fastest thing in the entire universe. Once something passes the black hole's invisible boundary, called the event horizon, it's pulled in forever and disappears from view. Black holes come in different sizes. Some are small, formed when huge stars explode at the end of their lives. But then there are supermassive black holes, giants that make even large stars look tiny. These can be millions or even billions of times heavier than our sun. Imagine crushing the weight of an entire galaxy into a single point. That's how powerful these supermassive black holes are. These enormous objects don't just float around randomly in space. They are found right at the centers of galaxies, including our own galaxy, the Milky Way. It's as if they're the silent rulers of their galaxies, using their invisible strength to shape everything around them. Scientists believe they play a key role in how galaxies grow and change over time. Supermassive black holes affect the movement of stars, the gathering of gas clouds, and even how new stars are born. Sometimes they release huge bursts of energy, powerful jets that shoot across vast stretches of space, changing the shape of entire galaxies. In our own Milky Way, scientists have found a supermassive black hole called Sagittarius A, sitting at the very heart of our galaxy. Even though we can't see it directly, we know it's there because of the way stars near it move. They spin around it at incredible speeds, like they're caught in a cosmic whirlpool. Despite their name, black holes aren't just empty spaces. They're among the most powerful and active forces in the universe, shaping it over billions of years. In fact, some scientists think that without supermassive black holes, galaxies might never have formed the way we see them today. Now, back to the mystery. Scientists believe that black holes start small, known as stellar mass black holes. These form when massive stars explode in events called supernovae. What's left behind is a core so dense that it collapses into a black hole. Over billions of years, that small black hole can grow bigger by pulling in everything around it: gas, dust, and even other stars. Eventually, with enough time and matter, it might grow into a supermassive black hole. But here's the shocking part. When astronomers look deep into space, which also means looking far back in time, they've found fully grown supermassive black holes in galaxies that existed less than 1 billion years after the Big Bang. This is a huge puzzle. The Big Bang, which created the universe, happened around 13.8 billion years ago. That means these gigantic black holes already existed when the universe was less than 1 billion years old. Still just a baby in cosmic terms. It's like walking into a nursery and finding a full-grown adult sitting in a crib. According to everything we understand about black holes, there simply wasn't enough time for them to grow so massive so fast. This discovery has left scientists both amazed and confused. It's forcing them to ask some very deep questions about whether we really understand how black holes grow. According to standard physics, black holes should form after massive stars die and collapse. These small black holes then grow bigger by merging with other black holes and feeding on gas and dust around them. A slow and steady process. But the black holes found in these ancient galaxies seem to have skipped all of that. They were already enormous when the universe was still very young. This brings us to one of the biggest mysteries in modern astronomy. How did these black holes grow so fast? Some scientists now believe that in the early universe something very unusual might have happened. Maybe some black holes formed directly from massive clouds of gas, skipping the star-forming stage completely. Others think these could be primordial black holes that were born in the first few moments after the Big Bang itself. If that's true, it would mean black holes have been around since the very beginning of time. And if that's the case, then we may need to rethink everything we thought we knew about the history of the universe. One of the most puzzling and surprising discoveries in modern astronomy is the existence of supermassive black holes in the early universe. These gigantic cosmic objects, some weighing millions to billions of times more than our Sun, were already present just a few 100 million years after the Big Bang, which happened nearly 14 billion years ago. This doesn't make sense based on what scientists currently understand. Normally, black holes start off small, forming when huge stars explode and collapse under their own gravity. After that, they grow slowly over billions of years by swallowing nearby gas, dust, and even entire stars. But in this case, some black holes were already fully grown giants, while the universe itself was still a baby. It's like planting a seed and finding a massive tree just a few days later. Something about it just doesn't add up. At the time these black holes were found, the first galaxies were only just beginning to take shape. Stars were still being born and there wasn't much material around for black holes to feed on. If black holes grow by eating the stuff around them, how could they have become so large so quickly when there was hardly anything there to consume? This strange discovery suggests that our current theories about how black holes form and grow might be missing something important. There could be a hidden process at work, something we haven't discovered yet, that allowed these ancient black holes to grow at lightning speed. To solve this mystery, scientists have come up with some fascinating ideas. One theory says that these black holes didn't start from stars at all. Instead, huge clouds of gas, some of them hundreds of thousands, or even millions of times more massive than the Sun, might have collapsed directly into black holes. This would mean they skipped the usual step of turning into stars first. By starting off big, These black holes wouldn't need as much time to grow into giants. Another idea is based on something called the Eddington limit. This is a kind of speed limit for how fast black holes can grow. As they pull in matter, they also give off a lot of radiation, which pushes outward and slows down how much more they can pull in. But some scientists think that, under very special conditions, black holes in the early universe might have broken this limit, allowing them to grow far faster than we thought was possible. There's also a theory about something called primordial black holes. These are black holes that might have formed right after the Big Bang, not from stars, but from the intense energy and pressure in the universe's first moments. If these black holes started off big, they would have had a major head start, allowing them to grow into supermassive black holes much earlier than usual, like joining a marathon halfway through and reaching the finish line before everyone else. Yet another idea suggests that black holes might have formed in groups, not one by one. These small black holes could have clumped together and merged with each other in the chaotic early universe. With so many collisions happening, they could have quickly grown into much larger black holes. In a short time, a bunch of tiny ones could have turned into a single, gigantic, supermassive black hole. But maybe the biggest surprise of all is that these early supermassive black holes might be telling us something entirely new about the universe, something we don't yet understand. Some scientists believe these black holes could lead to revolutionary discoveries in physics, like finding unknown forces or brand new types of matter that help black holes grow. These discoveries might even force us to rewrite some of the basic rules that we've believed for centuries. To solve this cosmic mystery, scientists are turning to one of the most advanced tools ever built, the James Webb Space Telescope, also known as JWST. This powerful telescope can see incredibly far into space, capturing light that's taken over 13 billion years to reach us. With each image, scientists are peering deep into the universe's past, back to the time when the first galaxies and black holes were forming. By studying these ancient galaxies and the supermassive black holes at their centres, astronomers hope to uncover the secrets of how such enormous objects appeared so early in the history of the universe. Every discovery brings us one step closer to solving this cosmic riddle. For thousands of years, human beings have looked up at the night sky with wonder, curiosity, and countless questions. They stared at the stars and asked themselves, is Earth the only place in this vast universe where life exists? The twinkling lights in the sky have always sparked the imagination, filling people's minds with dreams of other worlds. With billions upon billions of stars scattered across the endless cosmos, many began to believe that at least some of these stars might have planets like Earth, places where life could also thrive. For most of human history, though, this was only a dream. People imagined other Earths, but there was no proof. Scientists, stargazers, and dreamers kept searching and hoping, but they had no way to truly see what was out there. That all began to change in the last few decades of the 20th century. Thanks to powerful new telescopes and daring space missions, scientists have now discovered thousands of planets that orbit stars far beyond our own sun. These planets are called exoplanets, and their discovery has completely changed how we see the universe and our place in it. Some of these exoplanets might even have the right ingredients for life. While only a small number of them seem to have Earth-like conditions, each new discovery brings us one step closer to answering one of the greatest questions ever asked. Are we alone in the universe? Exoplanets are planets that orbit stars outside of our solar system. Some of them are rocky like Earth and might have oceans, atmospheres, or even temperatures that could support life. Others are massive gas giants like Jupiter, or strange worlds that defy what we thought was possible. Astronomers have found exoplanets in places and forms that are completely unexpected. Some are frozen in eternal winter, covered in thick sheets of ice. Others are blazing hot with entire oceans made of melted rock. There are even planets where it rains liquid metal, as the extreme heat in their skies turns iron into droplets that fall like fiery rain from the clouds. The very first confirmed discovery of exoplanets happened in the year 1992. These early planets were found orbiting a pulsar, a dead, collapsed star that shoots out beams of radiation like a cosmic lighthouse. These planets were incredibly strange and showed that worlds could form even in the most unexpected corners of the universe. Then, In the year 1995, astronomers found a planet named 51 Pegasi b. This was the first exoplanet discovered around a star similar to our Sun. It was a gas giant, much like Jupiter, and its discovery proved that planets orbiting stars like our own are real. That single discovery opened the floodgates for a whole new era of exploration. Since then, scientists have confirmed the existence of more than 5,005 exoplanets, and that number continues to grow rapidly. New discoveries are being made all the time, especially with the help of advanced space telescopes like the James Webb Space Telescope. This powerful instrument is not only spotting new planets, but also studying the gases in their atmospheres, looking for signs of life and unlocking the secrets of worlds far beyond our solar system. But not all exoplanets are alike. Scientists group them into different types based on things like size, materials, and how close they are to their stars. One of the most important groups is the gas giants. Gas giants are huge planets, much bigger than Earth. Two well-known examples in our own solar system are Jupiter and Saturn. These giants are mostly made up of hydrogen and helium, two gases that are lighter than air. Because of their size and brightness, gas giants are easier to spot in space and are often among the first planets scientists find when observing distant star systems. To get an idea of just how big they are, consider this. More than 1,300 Earths could fit inside Jupiter. These planets don't have a solid ground like Earth. Instead, they are wrapped in thick clouds of gas. As you go deeper into the planet, the gas becomes heavier and hotter. In the deepest parts, the pressure is so intense that even hydrogen, which is usually a gas, turns into a strange liquid form. Scientists think there might be a solid core at the very center, but no one knows for sure because we can't send spacecraft deep enough to find out. We know a lot about gas giants like Jupiter and Saturn because they shine brightly in our sky and have been studied by telescopes and space probes for many years. These planets also give off more energy than they receive from the Sun, which makes them stand out even more in space. Gas giants are not rare. In fact, most of the exoplanets discovered so far are gas giants. One big reason for this is that they are easier to detect. When a gas giant passes in front of its star, it causes a slight dimming of the star's light, something known as a transit. These dips in brightness allow astronomers to notice and study the planet, even if it's located trillions of miles away. Some gas giants found outside our solar system are even more extreme than Jupiter. For example, there are hot Jupiters, which orbit their stars very closely and have incredibly high temperatures. Then there are ice giants like Uranus and Neptune, which, while still mostly gas, contain more water, ammonia and methane, chemicals that make them different from Jupiter and Saturn. The discovery of so many gas giants has raised many fascinating questions. How do these giant planets form? How different can they be from one another? And is it even possible for life to exist on or around one of them? Perhaps on a moon that orbits a gas giant like Jupiter's icy moon Europa? Although gas giants seem too harsh and wild to support life as we know it, studying them helps us understand the building blocks of planets, how solar systems are formed, and what other types of worlds might be waiting out there in the great unknown. Each gas giant we discover adds a new piece to the cosmic puzzle, bringing us closer to understanding the incredible diversity of planets in the universe, and maybe, just maybe, bringing us closer to discovering life beyond Earth. Secondly, let's explore the amazing Neptune-like planets, fascinating worlds that are similar in many ways to the distant planets Uranus and Neptune, which both live far out in the cold reaches of our solar system. These types of planets are often called mini-Neptunes, because like Neptune and Uranus, they are mostly made up of gases rather than solid rock or metal. However, unlike the giant gas planets such as Jupiter and Saturn, mini-Neptunes are much smaller in size. To truly understand what mini-Neptunes are, it helps to look at their bigger relatives. Neptune and Uranus are both famous for their thick, swirling atmospheres filled with gases like hydrogen, helium and methane. This special mix of gases gives them their beautiful bluish colour and also leads to incredibly strong winds and violent storms. They're also known as ice giants because their atmospheres and inner layers contain frozen substances like water, ammonia and methane, making them not just gas worlds but icy ones too. Mini-Neptunes, while smaller, share many of these traits. Unlike Jupiter, the biggest planet in our solar system, which is a gigantic ball of gas. Mini Neptunes are much less massive. Their smaller size means they can still have thick, fluffy atmospheres made mostly of hydrogen and helium, but they don't have the super dense cores that big gas giants do. Because of this, their atmospheres are lighter and thinner, though still made mostly of gas. One of the most interesting things about mini Neptunes is that they usually don't have a solid surface like Earth or Mars. Instead, they are made up of layers of gas and ice. Some of them might have a rocky core buried deep inside, but it's hard for scientists to study these cores directly because of the thick gases that cover them. In fact, some mini Neptunes have been found with cloudy skies, powerful winds and stormy weather that make them look like smaller versions of Neptune or Uranus. Astronomers are especially fascinated by these Neptune-like planets because they appear to be quite common around other stars. So far, thousands of planets have been found outside our solar system. These are called exoplanets, and many of them fall into the mini Neptune category. Some studies even suggest that mini Neptunes could be one of the most widespread types of planets in our entire galaxy. What makes them even more exciting is how different each one can be. Some mini Neptunes have thick clouds that trap heat, making them incredibly hot on the inside. Others may have lighter atmospheres mixed with different ices and gases, leading to unique weather patterns and wild storms unlike anything we see on Earth. Even though they look like Neptune, these planets are different in other ways too. Because they are smaller, they might not have the strong magnetic fields or giant storms that their larger cousins do. But they can still be very active, with mysterious weather systems and maybe even oceans hidden deep beneath their clouds. Studying these strange worlds gives scientists valuable clues about how planets form and change over time. Every new discovery helps us understand more about our universe and raises new questions about what might be possible on other planets. As our technology continues to improve, we may soon be able to take a much closer look at these mysterious worlds. Future space missions could send robotic spacecraft to explore planets like these in detail, helping us unlock their secrets and learn even more about what kinds of worlds exist beyond our solar system. Now let's move on to another exciting group of planets, super-Earths. These are planets that are larger than Earth but smaller than Neptune. They don't get as big as the huge gas giants like Jupiter or Neptune, but they are still quite a bit bigger than our own planet. The term super-Earth simply refers to how large and heavy they are. It doesn't mean they're exactly like Earth, or that they can support life. Some super-Earths may have solid surfaces made of rock just like Earth. Others might be wrapped in thick blankets of gas or covered in icy layers. What makes them especially exciting is that some of them could have the right conditions for life. Scientists believe that if a super-Earth is at just the right distance from its star, not too hot and not too cold, there might be liquid water on its surface. And since water is necessary for life as we know it, these planets could possibly host living things, from tiny microbes to more complex creatures. Another fascinating thing about super-Earths is their gravity. Because they are more massive than Earth, their gravity would be much stronger. If a person stood on one, they would feel much heavier and find it harder to walk or jump. But this stronger gravity could also help hold on to a thick atmosphere, which would protect the surface from dangerous space radiation, something important for life to survive. Super-Earths come in many forms. Some might be ocean worlds, with water stretching from one side of the planet to the other. Others could have thick clouds and hot atmospheres, more like the planet Venus. Some may be rich in valuable minerals or contain chemicals that don't exist anywhere on Earth. Because they are so large, super-Earths might also have very active insides, with molten rock and even volcanoes. This volcanic activity could help create and maintain a stable atmosphere by releasing gases over millions of years. And if they have magnetic fields like Earth does, these planets could be protected from harmful solar winds, making them even more Earth-like and possibly friendly to life. Astronomers have already found many super-Earths around distant stars. Thanks to powerful new telescopes, we can now study them more closely than ever. Some famous examples such as Kepler 22b and TOI 700d have made headlines because they appear to be in what scientists call the habitable zone. This is the sweet spot around a star where the temperature is just right for liquid water to exist. In our solar system, there are 4 special planets known as terrestrial planets. These are Earth, Mars, Venus, and Mercury. What makes them stand out is that they are made mostly of solid rock and metal. They have strong, firm surfaces that you could actually stand on, unlike the big gas planets like Jupiter and Saturn. Those gas giants are mostly made of gas and don't have any solid ground beneath their clouds, so if you tried to land on them, you'd just sink. Because of their solid surfaces, terrestrial planets are especially interesting to scientists who are trying to find out whether other planets could support life. These rocky worlds may hold the key to discovering life beyond Earth. Earth is the most famous of all the terrestrial planets. Why? Because it's the only one we know for sure that has life on it. People, animals, plants, bacteria, everything we know that lives is right here. That's why scientists are always eager to find other planets that might be like Earth. They want to know, could there be another planet out there where life has taken root? This curiosity makes Mars, Venus, and Mercury especially fascinating to space explorers. Take Mars, for example. Often called the Red Planet, it has a dusty, rocky surface and shows signs that long ago, rivers and lakes may have flowed there. Some scientists think that billions of years ago, Mars might have had the right conditions for life. That's why space agencies like NASA have sent several robotic rovers, like Curiosity, Perseverance, and others, to drive around its surface, take pictures, dig into the soil, and search for any clues that life might have once existed there. Then there's Venus, which is sometimes called Earth's twin. That's because it's about the same size as Earth and made of similar materials. But don't let the nickname fool you. Venus is a very dangerous place. Its surface is extremely hot, even hotter than an oven, and it's covered in thick clouds filled with poisonous gases. Even though it's so different from Earth, scientists are still very curious about Venus. Studying it might help us understand how planets change over time, and why Venus became so harsh, while Earth remained a place full of life. Mercury, the smallest of the terrestrial planets, is closest to the Sun. Because of that, it has some of the most extreme temperatures in the solar system. During the day, Mercury gets so hot it could melt lead, but at night, without any atmosphere to keep the heat in, it becomes colder than an icy desert. Scientists are interested in Mercury because its surface is covered with craters from space rocks, and it gives us a good chance to study what happens when a planet doesn't have an atmosphere to protect it. What all these rocky planets have in common is that they have solid ground. That makes them different from the gas giants, and important for scientists searching for planets beyond our solar system, called exoplanets. Experts are especially interested in finding rocky exoplanets that lie in a special part of space called the habitable zone. The habitable zone is often called the Goldilocks zone, a term that comes from the famous fairy tale, where Goldilocks liked things that were not too hot, not too cold, but just right. In space, this zone is the area around a star where a planet is the right distance to have liquid water on its surface. Not frozen water, not steam, liquid water, like the kind we drink, swim in, and use for farming. This is very important because all living things on Earth, whether tiny microbes or large animals, depend on liquid water to survive. If a planet is too close to its star, like Venus, it gets way too hot. Any water would quickly boil away and vanish. It would be like standing next to a giant campfire. You'd burn up. On the other hand, if a planet is too far away, like Mars, it gets too cold. Any water would freeze solid, turning the planet into an icy wasteland. But Earth sits in that perfect middle ground. It's not too close and not too far from the Sun. This allows lakes, rivers, oceans, and even clouds to form and thrive, creating an environment where life can grow. This perfect distance from the Sun is one of the reasons Earth is so special. It allows water to move freely, and that water supports countless forms of life, from fish in the sea to birds in the sky, and of course, people. But distance alone isn't enough. A planet also needs a protective atmosphere. Think of a planet's atmosphere like a cozy invisible blanket wrapped around it. This blanket helps trap some of the sun's warmth and protects the planet from harmful space radiation and meteors. Without an atmosphere, a planet's temperature could swing wildly from freezing cold at night to burning hot during the day. That would make it very hard for life to survive. Earth's atmosphere is made up of many different gases. One of the most important is oxygen, which we breathe in every second to stay alive. Another important gas is carbon dioxide. Even though we only need a tiny amount of it, it plays a big role. It helps keep Earth warm by trapping heat. This is called the greenhouse effect. If we didn't have enough carbon dioxide, Earth could become too cold, but if there's too much, it could become dangerously hot. So, it's all about balance. Let's start by thinking about the Moon. Unlike Earth, the Moon does not have an atmosphere at all. This means there's no air to breathe, no clouds in the sky, and no protection from the harsh environment of space. Because of this, the temperatures on the Moon swing wildly between extremes. When the sun shines on the Moon during the day, it becomes scorching hot, reaching over 250 degrees Fahrenheit. But once the sun goes down and night falls, the temperature drops to an icy cold -280 degrees Fahrenheit. There's nothing to hold in the heat, and nothing to block the sun's harmful rays. Without an atmosphere, the Moon is completely exposed. It's a beautiful place to look at from Earth, but it's not somewhere life could survive. Now let's take a look at Venus. Venus is very different from both the Moon and Earth. Instead of having no atmosphere, it has one that's far too thick. This thick blanket of gas is made mostly of carbon dioxide, a gas that traps heat very efficiently. Because of this, Venus has something scientists call a runaway greenhouse effect. In simple terms, this means heat keeps building up and doesn't escape. As a result, the surface of Venus gets unimaginably hot, around 900 degrees Fahrenheit. That's hotter than the inside of a regular kitchen oven set to its highest temperature. And on top of that, the air on Venus is full of poisonous gases. With deadly heat and toxic air, Venus is one of the most dangerous places in the solar system. Nothing we know of could live there. This shows how important an atmosphere is. For a planet to support life, it needs an atmosphere with the right mix of gases. The atmosphere has to trap just enough heat to keep the planet warm, but not too much. It also needs to block dangerous radiation from space. If a planet has too thin an atmosphere, it will freeze. If the atmosphere is too thick, it will bake. Earth is special because it has the perfect balance. It's just right, not too hot, not too cold, and safe for living things. But there's another invisible hero that protects life on Earth: our planet's magnetic field. Think of it as a giant invisible shield that wraps around the Earth. This shield defends us from harmful energy that constantly pours out from the sun. This energy is called solar radiation, and without the magnetic field, it would hit Earth directly. Over time, it could even strip away our precious atmosphere, leaving us completely unprotected. Why is that so serious? Because our atmosphere does more than just hold in air. It gives us the oxygen we breathe and the nitrogen that helps keep everything in balance. It also acts like a blanket, keeping Earth's temperature steady and comfortable. If solar radiation were allowed to hit Earth without any defense, it would slowly tear the atmosphere away. Without air to breathe, without protection from the heat of the sun, Earth would become a lifeless, frozen world. Now let's turn our attention to Mars. Long ago, Mars may have had a magnetic field like Earth's, but at some point, it disappeared. Once Mars lost this protective shield, the sun's radiation started attacking its atmosphere. This didn't happen overnight, it took millions of years, but eventually much of the Martian atmosphere was blown away into space. Today Mars has only a thin layer of air, far too weak to trap heat or keep the surface safe from radiation. That's why the planet is now dry, cold, and empty. No oceans, no forests, and no signs of life. But there's something fascinating about Mars. Scientists believe it may once have looked more like Earth. It might have had a thick atmosphere, flowing rivers, and even shallow seas. Some think it may have had the right conditions for life to begin. But with no magnetic field to protect it, Mars couldn't hold on to these things. The sun stripped it bare. Today, it stands as a dusty, frozen reminder of what can happen when a planet loses its shield. This makes Earth's magnetic field even more important. It's not just a random feature, it's one of the key reasons why life is possible here. Without it, our world could have ended up just like Mars, cold, dead, and lifeless. Now let's talk about another ingredient that's crucial for life: water. Specifically, liquid water. Just being in the habitable zone isn't enough. This zone is the area around a star where a planet isn't too hot or too cold for water to exist. But even if a planet is in the right spot, it still needs water in the right form. Water in liquid form is incredibly important. It's the perfect place for the chemical reactions that life needs to begin and survive. Ice or water vapor isn't good enough. Life as we know it depends on having oceans, rivers, lakes, or even underground water flowing beneath the surface. Think about Earth. Our planet is full of life, and one big reason is because we have so much liquid water. The oceans cover most of Earth's surface. Without them, life would have a much harder time surviving. That's why, when scientists look for other worlds that might have life, the first thing they look for is signs of water. But finding water on other planets is not easy. Scientists use huge telescopes and advanced tools to look for tiny clues. They study the light from distant planets to see what kinds of gases are in their atmospheres. They look for temperatures that are not too hot or too cold, just right to keep water from freezing or boiling away. It's a tricky job, but finding liquid water gives us the best hope of discovering life beyond Earth. However, there's something else that matters when it comes to supporting life: the kind of star a planet orbits. Stars come in many sizes and temperatures, and that makes a big difference. Some stars are much bigger than our Sun. These stars are incredibly hot and bright, but they burn through their fuel very quickly. They live fast and die young, sometimes in just a few million years. That doesn't give planets orbiting them enough time for life to grow and evolve. The heat and radiation from these stars can also make conditions too harsh for life to survive. On the other end, there are smaller stars that are cooler and dimmer than the Sun. These stars live much longer, sometimes for tens of billions of years. But because they're not as hot, their planets have to be much closer to get enough warmth. If a planet is even a little too far away, it could be too cold for water to stay liquid. The best stars for life are the ones that are just right, like our Sun. Stars like the Sun are stable, warm, and live for billions of years. They shine steadily and give planets plenty of time to develop and support life. These stars offer the kind of balance that life needs. Even stars that are a little smaller than the Sun, called K-dwarfs, are good candidates. These stars burn their fuel slowly and shine for an incredibly long time, sometimes up to 40 or even 50 billion years. That's much longer than the Sun will last, and even though they're a bit cooler, they can still provide the right conditions for life on nearby planets. Exoplanets are planets that orbit stars far beyond our own solar system. These mysterious worlds can be millions or even billions of miles away from Earth. So far, in fact, that scientists cannot actually see most of them with their own eyes, not even through regular telescopes. But that doesn't stop them. Astronomers have come up with clever indirect ways to discover these distant planets. They study the light from faraway stars and how that light behaves. They also observe how stars move ever so slightly. With these techniques, they can uncover the hidden presence of planets that would otherwise remain invisible, giving us a peek into the vast and mysterious universe. One of the most popular ways scientists detect these hidden planets is called the transit method. Think of it like this. If you shine a flashlight and a tiny bug flies in front of the beam, you'll notice a brief shadow. That's exactly what happens on a cosmic scale when a planet passes in front of its star. Here's how it works. Scientists carefully watch a distant star, which could be located hundreds or even thousands of light years away from Earth. 1 light year is the distance light travels in a single year, about 6 trillion miles. These stars shine brightly, and when a planet moves across the face of the star from our point of view, it blocks a small bit of the star's light. This causes the star's brightness to dip slightly. The change is so tiny that you wouldn't notice it just by looking, but special instruments can measure it. This dip in brightness happens regularly, depending on how often the planet orbits the star. The amount of light the planet blocks tells scientists about the planet's size. The bigger the planet, the more light it blocks. By watching these dimming patterns over time, astronomers can tell that something is moving in front of the star, and that something is usually a planet. This clever method doesn't just help them find planets, it also gives clues about how big the planet is, how long it takes to orbit its star, and even if the planet might be in what's called the habitable zone, the perfect distance from the star where temperatures might be just right for life to exist. A special telescope called the Kepler Space Telescope, launched by NASA in the year 2009, used this method for many years. It kept its eye on more than 150,000 stars and discovered thousands of exoplanets. Thanks to Kepler, we now know that planets are extremely common in our galaxy, and some might even be similar to Earth. Another amazing method scientists use is called the radial velocity method, often nicknamed the wobble method. Here's the idea. When a planet orbits a star, its gravity tugs gently on the star. It's like a small child pulling on a parent's hand. The star doesn't stand perfectly still. It moves just a little, almost like a gentle wobble. This wobble is way too small for the human eye to see, but powerful scientific instruments can detect it. These instruments study the light coming from the star and notice tiny changes caused by something called the Doppler effect. You've probably noticed this effect when a car zooms by, and the sound changes as it moves, higher pitched as it approaches, lower pitched as it moves away. Light from stars does something similar. When a star moves toward us, its light shifts slightly to the blue side of the spectrum. When it moves away, the light shifts toward red. By measuring these color shifts, scientists can figure out that a planet is pulling on the star. Even if the planet is so far away that we'll never see it directly, this method lets scientists detect its presence. It can also tell them how heavy the planet is, how far it is from its star, and sometimes even what its orbit looks like. Over the years, this technique has helped discover hundreds, and possibly even thousands of exoplanets. It's like listening to the quiet footsteps of a hidden traveler walking through space. Sometimes scientists get lucky and are able to capture actual pictures of exoplanets. This rare and amazing technique is called direct imaging. But it's not easy. Stars are incredibly bright and the planets around them are much dimmer. Trying to take a picture of a planet next to a bright star is like trying to see a tiny candle flame next to a spotlight. To solve this, astronomers use special telescopes equipped with powerful technology that can block out the star's blinding light. This lets them focus on the much fainter light coming from the planet. It's like wearing sunglasses that help you see something small and dim next to something very bright. Direct imaging doesn't happen often, but when it does, it's a big deal. These rare images help scientists study a planet's size, color, and even its atmosphere. They can learn if the planet is rocky like Earth, icy like Neptune, or gassy like Jupiter. They can also look for signs that the planet might support life. Every time a new planet is photographed, it brings us one step closer to understanding the countless worlds that exist in the universe. Another incredible method used by scientists is called Gravitational Microlensing, and it sounds like something out of a science fiction movie, but it's very real and very powerful. Here's how it works. Gravity can bend light. So, when a massive object, like a star, passes in front of a more distant star, the gravity from the front star bends and magnifies the light from the one behind it. If there's a planet orbiting the front star, it can create a little extra blip in the brightness. This tiny flash of extra light is enough to tell scientists that a planet is there. This method doesn't require light from the planet at all. Instead, it relies on gravity and light from stars far behind it. That's why gravitational microlensing is so useful for finding planets that are way too distant or too faint for any other method. Even though it's rare and unpredictable, this technique can discover planets that no other method can. Some of the most distant and strange exoplanets we've found so far were detected this way. Imagine a lonely planet floating through the endless darkness of space. Far away, a distant star glows, sending out its light across billions of miles. Normally, the star's light travels in a straight line toward us here on Earth. But once in a while, something magical happens. If that wandering planet drifts directly in front of the star, it causes a surprising and powerful effect. Instead of just blocking the light, the planet's gravity bends it, like a magnifying glass bending sunlight. This bending makes the distant star look brighter, and sometimes even larger than it truly is. This strange effect happens because gravity isn't just a force, it also changes the very shape of space around it. That idea comes from Albert Einstein's famous theory of relativity. The heavier something is, like a planet, a star, or even a black hole, the more it pulls and twists the space around it. So, when a planet passes directly between us and a faraway star, its gravity slightly warps the light that's coming from the star. This warping creates a temporary brightening that we can see from Earth. Scientists call this amazing event gravitational microlensing. It doesn't last long, but it can reveal something we would never have seen otherwise. What makes gravitational microlensing so incredible is that it can uncover planets we can't see in any other way. Most planets are discovered by either watching how their light reflects, or by noticing how they gently tug on their parent stars with their gravity. But these usual methods don't always work, especially if the planet is very small or very far away from its star. Microlensing gives us a rare peek at these hidden worlds, even if they're light years beyond our reach. It's a bit like finding a hidden gem in the night sky. When that brief brightening happens, scientists on Earth quickly use powerful instruments to measure how much the star's light changes. From that tiny flicker, they can figure out amazing details: how big the planet is, where it is, and even how far it orbits from its star. But gravitational microlensing doesn't just help us find planets. It's also a way to discover other mysterious things in space, like black holes, neutron stars, or strange objects we still don't fully understand. Since many of the planets found using this method are located in distant corners of the galaxy or even the universe, this technique opens up a whole new way of exploring space. It lets astronomers reach farther than ever before, into places they once only dreamed of studying. Thanks to this and other advanced methods, astronomers have already discovered a number of fascinating exoplanets, planets that orbit stars outside our solar system. Some of these planets are especially exciting because they might have the right conditions to support life. Here are a few of the most promising examples. Proxima b. This planet orbits a star called Proxima Centauri, which is the closest star to our solar system. It lies just over 4 light-years away. Proxima b is located in what scientists call the habitable zone, the area around a star where the temperature might be just right for liquid water to exist. That's important, because water is essential for life as we know it. However, scientists are still trying to figure out whether Proxima b has an atmosphere strong enough to protect it and keep it livable. The TRAPPIST-1 system. About 40 light-years from Earth lies an extraordinary star system called TRAPPIST-1. This system contains 7 planets that are all roughly the same size as Earth. Even more exciting, 3 of these planets are in the habitable zone. If these planets have the right conditions, like water and an atmosphere, they could possibly support life. Because of this, TRAPPIST-1 has become one of the most closely watched systems in the universe. Kepler 442b. This planet, often called a super-Earth, is located around 1,200 light-years from Earth. It's larger than our planet, but it orbits within the habitable zone of its star. Scientists believe it might have the right temperature and possibly an atmosphere that could support life. That makes Kepler 442 one of the most interesting candidates for habitability. LHS 1140b. This rocky world lies about 40 light-years away from Earth. It has captured the interest of astronomers because it's believed to have a thick atmosphere and may even have liquid water on its surface. Its rocky terrain is similar to Earth's, making it another strong possibility in the hunt for alien life. One of the most mind-blowing and mysterious parts of our universe is something we cannot even see: dark matter. It's a strange, invisible kind of matter that acts like an invisible web, quietly holding the entire universe together. Even though we can't look at it with our eyes or take a picture of it with even the best telescopes, scientists are sure it exists. Why? Because of how it affects the things we can see, like stars and galaxies. Without dark matter, the way galaxies spin and move through space wouldn't make any sense at all. The universe would fall apart. Now, regular matter, the kind we're made of, the stuff that makes up stars, planets, and everything we can see, glows or reflects light. That's how telescopes pick it up. But dark matter is different. It doesn't shine. It doesn't reflect, absorb, or give off any kind of light or radiation. That's why scientists call it dark. Not because it's gloomy or shadowy, but because it's completely hidden. It's invisible, and yet its pull is powerful. Galaxies spin so quickly that the stars inside should be flying away into space, but they don't. Something invisible is pulling them inward, keeping them together. That something is dark matter, and it has been quietly shaping the universe since the beginning of time. To get an idea of how important dark matter really is, let's think of the universe as one gigantic puzzle. But here's the twist. Most of its pieces are completely invisible. Everything we can see, stars, planets, gas clouds, even people, makes up only about 5% of the entire universe. That means everything we've ever looked at in the night sky is just a small piece of the bigger picture. A much larger part, around 27%, is dark matter, the mysterious unseen substance that doesn't shine or glow. We can't see it directly, but it plays a huge role. It acts like a kind of invisible glue, holding galaxies together. Without it, galaxies like our own Milky Way wouldn't have their beautiful spiral shapes. Instead, stars would just drift apart, floating away into the emptiness of space. But that's not the end of the mystery. The biggest and strangest part of all is something even more puzzling: dark energy. This force makes up the remaining 68% of the universe, and instead of pulling things together like dark matter, dark energy is doing the exact opposite. It's pushing the universe apart faster and faster as time goes on. Scientists still don't know what dark energy really is, but they believe it's the force behind the universe's rapid expansion. So, when we step back and look at the big picture, we realize something astonishing. Most of the universe, more than 95%, is made up of things we can't see and don't fully understand. Yet, these invisible forces are shaping everything, from tiny atoms to giant galaxies that stretch across the cosmos. For many years, actually for more than 80 years, scientists have been chasing down the mystery of dark matter. They are convinced it's real, not because they've seen it, but because of the strange way galaxies behave. When astronomers study galaxies that are millions or even billions of light years away, they see that these galaxies are spinning too fast for the amount of visible matter they contain. According to all the laws of physics we know, they should fly apart. But something invisible is holding them together. That something is dark matter. To understand how dark matter helped shape the universe, we need to travel back to the very beginning, just moments after the Big Bang, which happened around 13.8 billion years ago. Back then, the universe was extremely hot and wild, filled with energy and tiny particles flying around in chaos. But as the universe began to cool down, dark matter started playing its part. It acted like an invisible scaffold or framework, pulling gas and dust into place and helping form the first stars and galaxies. Without it, the early universe might have stayed a chaotic mess. No galaxies, no stars, maybe even no life. Even though dark matter has played such an important role, we still don't know what it's made of. Scientists are trying to figure out if it's composed of particles we haven't discovered yet, or if it's connected to mysterious forces we haven't imagined. To solve this puzzle, researchers are using all kinds of amazing tools: gigantic detectors buried deep underground, particle colliders that smash atoms together, and powerful telescopes in space. Every experiment, every clue, brings us closer to finding the truth. But the mystery isn't solved just yet. Understanding dark matter isn't just about solving a science riddle. It could completely change the way we understand the universe. If we figure out what dark matter really is, we might also learn more about how the universe was born, how it grew, and maybe even discover new laws of physics that could change everything we thought we knew. Recently, scientists have made exciting progress, thanks to some of the most advanced technology ever built. Even though dark matter remains invisible, these discoveries are giving us better and better clues. One of the most important pieces of evidence comes from something called the cosmic microwave background, or CMB for short. This is a faint glow of energy that was left over from the Big Bang, like a baby picture of the universe. It's the oldest light we can see, dating back nearly 13.8 billion years. When scientists study this ancient light, they see tiny ripples, small patterns that show how matter started to clump together. And these patterns suggest that dark matter must have been there from the beginning, helping shape the first stars and galaxies. But how can dark matter do this if it can't be seen? The answer is gravity. Even though dark matter doesn't shine, its gravity still pulls on regular matter. It helped gather gas and dust into huge clumps, leading to the creation of stars, galaxies, and massive clusters. Without it, the universe might have stayed scattered and empty. Today, scientists are still hunting for ways to detect dark matter directly. They're not just looking at how it moves galaxies, but they're also trying to find particles or signals that might reveal its true nature. Every new discovery brings them a step closer to solving this epic mystery. In the early days, right after the Big Bang, The universe was like a giant storm of heat and energy. Everything was extremely hot, packed together tightly, and moving wildly in all directions. As it started to cool, things began to slow down and form more organized structures. But this transformation wasn't easy. Think of the early universe like a boiling soup, full of wild, swirling particles. Something had to help bring order to that chaos. That something was dark matter. Even though it was invisible, it was everywhere. And because of its strong gravity, dark matter started to clump together into huge invisible clouds. These clumps pulled in irregular matter, which helped form the very first galaxies and stars. Without dark matter's invisible hand guiding everything, the universe might never have taken shape the way it did. There would be no galaxies, no planets, no people. Dark matter was like a hidden blueprint, shaping the universe from behind the scenes. And now, billions of years later, scientists are still trying to read that blueprint and unlock its secrets. One of the most fascinating things about dark matter is how it forms something called dark matter halos. Imagine these halos as gigantic invisible clouds that gently surround galaxies like a protective bubble. They are not made of anything we can see, touch, or shine light on, but they are absolutely real. These halos help keep galaxies from flying apart. Without them, the stars in a galaxy would spin out into space and the galaxy itself would fall apart like a merry-go-round without a center pole. Scientists believe that every single galaxy in the universe, including our very own Milky Way, is surrounded by one of these mysterious halos. This idea was a major turning point in our understanding of the universe. It showed not just that dark matter is real, but that it plays a vital role in keeping galaxies together and in shaping the way they grow and move through space. In fact, without these dark matter halos, galaxies might not even exist the way we know them. One of the most important tools scientists use to find evidence of dark matter is a clever trick of nature called gravitational lensing. Here's how it works. When something incredibly heavy, like a galaxy or a big cluster of galaxies, sits between us and a more distant object, its gravity bends the light coming from behind it. This bending doesn't just change the direction of the light, it actually makes the object behind look brighter or distorted, like you're looking through a glass lens. This cosmic lensing effect is incredibly useful. It helps scientists see mass that is invisible, because dark matter, while unseen, still has gravity, and gravity bends light. By studying how the light is stretched and curved as it passes through space, researchers can map out where the dark matter must be. Time and again, they've discovered that there's way more mass in galaxy clusters than we can see with any telescope. That invisible mass is believed to be dark matter. So even though we can't directly observe dark matter, we know it's out there because it pulls on light in a very noticeable way. This light-bending effect has become one of the strongest clues that dark matter really exists. When light from distant galaxies passes through massive clusters of galaxies, the light gets bent, just like a beam shining through a magnifying glass. Scientists study these strange patterns of distorted light to figure out how much dark matter is present and where it's hiding. This has helped us draw much clearer pictures of how dark matter is spread across the universe. But that's not the only method researchers are using. They're also looking at something called the Cosmic Microwave Background, or CMB for short. This is the faint glow left over from the very first moments after the universe was born, about 13.8 billion years ago. By analysing tiny changes in this ancient light, scientists can find more clues about how dark matter influenced the early universe. Even though gravitational lensing and the CMB give us strong hints, scientists are still chasing the ultimate prize, discovering the actual particles that make up dark matter. According to one theory, dark matter might be made of special particles called WIMPs, which stands for Weakly Interacting Massive Particles. These particles are believed to be incredibly shy. They barely interact with regular matter at all, which makes them extremely hard to find. To try to catch one of these elusive WIMPs, scientists have set up some amazing experiments. Some of these detectors are buried deep underground, in quiet places where nothing else can interfere. Others are built into giant machines like the Large Hadron Collider, a powerful particle smasher located in Europe. These experiments are designed to see if, just maybe, a dark matter particle will bump into a regular particle, creating a tiny spark of evidence. So far, no one has seen a dark matter particle directly, but that hasn't stopped the search. In fact, every experiment, even the ones that don't find anything, helps narrow down the possibilities and brings us closer to the truth. Scientists say that even the smallest clue could unlock some of the deepest secrets of the universe. Dark matter remains one of the biggest mysteries in all of science. It is invisible, but its effects are everywhere. We can see its influence in the way galaxies move, in the shapes of galaxy clusters, and in the fingerprints it left on the cosmic microwave background. All of this proves that dark matter is real and powerful, even if we don't yet fully understand it. Studying dark matter is not just about the past, it's also about the future. The more we learn about it, the more we understand the invisible forces that have shaped the universe from the very beginning and continue to shape it today. Dark matter might even be linked to another cosmic mystery, dark energy, a strange force that is making the universe expand faster and faster. By unlocking the secrets of dark matter, scientists hope to learn more about how everything in the cosmos fits together, and what might happen to it billions of years from now. And the journey has only just begun. New missions in space are opening up even more ways to study the hidden universe. The James Webb Space Telescope, launched in the year 2021, is giving scientists the clearest view ever of faraway galaxies, stars, and cosmic structures. By looking farther and deeper than any telescope before, it could help reveal how dark matter shaped the universe from its earliest days. Back here on Earth, researchers are building even more advanced dark matter detectors, some placed deep under mountains, others even floating in space. These devices are designed to catch the faintest signals from dark matter particles. With every new tool and every new discovery, we come one step closer to solving this cosmic mystery. Dark matter may be invisible, but it is one of the most powerful forces in the universe. It has been shaping galaxies and stars since the dawn of time, and while we're still only beginning to understand it, the discoveries we've made so far are incredibly exciting. The discovery of the universe's very first stars is like opening a magical window into the deep, distant past. These ancient stars, known as Population 3 stars, are unlike any stars we see today. What makes them truly special is that they were made from only two basic ingredients, hydrogen and helium. These were the only elements floating around in space shortly after the universe was born in a powerful explosion called the Big Bang. These first stars didn't appear right away. They came to life during the universe's early, wild, and mysterious years, long before galaxies or planets had formed. Today, scientists are using the James Webb Space Telescope, or JWST for short, to search for clues about these stars. This incredible telescope allows us to look back billions of years, almost like using a cosmic time machine to glimpse moments that happened near the beginning of everything. To understand how these stars came to be, we have to go back around 13.8 billion years to the moment of the Big Bang. That was the instant when the universe began, an unimaginably hot and dense explosion that started it all. In just the first few minutes after this event, only the simplest elements could form. These were hydrogen, helium, and tiny traces of lithium. Hydrogen, which is the lightest and most common element in the universe, is made of just one proton. Helium comes next, with 2 protons and 2 neutrons in its nucleus. Together, these elements became the first building blocks of the universe. At that time, heavier elements like carbon, oxygen, and iron didn't exist yet. They would only be created later, deep inside the hearts of stars. In those early days, the universe was a dark and silent place. There were no stars, no galaxies, and no light, just vast clouds of invisible gas. This pitch-black chapter in the universe's story is called the Cosmic Dark Ages, and it lasted for hundreds of millions of years. It was a time of great stillness, but something powerful was slowly beginning to happen. Gravity, the force that pulls objects together, began to work its magic. Over time, gravity started pulling together the floating hydrogen and helium gas, squeezing it tighter and tighter. As these gas clouds collapsed under their own weight, they became hotter and denser. Then, finally, the first stars were born, and with them, the universe lit up for the very first time. These first stars, the population 3 stars, were nothing like the ones we see in our night sky today. They were absolutely massive, many of them hundreds or even thousands of times bigger than our Sun. Because they were so large, they burned their fuel very quickly and lived short, brilliant lives. While stars like our Sun can shine for billions of years, these giants only lived for a few million years before dying in dramatic explosions. Since they were made only of hydrogen and helium, they didn't have any of the heavier elements that stars today contain. That's why scientists gave them the special name Population 3, to separate them from younger stars, which belong to Population 2 and Population 1. The Population 3 stars did something incredibly important. They ended the darkness of the cosmic dark ages. When they began to shine, they released powerful ultraviolet light that changed everything. This light started a major transformation called cosmic reionization. Before this happened, the universe was filled with neutral hydrogen gas, which blocked light from travelling. But the ultraviolet radiation from these early stars had enough energy to knock electrons off hydrogen atoms, turning the gas into ionized hydrogen. This process made space more transparent, allowing light to travel freely for the first time. It was a turning point in the history of the universe. These giant stars may have lived short lives, but their endings were spectacular. They didn't fade away quietly. Instead, they exploded in supernovae, huge cosmic blasts that scattered newly created heavy elements across the universe. During these explosions, elements like carbon, oxygen, iron, and even gold were thrown out into space. These materials would go on to form new stars, planets, and eventually life itself. In this way, the deaths of Population 3 stars were not just endings, they were also beginnings. They planted the seeds of everything that would come after: solar systems, oceans, trees, animals, and even people. Studying these stars is one of the hardest tasks in modern astronomy. Because they are so incredibly far away, the light they gave off has been travelling through space for more than 13 billion years. By the time it reaches Earth, that light is very faint and hard to detect. Instead of seeing the stars directly, scientists look for clues they left behind. One clue is the enormous bubbles of ionized hydrogen that may have formed around them. These bubbles were created by the powerful light from Population 3 stars stripping electrons from the surrounding gas. By measuring the size and shape of these bubbles, astronomers can learn more about the ancient stars that caused them. The study of Population 3 stars isn't just about understanding the past, it's also about discovering how life began. These stars were the first to create the heavy elements needed for life, like carbon and oxygen. Without those elements, planets couldn't form, and neither could living things. By learning how these early stars lived and died, scientists can better understand how our own planet, and all life on it, came to be. Population 3 stars also help answer big questions about the universe. They played a key role in forming galaxies, black holes, and other giant structures in space. By following the story of these stars, from their birth in dark gas clouds to their fiery deaths, we begin to piece together the grand puzzle of how the universe changed and evolved over time. Each new discovery adds another piece to this cosmic puzzle, helping us see the big picture of how everything in space, including us, came to be. Thanks to the incredible power of the James Webb Space Telescope, scientists are now closer than ever to uncovering the secrets of the first stars. JWST is already giving us amazing glimpses into the early universe, and soon it may reveal even more, like how the very first galaxies took shape. Dark energy is one of the most puzzling and fascinating ideas in all of modern science. For many years, scientists have been trying to figure out what it is, but even today, it remains a great mystery. What makes dark energy so strange is that it seems to make up almost 70% of everything in the universe, but we can't see it, touch it, or measure it directly. In fact, we only know it's there because of the strange way it affects the universe around us. Let's imagine this in a simple way. Picture yourself standing in the middle of a quiet room. Suddenly you feel a strong push on your back, but when you turn around, there's no one there. You didn't see who pushed you, but you definitely felt it. That invisible push is a lot like dark energy. We don't know what's doing the pushing, but we can see how it moves things in space. To understand just how important dark energy is, think of the universe as a giant pie. The biggest slice, about 68%, is made of dark energy. Even though it's everywhere, it's completely invisible. We can't observe it with telescopes or any tools we normally use in science, so how do we even know it exists? It all began with a big surprise in the late 1990s. Two different teams of scientists were looking at very distant exploding stars called supernovae. These supernovae are like cosmic lighthouses. Because their brightness is always about the same, they help scientists figure out how far away things are in space. But when scientists measured the distance to these supernovae, they found something shocking. The stars were much farther away than they had expected. This meant the universe was not just expanding, it was expanding faster and faster over time. That was not what anyone had believed before. Until then, most people thought the universe might be slowing down because of gravity. After all, gravity pulls things together. But this new discovery showed the opposite was happening. Something was pushing the universe apart, and that something was given a name: dark energy. To understand this better, think of space as a stretchy fabric, like a rubber sheet. When this fabric expands, everything on it moves away from everything else. Galaxies, which are huge groups of stars, are like little dots on that rubber sheet. As the universe stretches, the galaxies move farther and farther apart. Scientists also compare this to a balloon. When you blow up a balloon, any dots drawn on the surface of the balloon move away from one another. In the universe, dark energy is like the air filling the balloon. It makes the whole thing grow, pushing everything farther apart. But dark energy is no ordinary force. Most forces, like gravity or magnetism, pull things toward each other. But dark energy does the opposite. It pushes things away. And here's something even more curious. It seems to be getting stronger as time goes on. That means the universe isn't just expanding, it's speeding up. Even though scientists know dark energy is doing something important, they still don't really know what it is. There are several ideas, or theories, about what it might be. One idea is called the cosmological constant. This theory was first introduced by the famous scientist Albert Einstein. At first, Einstein thought the universe wasn't expanding or shrinking. It was just staying the same size. To make his equations work, he added something called a cosmological constant, a steady energy that fills space. Later, when it was discovered that the universe really is expanding, Einstein thought his idea was wrong and called it his biggest mistake. But much later, scientists brought the idea back to explain dark energy. In this theory, dark energy is a constant invisible force that fills all of space evenly and doesn't change over time. Another idea is called quintessence. This theory suggests that dark energy is not constant. Instead, it might change from place to place or grow stronger or weaker over time. In this idea, dark energy acts like a strange kind of energy fluid that moves through the universe. Just like a magnetic field can change and shift, this energy might also be changing all the time. Some scientists even think extra dimensions might be involved. We usually think of the universe as having 3 dimensions: length, width, and height, plus one more for time. But some theories suggest there might be more dimensions we can't see. If those extra dimensions really exist, they might be affecting our universe and could help explain the mystery of dark energy. And then there's the idea of modified gravity. Maybe dark energy isn't a force at all. Maybe we just don't fully understand how gravity works over huge distances. Some scientists think that gravity might behave differently across billions of miles. If gravity is weaker than we thought in the far reaches of space, that could explain why galaxies are speeding away from each other, without needing dark energy as a separate force. One of the most powerful tools scientists use to study the universe is something called the Cosmic Microwave Background, or CMB. This is a very faint glow of light that has been travelling through space for almost 14 billion years, ever since the moment the universe began in the Big Bang. You can think of it as the universe's baby picture, a leftover heat from when everything started. Even though it's very faint, it carries a treasure trove of information. By carefully studying tiny patterns and differences in this ancient light, scientists can learn about how the universe looked in its earliest days. These patterns help researchers figure out the shape, size, and even the future of the entire universe. Most importantly, they offer clues about how dark energy might be making the universe expand faster and faster. To investigate dark energy more deeply, scientists around the world have launched a number of major projects. One of the most exciting of these is called the Dark Energy Survey, or DES. This project uses powerful telescopes in the mountains of Chile to take high-quality pictures of the night sky. Since it began in the year 2013, DES has been observing and collecting data from hundreds of millions of galaxies across a huge area of space. By looking at how these galaxies are spread out and how they move, scientists are trying to understand how dark energy has shaped the universe over billions of years. Another major effort to unlock the secrets of dark energy is the Euclid mission, a space telescope launched by the European Space Agency in July of the year 2023. Euclid is now floating far from Earth, observing the universe with incredible precision. It is specially designed to measure the exact shapes, sizes, and locations of galaxies billions of light years away. By creating a giant map of the universe, Euclid will help scientists trace how matter and dark energy are distributed across space and time. But dark energy isn't just about understanding the past. It might also tell us something very important about the future of the universe. Right now, we know that dark energy is causing the universe to expand faster and faster. But what happens if that acceleration continues forever? One possible future is called the Big Rip. In this wild and frightening idea, the force of dark energy would keep growing stronger and stronger. Eventually it might stretch the universe so much that galaxies would fly apart, stars would be ripped to pieces, planets would be torn away from their orbits, and even atoms might be pulled apart. Everything could be destroyed in the end. Thankfully, if the Big Rip does happen, it would likely take tens of billions of years, so we don't need to worry just yet. There's also a very different idea about the future, called the Big Crunch. This could happen if dark energy weakens over time instead of getting stronger. If that happens, the expansion of the universe might slow down, stop, and then reverse. The universe would start shrinking instead of growing. All the galaxies, stars, and planets would begin to move closer together. Eventually, everything might collapse back into one tiny point, just like at the very beginning. The truth is, no one knows for sure what will happen. Dark energy is still one of the biggest mysteries in all of science. We can't see it, we can't touch it, and we can't directly measure it. And yet, it makes up about 70% of the entire universe. It's like an invisible engine that's speeding up the expansion of space, and we're only just beginning to understand it. Scientists aren't even sure what dark energy really is. Some think it might be a kind of constant energy that fills empty space. Others believe it could be something that changes over time, or maybe it's connected to hidden dimensions of space we haven't discovered yet. What we do know is that solving the mystery of dark energy is one of the most important challenges in science today. With new space missions, better telescopes, and smarter technology, we are slowly moving closer to the answer, and one day, perhaps in the not-so-distant future, we may finally understand what dark energy is, and how it will shape the universe for billions of years to come. A biosignature, sometimes called a chemical fossil or a molecular fossil, is any kind of substance or pattern that could be a sign that life exists or once existed on a planet. This evidence might come from an element, a special kind of molecule, or even a strange pattern in the atmosphere. These clues don't have to be living things themselves. They can be leftovers or byproducts of life, like a fingerprint left behind after something was there. Scientists who study astrobiology, the science of life in the universe, depend on biosignatures to help them search for signs of life beyond Earth. These signs can show up in many different forms. For example, some gases or unusual chemical mixes in a planet's air might point to the presence of living things. In other cases, scientists might spot strange rock shapes, tiny fossils, or changes in a planet's light that could all be hints of alien life, whether it's tiny microbes or even advanced civilizations. Biosignatures are grouped into 10 major types, each one offering a different kind of evidence that life might be, or once was, there. Isotope patterns. Living things use elements like carbon or oxygen in very specific ways. When they do, they leave behind isotope patterns, versions of elements with different weights, that are very different from patterns made by non-living processes. Chemical signatures. Some chemicals, like oxygen and methane, can exist together only if something is constantly creating them. That something might be life. Organic matter. Life forms naturally make organic molecules like proteins, fats, and sugars. These can sometimes get trapped in rocks or mud and stay there for millions, or even billions, of years. Biological minerals. Some tiny life forms make minerals in ways that nature alone does not. For example, some bacteria create special crystals of magnetite, which are different from the ones made by volcanoes or other natural forces, microscopic structures. Under a microscope, scientists might see tiny patterns or textures, like microfossils or thin films of bacteria, that suggest living things were once present. Macroscopic structures. On a larger scale, scientists may find big rock formations, like ancient coral reefs or layered rocks called stromatolites, that were built by colonies of microbes long ago. Changes over time. If a planet's atmosphere or surface light changes regularly, like in cycles, it might mean life is changing it, just like Earth's plants affect our oxygen levels. Surface reflectance features. Some life forms have pigments, colour molecules, that change how a surface reflects light. These changes can sometimes be seen from space. Atmospheric gases. Gases like oxygen, methane, and nitrous oxide often come from living organisms. If we find them in the air of another planet, it might mean something alive is there. Technosignatures. These are signs of intelligent life, such as artificial lights, radio signals, or pollution. Things that could not happen on their own in nature. Not every odd pattern or strange chemical mix is a sure sign of life. To be taken seriously, a biosignature has to meet three main rules. Reliability. It must be something that is usually made by life and not easily explained by non-living processes. Survivability. It must be stable enough to last long enough so we can find it. Detectability. We need to have the tools and technology to actually notice and measure it. One big problem is that nature, without life, can sometimes copy the effects of life. For example, volcanoes or chemical reactions in rocks can sometimes release gases like methane or oxygen, tricking scientists into thinking life might be there. So researchers have to be very careful and check every other possible explanation before jumping to conclusions. One clever way scientists do this is by looking for chemical imbalances that don't make sense unless something, possibly life, is keeping them going. For instance, if a planet's air has both oxygen and methane at the same time, that's a big clue. Normally those two gases would react with each other and disappear quickly, so if both are still present, something must be making more of them, possibly some form of life. For a biosignature to be useful, it has to last long enough for our tools, like space probes, telescopes, or maybe even astronauts to find it. One way this happens is through waste left behind when living things use energy. These metabolic byproducts are like footprints of life, showing where it has been. Also, the physical remains of life, such as fossils, can be preserved for a very long time. In fact, scientists have found fossils on Earth that are as old as 3.5 billion years. These preserved signs are some of our best evidence that life existed long ago. However, even if life leaves behind signs, we still need the right tools to find them. Sometimes, our telescopes or instruments aren't powerful enough to detect the tiny changes or signals. Life might exist, but we might miss it simply because our technology isn't advanced enough yet. Some biosignatures are easier to spot than others. For example, oxygen is one of the most promising. On Earth, it's mostly made by plants and microbes during photosynthesis, the process of turning sunlight into energy. It's also needed for many animals to breathe. Oxygen leaves a clear signal in a planet's atmosphere and is easy to detect because it affects how light passes through the air. But there's a catch. Oxygen can also form without life. A process called photolysis, where light breaks apart water or carbon dioxide, can produce oxygen. If a planet loses its water or lacks other gases, oxygen might build up in the air naturally. That's why scientists must be very careful not to mistake a natural process for a sign of life. They need creativity, careful analysis, and deep knowledge to tell the difference between living and non-living causes. And then there's the opposite problem: false negatives. This is when life really is present. but its signs are too faint or hidden for us to notice. Maybe the atmosphere hides the signals, or maybe life exists deep underground where we can't see it. Scientists are studying this problem closely, especially as they prepare for the next generation of telescopes that will study the skies of distant planets. Finding biosignatures isn't just about what's out there. It's also about the tools we use here on Earth. One issue is telescope resolution. If a telescope isn't sharp enough, it might miss subtle signs of life. Also, many telescopes and space missions are designed by large teams of scientists with different goals. Sometimes they have to make trade-offs, like choosing to study a planet's weather instead of focusing entirely on the search for life. This means some biosignatures might be harder to spot simply because the mission wasn't built specifically to look for them. Earth's own history gives us a valuable guide. Our planet has been home to life for billions of years, and much of that life has left behind chemical clues. Fields like geochemistry, geobiology, and geomicrobiology study these ancient traces, helping us understand what biosignatures really look like. Some important examples include microfossils and stromatolites. These are structures built by ancient microbes, sometimes layered in beautiful patterns. Molecular markers, or biomarkers. These are specific molecules made only by life, like certain fatty acids and alcohols. Isotopic patterns. Life tends to use elements like carbon, nitrogen, and hydrogen in ways that leave behind unusual isotope ratios. Metal patterns. Some metals, like iron, molybdenum, chromium, and rare earth elements, change their abundance or isotopic makeup in the presence of life and environmental changes. For example, by analysing the types of fatty acids in a rock, scientists can figure out which kinds of bacteria or archaea once lived there. Long-chain fatty alcohols, especially those with more than 23 carbon atoms, are signs of planktonic bacteria. Other molecules like alkanes, alcohols, and fatty acids with 20 to 36 carbon atoms often come from higher plants. These are usually found in soils and in ancient peat deposits, formed from plant waxes. Life has a way of leaving behind special clues that can tell us it was once present, even if that life disappeared millions or even billions of years ago. These clues are known as biosignatures, and they can take many different forms. Some biosignatures are chemical, like tiny bits of special molecules including DNA, fats, called lipids, proteins, and amino acids, the building blocks of life. Others are strange substances that look like kerogen, which is a kind of fossilized organic matter. Biosignatures can also appear as unusual patterns or shapes in rocks and sediments that hint at something once being alive. Tiny life forms, like microbes, are especially good at changing the environment around them. As they live and grow, they create chemical changes and leave behind marks in the materials they touch. For example, some types of bacteria can make tiny holes in carbonate rocks. Under a microscope, these holes look like little swirls or branches. They're very different from the natural bubbles or spaces found in ordinary rocks. These special patterns can be powerful hints that microbes were once there. But it's important to be cautious, because just finding a strange shape doesn't automatically mean life created it. Sometimes nature itself can make patterns that look biological, even when there was never any life involved. One of the most famous examples of this mystery comes from a Martian meteorite named ALCH 84001, ALCH 84001. This space rock was found in Antarctica and is believed to have come from Mars. Inside it, scientists discovered tiny crystals of a mineral called magnetite, along with tiny shapes that looked a lot like bacteria. At first, many experts were excited. They thought this might be real evidence of ancient life on Mars. But as time passed and more studies were done, most scientists came to believe that the structures were simply too small to be actual fossilized cells. The debate continues, even after more than 25 years, making it one of the longest-running scientific arguments about life beyond Earth. From this case, scientists learned something very important. Morphology, which means the shape or structure of something, can't be used alone as proof of life. Even if something looks like it was made by a living creature, that doesn't mean it really was. People might interpret shapes differently, and that can lead to mistakes. Today, scientists agree that to make a strong case for life, you need more than just shapes. You need chemical evidence and other clues as well. No single chemical or compound can tell us for certain that life once existed. Instead, scientists look for special patterns in organic, carbon-based molecules, patterns that only life is known to create. For instance, when living cells die and break down, they leave behind lipids, or fatty molecules, from their cell membranes. These lipids often show a very regular pattern. They're usually concentrated, have a certain size, and tend to have even numbers of carbon atoms, which doesn't usually happen in non-living chemistry. Similarly, living things only use left-handed amino acids, while random chemistry would produce a mix of left and right-handed ones. This kind of handedness could be another big clue, but biosignatures aren't always about chemistry. They can also appear as magnetic signals. Some types of bacteria leave behind tiny magnetic particles, which can be detected long after the microbes themselves are gone. Chemical biosignatures are usually made of complex molecules built from carbon, hydrogen, and other elements like oxygen, nitrogen, and sulfur. These molecules are sometimes found in things like crude oil or petroleum, where they have been slowly transformed over millions of years from ancient living material. Each biosignature has its own unique fingerprint. The slow transformation of a living matter into oil leaves behind a trail of evidence. Many of the molecules found in oil are very large, with high molecular mass, which helps scientists spot them. Some well-known examples include pristane, steranes, and triterpenes. These chemicals come from plants, especially land-based flowering plants, and are created as the original biological material breaks down over time. When scientists study oil or the rocks it comes from, they look for tiny amounts of these biosignatures using powerful tools like gas chromatography and mass spectrometry. These tools help them identify and measure the different molecules present. By doing this, they can figure out where the oil came from, how old it is, and what kind of environment it formed in. This is why biosignatures in oil are often called chemical fossils. They record the ancient history of life, locked inside molecules. These chemical clues help geologists and chemists follow the journey of oil deposits through underground layers. The exact pattern of biosignatures in a sample can reveal how far the oil has moved or whether it has been contaminated. Because these molecules are very tough and resistant to heat, pressure, and time, they're also useful in other areas, like tracking oil spills or studying polluted lubricants. Still, scientists must be careful when examining raw rock samples, since these can be contaminated or broken down by natural processes over the centuries, making it harder to get accurate results. Now, when it comes to finding life on other planets, scientists often look at atmospheres since they can hold powerful clues. Over time, life changes a planet's atmosphere in ways that natural processes cannot. Earth, for example, has huge amounts of oxygen and small amounts of methane in its air, both gases that come from living things. This strange mix is hard to explain without life. Even the colour of a planet might give away the presence of life. Life that uses sunlight for energy, like plants, often contains special pigments, which reflect light in unique ways. By looking at how a planet reflects light, scientists can guess whether it might have vegetation or something like it. This technique is called studying the planet's reflectance spectrum. Some life forms can even glow under ultraviolet light, which could be seen by powerful telescopes from space. Recently, scientists have started finding gases like hydrogen and methane in the skies of faraway planets. But just spotting these gases isn't enough. We also have to understand how the planet's atmosphere behaves. For example, finding both oxygen and methane on the same planet could be a very strong sign of life. That's because these two gases usually react and cancel each other out, so if they both exist at the same time, something must be constantly producing them, most likely something alive. Other interesting gases to look for include dimethyl sulfide and chloromethane, as well as combinations like methane and carbon dioxide. One of the most exciting recent discoveries is the possible presence of phosphine in the atmosphere of Venus. On Earth, phosphine is mainly made by living organisms, so its presence on another planet could point to life, though more research is still needed. When a planet's atmosphere is out of balance or in disequilibrium, it can be a signal that life is doing something unusual. Earth's atmosphere, for example, has been shaped and changed by life in ways that would never happen through natural chemistry alone. Since Earth is the only place we know for sure has life, scientists often use it as a model. But they also realize that alien life might be very different. It might not use the same chemicals or leave the same kinds of biosignatures we see here. That's why some researchers look for what they call agnostic biosignatures, signs of life that don't depend on Earth-like biology. They believe that all life, no matter how strange, needs energy to survive. And to get energy, there must be some kind of chemical imbalance, a condition that living things can take advantage of. By understanding the balance created by geological, non-living processes, scientists can spot when something is off, which might mean life is present, even if it's nothing like what we've ever seen before. Finding signs of life on another planet, such as a biosignature, is one of the most exciting discoveries scientists can make. A biosignature is something that hints that life, either in the past or present, may exist somewhere beyond Earth. But interestingly, discovering that a planet does not have life can also be just as important. Life depends on special kinds of chemical conditions, especially something known as redox imbalances. This happens when certain chemicals are more likely to either gain or lose electrons, creating energy that living things can use. Now, if a planet has this kind of energy-rich environment, but there's no life around to take advantage of it, that's known as an anti-biosignature. It's like seeing a dinner table full of food, but no one sitting down to eat. It tells us something valuable about the place. It could mean that life never existed there, or that something happened to wipe it out. One fascinating idea related to life is the polyelectrolyte theory of genes. This theory says that for a molecule like DNA, or any similar genetic material, to evolve through natural selection, it needs to have a special repeating structure. In the year 2002, two scientists named Stephen A. Benner and Daniel Hutter suggested that DNA, or any life-forming molecule, must be a polyelectrolyte. That means it contains repeating charge sections that help it work properly in water. Without this structure, the molecule wouldn't be able to evolve. These scientists even came up with ideas for how we might look for such genetic materials on places like Mars, Enceladus, one of Saturn's moons, and Europa, one of Jupiter's moons. One of the most debated questions in the search for life on Mars involves a simple gas, methane. Methane is important because it breaks down quickly in a planet's atmosphere when exposed to sunlight and other natural processes. So if there's a lot more methane than expected, it could mean that something, possibly life, is constantly making more of it. Since the year 2004, different spacecraft and ground-based telescopes have reported detecting methane in the thin atmosphere of Mars. The amounts found have varied quite a bit, from as little as 0.24 to 0.65 parts per billion, and in some rare spots, even as high as 45 parts per billion. These are very tiny amounts, but they still matter. However, more recent data from a very advanced instrument on board the ExoMars Trace Gas Orbiter, which was launched in 2016, told a different story. This spacecraft didn't detect any methane at all, and it set a new upper limit of only 0.05 parts per billion. That's incredibly low, so low that it seems to contradict the earlier findings. This strange difference has only made the mystery of Martian methane even more puzzling. Even more confusing is how fast the methane seems to appear and disappear. Right now, scientists don't fully understand how chemicals behave in Mars' atmosphere. The way methane comes and goes so quickly doesn't match any current model of how gases are supposed to break down. To really solve this mystery, scientists would need to send a lander or robot with a tool called a mass spectrometer. This instrument could study the kinds of carbon atoms in the methane, especially carbon-12 and carbon-14. By comparing the amounts of these carbon types, scientists could figure out if the methane came from living organisms, just like they do here on Earth. There's another piece of the puzzle too. Mars's atmosphere contains a lot of carbon monoxide and hydrogen, two gases that are full of potential energy. On Earth, microbes and other life forms would quickly use up these gases as fuel, but on Mars they seem to just hang around in the air unused. This is another possible anti-biosignature, because it suggests that no life is present to take advantage of the available energy. To some scientists, this could be a clue that life is either not there or has not yet been found. The science that explores life in space is called astrobiology. At its heart is the belief that if life exists beyond Earth, we might be able to recognize it through the clues it leaves behind, like biosignatures. but for a biosignature to really count as proof of life, it must be something that living things are likely to produce, and something that natural non-living processes, known as abiotic processes, are very unlikely to create. To confirm that a biosignature truly comes from life, scientists have to rule out every other possible explanation. Like all major discoveries, finding real evidence of alien life will take time, many experiments, and a lot of careful analysis. Back in the 1970s, NASA made history with its Viking missions to Mars, which were the first to carry out experiments designed to search for signs of life on another planet. The two Viking landers each had 3 different experiments to test whether life, especially microbial life, might be present. They looked for things like metabolism, but unfortunately the results were unclear. Some tests gave hints of something interesting, but others did not, leaving scientists with no final answer. Today, NASA's Curiosity rover is still hard at work on the Martian surface. It is part of the Mars Science Laboratory mission, and its job is to explore whether Mars could have supported life in the past, or maybe still can. Curiosity is equipped with many tools that can search for signs of life, such as organic molecules, possible microbial remains, ancient chemical patterns, and special gases that might have been produced by living things. It focuses on areas where organic matter might be preserved in rocks, which improves the chances of finding ancient fossilized life. At the same time, the ExoMars Trace Gas Orbiter, launched in 2016, continues to study Mars from above. It is mapping where gases like methane come from, and this information is helping scientists decide where to land future missions. One of those missions is the Rosalind Franklin rover, named after the famous scientist who helped discover the structure of DNA. This rover was planned to launch in 2022, and it will be able to drill as deep as 2 meters below the surface of Mars. That's important because under the surface, any signs of life could be better protected from the harsh radiation that hits the planet's surface every day. Another mission, called the Mars 2020 rover, also known as Perseverance, launched in the year 2020. Its goal is to study parts of Mars that may once have had the right conditions for life. It is exploring the rocks, soil, and ancient environments of the planet to find out more about its history and whether it was ever habitable. Perseverance is also collecting rock and soil samples that could one day be brought back to Earth, where scientists can study them with even more powerful tools than those sent to space. When we look beyond the planet Mars in our search for life, one exciting mission that stands out is NASA's Dragonfly mission. This mission is planned to launch in the year 2025, and it will head toward Titan, the biggest moon of the planet Saturn. Titan is a fascinating place because it has a thick atmosphere filled with complex carbon-based chemicals. Scientists believe that Titan may have the right conditions for early forms of life to begin, or for what is known as prebiotic chemistry, the kind of chemistry that might have happened on Earth before life actually started. The Dragonfly spacecraft is not just going to fly past Titan, it will actually land there and explore its surface and skies. It will search for biosignatures, which are signs that life might have existed in the past, or could even exist now. By flying from one location to another like a drone, Dragonfly will study the moon's atmosphere, the icy ground, and the mysterious organic materials that cover it. The hope is to find out whether Titan, even though it is so far from the sun and extremely cold, might still be a home for life. Another amazing mission is the Europa Clipper, which will explore Europa, one of the smaller moons orbiting the giant planet Jupiter. This spacecraft is set to launch in October of the year 2024, and it is expected to arrive at Europa in April of the year 2030. Instead of landing, Europa Clipper will fly by the moon many times to collect data. Its main goal is to find out if Europa, which is covered in thick ice, could have an ocean of liquid water underneath, and whether that ocean could support life. Scientists are especially interested in Europa because they believe that underneath its frozen surface lies a huge salty ocean. In fact, this hidden ocean might contain 2 to 3 times more water than all the oceans on Earth combined. Here's some of the evidence that supports this exciting idea. In the year 1979, NASA's Voyager 1 spacecraft took the first close-up pictures of Europa. The images showed strange surface features that looked like cracks or ridges, similar to what we see with tectonic activity on Earth. Scientists thought this might be caused by an ocean below pushing and shifting the ice above. In 1997, NASA's Galileo spacecraft noticed a small change in Europa's magnetic field as it flew past. This was taken as a strong clue that something conducting electricity, like a salty ocean, was hiding under the ice. Then, in 2012, the Hubble Space Telescope captured something astonishing: a giant plume of water vapour erupting into space from Europa's surface. This suggested that water from the ocean below might be escaping through cracks in the ice. The Europa Clipper will carry special instruments to investigate further. It will try to confirm if the ocean really exists, find out what it's made of, map the icy surface, and search for any signs of activity linked to that deep ocean. All of this could help us answer the big question: could life survive in such a place? Now let's talk about another moon with a hidden ocean, Enceladus, a small moon orbiting Saturn. While there isn't a mission yet that's specifically designed to search for life on Enceladus, this little moon has shown some amazing signs that make scientists very curious. In the year 2005, NASA's Cassini spacecraft spotted jets of water vapour shooting out from cracks near Enceladus's south pole. These geysers were later found to contain salt and organic molecules, the kinds of chemicals that life might need. Then in 2014, more detailed measurements supported the idea that a huge underground ocean exists beneath Enceladus's icy shell. Because of all this, many scientists hope that future missions will visit Enceladus and look for signs of life there too. But what about life outside our solar system? The closest potentially habitable planet beyond our Sun is called Proxima Centauri b. It orbits a star that is only 4.2 light-years away. In space terms, that's actually quite nearby. But even at that short distance, using today's spacecraft technology, it would take more than 18,000 years to reach it. That means we can't visit it anytime soon. Instead, scientists use powerful telescopes to study planets like Proxima Centauri b from afar, hoping to spot signs that life might exist there. So far, scientists have not yet found any confirmed signs of life on exoplanets, planets outside our solar system. However, this field of research is growing fast. A big step forward came in December of the year 2021 when NASA launched the James Webb Space Telescope. Although the Webb telescope can't detect certain key gases like oxygen in the atmospheres of exoplanets, it can still spot clues, such as chemical patterns or temperature changes, that might hint at life. Looking toward the future, new telescopes being built on Earth, like the 30-meter telescope and the extremely large telescope, will allow scientists to study the atmospheres of distant planets in much greater detail. These massive telescopes will be able to separate real signs of life from false positives, such as oxygen that might be produced by things other than living creatures.